Welcome, everybody. Wow. Hi. Welcome to the first annual Comic-Con in San Diego. Yay. My name is Alex, and I run operations at Comma. And this is George. I think some of you guys might know him.
If you're going to change the world, there's no point if you're just going to change the world like everybody else. Maybe I'll borrow a slogan, think different. Welcome to Comic-Con. I think you guys are going to enjoy it. You know, in 10 years, people are going to be like, you were there for the beginning. Thank you all for being here.
You know, at Comma, our mission is to solve self-driving cars while delivering shippable intermediaries. Today, you're going to learn about, the history of Comma, where we came from, where we are right now, and where we're going. It is my pleasure to bring to the stage one of our hardware engineers, Robbe Derks.
Hi, welcome everybody. How's everybody doing? Good? Great. Let's wait for my presentation to start. Cool, so I'm Robbe. I'm one of the hardware engineers, and today we're going to talk about how Comma actually works. Clicker not working. It's on. Oh, there it is. A little slow. We go to the next slide, please. No. So today we're here to answer the question, how can something like Comma exist? So we support most of the cars that have been shipped in the last 5 years. And how does this actually work? Because if you think about it, we have all these different brands. They all work slightly differently. You would think they would all have different standards. But somehow we managed to build a system with only a few engineers, which works on most of the cars that are sold in the last few years. So, how does a modern car actually work? I mean, probably most of you already know that most cars are now filled with a bunch of electronics. So we have a bunch of connectivity going on. We have the comfort system. We have the powertrain stuff, which runs the engine. We have an infotainment system. But most importantly, most modern cars also ship with an ADAS system. So what does ADAS stand for? Clicker's not working great. There it is. Top, yeah, I'm pressing the top one. It's not doing anything. One back. There you go. So an advanced driver assistance system. So this means this is a system that's built for safety and for comfort. So it has both lane keep assist, which keeps you inside of the lane if you're not paying attention. Probably doesn't work very well on your car. But it also has stuff like ACC, adaptive cruise control, to keep distance with the car in front of you. And what we really care about is that the system has control over the gas and the brakes. This is really important for us because that's obviously something we want to control. Cool. So how does this ADAS system look in most cars? So usually you have two systems which do the ADAS, which is the radar, and you have the vision system. So those are used. The radar system is used to measure the distance with the car in front of you, and you also have the vision system to look at the lanes and give some more visual clues into the system. These then send messages over to the actuators, such as gas, brakes, and steering, which then control your car. Cool. So if we look at this from a topology perspective, we have all these different systems. So usually you have the ADAS camera and the radar, which we already talked about. You have brake systems, power steering, engine control sensors, diagnostic stuff. There's infotainment, user interface, all the buttons in your car. Everything that's electrical in your car is connected over these bus systems. On most cars, these are actually divided up into 3 different buses. Keep pressing. Oh, it's the bottom one. I see now. So you have the powertrain bus, which is the most important one. So this runs all your engine control stuff. You have a body bus, which is a little bit less important. This runs like your infotainment system and all the other buttons in your car. And then there's one extra bus, which is a radar bus. Usually they separate this one out because there's a lot of data going on it, so we don't want to have all that data on the other buses. So if we want to control the car, like where do we want to be? Well, first of all, we want to get the radar points, but we also want to see what the camera is actually sending. So you have all these bus systems. But what's actually going on these buses? Well, all these buses use a protocol that's called CAN bus. This is used in most cars, and it basically consists of these messages which have an identifier and a data portion, and they get sent around the bus, providing all the data to the other modules. So this is, for example, one of the messages that goes around on the bus. So you can see there's two lines there. They go out to each other, which means this is a dominant bit, and you have recessive bits. And these then make up the identifier and the data portion and some other stuff we don't really care about. So why do all the cars use CAN bus? I mean, this is kind of a wonder, right? Like you have all these cars, they're all made by different brands, and somehow they all ended up with the same kind of bus system. Well, it turns out that in 1996, when cars weren't very electronically complex yet, they all were mandated to use a diagnostics port, so which is called an OBD2 port. You guys probably have seen this already, like below your dashboard. There's a port which is used for diagnostics. In the specification, like it mentioned, that you can use one of 5 buses, of which the most common one was CAN bus, and so all the car manufacturers just chose the CAN bus and just went with it. Now, cars weren't very complex back then, so we usually only had this one CAN bus going on. But after that, like they merged out, and when they built all electronic systems, they just went with what they already knew, and they just went with CAN bus. Cool. Now we know how a car like kind of works on the inside. Like, how do we actually take control over the car? So, controlling the car is basically 3 different steps. So first, we have to connect to the CAN buses. After that, we have to figure out which message is which, because they just have an identifier, which is a number, and they have a data portion, which just looks like random garbage. And then after that, we have to intercept it and send better control messages. So let's first look at how we connect to the CAN bus. So if you go back to this topology, like I already said, like we really care about the data on the radar bus, and we care about the messages which the ADAS camera can send to the rest of the car. So the ADAS camera is in control of joining the radar and the vision data, and then providing all the ACC messages which control gas and brakes, and then also the lane keep assist messages which can put torque on the steering wheel to steer your car. So where do we want to tap off? We want to tap off. Oh, there you go. Back. There you go. So we want to tap off at this point. This point is kind of ideal because it's right in the cabin. Like this ADAS camera is located behind your rearview mirror. So that's the ideal spot to tap off these buses. You don't have to mess around in the engine compartment or anything. You can just take this connector, take it out, and then mess with it there. So if we simplify this diagram, so we have the radar system, which sends messages to the camera, and then the camera system sends messages to the rest of the car. So what do? We just connect to the radar. We split apart the camera and the rest of the car, and then use a scan-to-USB interface to actually talk to the car. The scan-to-USB interface is called the Panda, and then the openpilot device is the part that runs all the application code, all the machine learning models, which actually then figures out which messages to send. So to connect to the car, we used to make this thing called the giraffe. Maybe some of you who've been around for a long time still remember the giraffe. And we have the Panda. If it ever comes up, there's the Panda. This is the white Panda. This is the first one we sold. And as you can see, this is basically just an OBD2 port, which has 3 CAN buses on it, and it has a USB connection to go to the openpilot device, which we used to sell, which was the Eon. This is just a photo in a 3D printed case with a heatsink. It's pretty simple. Cool. So if you put this all together, it kind of looks like this. So it's not the cleanest setup. Like your camera cover is gone. Like giraffe is just bungling down there. There's the Panda plugged in. You have a USB connection, which is kind of flaky. And then the device mounted to your windshield. So what about these giraffes? So we used to have basically like 4 types of giraffes. These are the main ones that we sold. So we had the Toyota one, which is common for all Toyotas. Then we had the Honda Bosch one, which is for Honda cars, but then with a Bosch camera installed. And then we also had Honda harnesses for the NIDAC camera system. Now we actually have 2 versions because anybody spot the difference? I mean, this connector is upside down on one of them. So if one day, like NIDAC decided it would be really funny to like flip the connector around, so we had to make another harness. Cool, so giraffes. So it's not a very clean install. You saw that in the picture. There's a bunch of switches on it. So if like an openpilot device is not connected, the car buses will still be separated. So your car thinks the camera isn't there, the radar isn't there, so it throws all sorts of faults. There's also like a lot of variants, they're all very different. They're hard to manufacture because they're so different. And it's also terrible naming. Like, who knows what you're talking about if you're talking about your giraffe? So giraffes are canceled. So then we went, on 2019, we rethought this whole ecosystem, and we came up with what's called the car harness. So car harness is a very clean install. You can put it all behind your camera cover. There's no switches anymore. So if you disconnect your device, it actually has a relay inside, which switches your buses back together. So if you unplug your openpilot device, your car will just think there's nothing happened, and everything will work great. Car is happy. So this whole system is very generic. So we have like the cabling system, we have the stuff that plugs into the OBD port, which is generic for every car. We have the harness block, which we manufactured. This has the relay in it and the other switching logic. And then there's one custom connector for every car, which is the car harness connector. So this one's very easy to manufacture because most things are common, and it's also a great naming scheme. Like everybody knows what you're talking about if you're talking about a harness. Cool. So we have all these different car harness connectors because like at this time we support, I think, 134 different cars, not only Toyota and Honda anymore. So we have all these different connectors. We get all of these made. So we have 2 for Honda, which we already saw. We have the NIDAC one and the Bosch one. Like now that there's a harness connector, we can actually just flip it around and it still fits. We have the Toyota one, we have the Nissan one, which also has 2. We have a VW one, we have an FCA one, a Subaru one. And then there's Hyundai. They apparently didn't think it was necessary to make a standard in their company. Like most of these actually use the same connector, but some of the like buses, they just like pretended it was funny to flip the high and the low pair, and it's like, okay, ship a car that way. So we connected to the car buses. This is already figured out. Now, how do we know which message is which? Because we have all these messages going on. As you can see, like we did a log of all the messages on the CAN bus. This is a video of the actual drive, and then you have all these messages going on. There's actually a lot more. There's a whole bunch of messages. And you all have this identifier, and then a bunch of random bytes, which change during the drive. So how do you figure out how to, what part is which? Well, this takes quite a bit of reverse engineering effort, which we built a tool for called Cabana. I think Drew's going to do a lightning talk, and he's going to talk a little bit more about how to use this. But as you can see, like you can label all this data once you figure out which is which. And then we can actually see like, okay, this message is actually for like wheel speeds. So you have the 4 different wheels of the car. So we figured that out. You can plot this value. So you can see it corresponds with the picture now where it's stationary for a while and suddenly you start moving and see all the wheel speeds of the car. Cool. Now we have all the messages figured out. Where do we actually store these definitions? So what industry standard for these definitions is called a DBC file, which is basically a definition file for every CAN message on the bus. So it's just this large text file which specifies, like, okay, this identifier is called this message, these bits in this message say this. Now these aren't available from any car manufacturers because there are like internal secrets. So we created this project called OpenDBC, which we host on GitHub, which has all these reverse engineered DBC files for all the cars we support. So as you can see, this is the one for the Civic, which we were looking at before. So this is, for example, the wheel speed message we were looking at with all the 4 wheel speeds, and then also a checksum to make sure the message arrived correctly. So what kind of messages go around on the bus? So you have sensor values, button states. So if you press a button, like a bit toggles. There's control messages going on saying like, okay, I want to accelerate by X amount of meters per second squared. There's stuff about like what shows up on your dashboard, so you can throw arrow messages on the dash. There's the radar points going on from the radar, et cetera, et cetera. Okay, we figured out which message is which and how to connect to the CAN bus. What's left? Well, we just need to figure out like which message to actually send. Like how do we figure out what a better message is to keep you inside of the lanes and not just like drive out of the lanes and then bounce back. So we actually want to stay in the middle of the lane. Well, for this, we need to look at openpilot without all the fluff. So openpilot is made up of all these services which talk to each other. Each service has this one specific purpose. We call them daemons, so that's why every one of them ends with a D. So it's camera D, model D, sensor D, controls D, etc. So we have the camera D, which is responsible for sending camera frames to the model. And the model D just runs our AI models on them and actually outputs the information we care about. So for example, we have camera frame with the model input overlaid. Then we have sensor D, which takes all the values that the sensor outputs, and then those get all sent to controls D. Controls D is this big blob of code. It's mostly mathematics with like path planning and stuff, which we'll look into a little bit more. Controls D then actually generates the car-specific messages you want to send, which are then forwarded to the Panda or CAN to USB interface, and then the Panda sends them over to the car such that the car is happy. So that's our, let's go back one more. So that's our Panda inside of the comma.ai. If you open up the case, that's what you'll see. So there's an STM microcontroller in here, which provides USB to the phone, and then it has this OBDC connector, which outputs the CAN buses back to the car. And then here's the harness connector installed in the car. So after that, we'll look a little bit into what Control Z is doing. So Control Z basically exists of like 3 big layers. So the top layer is the general longitudinal and lateral planning. So this basically means, okay, the model outputs, we want to be on this path, but you're actually over here. Like, what's the actual best plan to get on the path that the model wants you to be at? So this then gets output to the control loops, which are very generic. So they're all in SI units or in like meters and meters per second squared and stuff like this. And they actually go from the path to like the curvature you want to be in. And then the curvature gets converted into an angle, and then the angle gets into a control loop, which then provides how much torque you actually want to put on the wheel to get to that path. Beneath all of this, which is all generic, there's all the car interfaces. So each car make we support has its own little interface, which basically specifies, okay, like how do we want to send these messages, at what rate, how do we fill them in, et cetera, et cetera. What are the car-specific limitations? And on average, we managed to support 134 cars with only, on average, 45 lines of code per car. So this is really easy to maintain. We also don't really have to own all these cars, because a lot of this code actually comes from the community. We only own, I think, 6 cars at Comma. So a lot of this comes from community contribution, which is really nice. Okay, so now we figured out how to control a car, right? So talk should be over. Well, no, there's a fourth thing. You have to make sure that it's actually safe. Because obviously you don't want to be on the highway and then your wheels suddenly start spinning like this. That's not a good thing. So how do we figure this out? Well, from the beginning, Comma set out to be very safe. So we made this one text file explaining very concisely what our safety model is. And this basically boils down to 2 points. So the first is that the driver always needs to be attentive and ready to take over at all times. So comma.ai is a level 2 system, which means that it requires the driver to always be attentive, and if it messes up, that the driver needs to be able to take over. We do this by enforcing that if you, for example, press the brakes or the gas, that openpilot disengages and you have full control over the car again. The second part means that the vehicle shouldn't alter its trajectory too fast for a human to take over. So for example, if you're going fast on a highway, you don't want the car to swerve suddenly and steer you off the road. This is enforced in our Panda safety library. So the Panda safety library is this piece of code which runs on a Panda. It runs on an STM32, which is an SLB-rated microcontroller. And this code is meant to be very simple. So it doesn't use a lot of external libraries. It's very easy to reason about. And this basically has this basically enforces, like, for every message, if it's safe to send this message or not. So if you're going on a highway and you want to suddenly steer very hard, the Panda's not going to allow that. So even if like somebody messes with openpilot code and you introduce a bug or anything, the Panda will not allow this message to be sent to ensure that you're safe. So quick example. For example, on the Toyota, there's this acceleration message, which has ID number 0x343. And in it has a 16-bit signed value, which basically tells the car to accelerate or decelerate. It's divided by 1,000, so in the end you get up with the limit, you end up with the limits minus 32 and 32 meters per second squared. Now, I'm sure that a lot of you know that 1G is like 9 meters per second squared, so this is quite a big range. So you don't want your car to suddenly slam on the brakes with 3 Gs of force. So the Panda enforces these limits. So we have a limit between minus 3, which is pretty hard braking, and we have a limit of 1.5, which is pretty fast acceleration, but still within our safety model. So the Panda gets messages. It checks if it's in between these limits. And if it is, it'll allow the message. If it's outside of this limit, it'll block the message and you'll be safe. So, to circle back to the beginning of our talk, how can something like comma exist? I think it boils down to 3 different points. So first, the cars are more similar than they look at first glance. So we know with all the OBD2 stuff that they all ended up using CAN bus, except for a few German brands which use Flexway, but whatever. So they're all using CAN bus. They all have the same generic setup with the radar connected to the camera and then the camera sending messages to the rest of the car. That's very nice. They're all accessible from the cabin, so it's very easy to build the hardware. Then the second point is that most of the code base is very generic. So you saw that, for example, controls D, which should be the one generating the messages, is even mostly car independent. So all the planner stuff, all the control stuff is very car independent. And then finally, the hardware difference is also abstracted away with the car harness. So most of our hardware system is very generic, with only the car harness connector being the part that really differentiates them. Thank you. Is there any questions? Yes, I'm not sure if everybody heard the question, but the question is, do we run into issues with OEM systems detecting that we are sending the messages instead of the car itself?
Yeah, because you're tapping into the canvas network.
Yes. No, this doesn't really happen. Because for one, we just cut the CAN bus in half. We have all these messages, and the Panda forwards every message that comes through, which we don't care about. So if there's something with like button states or something, it just passes it through and the car doesn't even know it was there. Then second of all, we use the same structure that the ADAS system uses itself. So we just replace the control messages it would send, so the car doesn't really know who is sending the messages, like if it's either the ADAS system or if it's openpilot. So it completely mimics the internal car system. So, yeah. Yes. So the question is about Tesla. Actually, I own a Tesla myself. So that's probably why it's one of the carports. So I have an AP2 Tesla. There's the autopilot module, which is behind the glove box. It also has this one connector, which goes to the radar and to the car. So I also built a harness for that. So I'm intercepting that, and I'm sending messages as if I was the autopilot system. Now, there's also the people who have very early Teslas, which don't have the AP system, so which don't have autopilot. So those are also pretty big in our community with adding openpilot to their car.
So how do the two compare, since you have a perfect configuration to compare?
I think openpilot is a lot nicer on the highway, at least. I don't have longitudinal control on my Tesla yet. So Tesla's still doing gas and brakes, so I still have all the ghost braking issues that Tesla deals with. But on the other hand, I think the the lateral control is really nice from OpenPilot. So, yeah.
Thanks. First, thanks for the presentation. It was really great.
Thank you.
How do you come up with the values like the 0.3 for deceleration? Like, is there any better way to do it besides just following each other around and brake checking each other until?
Yes, there is actually a better way. So there's this body called ISO, which enforces these limits on car manufacturers themselves. So they publish all these specs, all these standards, which say like, okay, to have a safe ADAS system, a safe ACC system, you need to be between these limits. So we looked at those limits and we actually enforced those. I think on some of our actuator values were even like slightly below the ISO limits. So there's just from testing ourselves, we found out these limits to be very safe. So the question was, how are the claims about safety validated? Well, the Panda safety is this part of the C code, which is very generic. So it doesn't have a lot of interface with the rest of the Panda code. So we actually built this into a shared library ourselves. And then every time there's changes, it runs through automated CI tests. So we actually try to break it. So we have all these unit tests on the code, which test every limit it enforces and make sure that these limits are always enforced. Also, we try to be implementing the ISO 26262 standard, which is also one of the C safety definitions, which is, I mean, it's just good practice if you're writing any of these codes.
Yeah, actually, I was going to ask about that ISO 26262 and if you need to be certified to it. And how are you reaching that through software testing or and the hardware?
Well, some of this just comes down to static code analysis. So for this, we also have automated tools to test this. But on the other hand, it's still a level 2 system. So we need to ensure that this code doesn't mess up, which we do with our automated tests. And other than that, we also still have the limits which are usually present in the ECUs of the cars. So if you send a torque limit a torque value that's too high in, for example, a Honda car, it won't even accept that message. So even on top of that, there's the ECU safety, which is in the car itself.
So also, ISO is a standard, not a regulation. So there's no certification body. You self-certify that you comply with it. I think you're also looking for MISRA C.
Oh, MISRA C, yeah, that was the name I was looking for.
So MISRA, you're using MISRA C and not AutoSAR C++, or?
We're using CPP check to check all the MISRA regulations, yeah.
I was wondering, how do you get like can you get radar data from the blind spot monitoring, the 2 radars on the back of the car?
Yeah, so that depends on the car. So on some cars, the blind spot radars are actually available from the powertrain CAN bus. On some cars they aren't, but also on a lot of cars we see that they don't actually output any radar points. So they actually only output like if there's a car in the blind spot or not, so it's only 1 bit, so it's not extremely useful. We still use it though for our lane change stuff, so we check that there's no car there if we have the data. But we're also working on trying to get more data out of the blind spot radars because they seem very interesting for the future of comma.
Thanks for the presentation. The car harness, will it have ability to accept more cameras in the future? Or I know George is all about the 1 camera because it's, the potential is not fulfilled, but going forward.
We don't actually use the camera images coming from the ADAS camera because it doesn't actually send that data out over the CAN bus. So we use our own internal camera in our openpilot device. So the comma 2, which we now sell, which has 1 camera, and for most stuff we do, that should be enough.
Could you maybe speak to your hardware fail-safes if there's like a catastrophic failure in the comma system that reconnects the CAN bus and the car is able to?
Yeah.
Is it like an analog sort of thing on the board?
It is implemented in hardware, yes. So we have this relay which is powered by the Panda. So the Panda says, okay, I want to be in control, which then actuates a relay, splitting the buses apart, and then actually starts forwarding the messages. Now, this can fail in 2 ways. So either the relay stays closed, which is very easy to detect. So you just see like if a message still went through, which you didn't expect to go through. And another way it can fail is that it stays open, and then the car just will fault because it doesn't see all the messages because we're not sending everything.
And OEM cars fall in the safe way?
OEM cars tend to fall in a safe way, yes. Yeah.
Anyone else with a question?
My question is also in regard to the range limits. Do you always know that if it's out of range that you can safely throw it away, or would you consider limiting it? And second one is, if it's like on the lower end of the range and the higher end of the range, is that also kind of something you consider when executing those messages?
Yes, so a lot of these limits in the safety code are actually based on speed as well. So torque limits are based on speed. Second, if we drop a message, like this, in practice, this shouldn't really happen. Like this only happens if the openpilot code messes up or if there's a bug. Because in the openpilot code, we also tend to want to stay within those limits. So usually we stay in those limits and everything's fine. If we do go outside of these limits, and this would pose a safety issue, then we would just block the message and go on with our day. If this continues for a long time, and a lot of these messages get dropped, then the car will start complaining because it does expect a certain frequency of these messages.
Great, I've got a question back here.
So I think I have a question about hardware and OEMs potentially in the future locking out foreign parts. And the reason why I have this thought is because I saw videos on like the right to repair and how different companies make it hard to repair their software without, their signed specific hardware. And I was wondering, is this something comma is going to consider in the future where it's not a problem now, but OEMs might make it so that only certain pieces of hardware can communicate with their systems to control the car?
Yes. So, well, first of all, we tend to use the same message structure as the internal components itself. So as long as there's not any signing going on, the car doesn't even know the difference between their own internal modules and what we are sending. Second of all, there has been some very recent car implementations which do use the signing, and that's something we're working on.
I'll break it if I need to.
All right, so I just have a question. I think it's similar to what was asked before, but rather than dropping the package, would it be better to just clamp it to the maximum value that the limit you enforce?
Well, that's an interesting question. Well, we don't do this because we don't want the Panda safety code to actually start generating messages. So the Panda safety code is designed from the bottom up to only be able to read messages and block them. If we don't do this, if we actually allow the Panda to generate messages, this will make the system very hard to reason about. So you'll have openpilot, which we log, then sending a message, and the car reacting differently than what we expect. So we just drop the message, and then we know this is very easy to reason about, and we know what the car will actually do. Now, in practice, this doesn't really happen, because openpilot is pretty good at keeping it between the limits.
Great, and we're sending a mic upstairs so you guys we can hear you. Does anyone else have a question down here?
Did you guys ever, or do you plan to maybe modify the firmware on any existing car modules? Let's say if you need to get around some limit that's arbitrarily too low or too high on the OEM side.
This is something that's been going around in the community a little bit. We don't actively endorse this or support this. But there is some people who have figured out how to alter these limits, especially on the Honda cars, which have a pretty low steering limit. So yeah, we do block these users if they change them to unsafe values, though.
Hey, thanks again for great presentation. One note, it would be nice if you guys put it into some kind of document, like explaining architecture and all that, because it's very useful for somebody starting. Another thing I wanted to ask, with the cars, for the cars with the weird arrangement, like Hyundai, they have radar connected to different places. What is comma planning to do about it?
Well, some of the cars have a slightly different topology. So I know on one of the cars, for example, the ADAS camera sends to the radar, and then the radar forwards it to the rest of the car. Usually we do find a way to tap into those cars as well, though. Sometimes we just tap it off of the camera and only control the lateral part of the steering. So we just control steering and not gas and brakes, which is an easy workaround. But there's also other harnesses floating around which actually do pull it off on split the bus at a different point, which makes us control the rest of the car.
Great. Got a question down here.
Given that most of our cars are only designed to keep ourselves within the lane, and we're extending that to more active use of the steering motors, have you done any research into if that shortens the lifespan of our steering motors, what the implications might be there?
Well, I think we can say pretty certainly that this doesn't, because these motors, they're not actually meant to provide the ADAS system, so not for lane keep assist, but they're actually there to provide power steering. So they actually put so much torque on the wheel when you're like just flinging the wheel around yourself. They actually put way more torque on the wheel than we would just driving it through the ADAS messages. So this wouldn't hit any hardware limitations at all.
For the DBCs you guys reverse engineer, do the companies care? Do they say anything, provide you guys feedback?
I'm not sure if we ever got any feedback on it, but I'm pretty sure they don't probably even know it exists.
Like header files, they can't be copyrighted?
Out of curiosity, how does CanFD affect things? Is that something that you guys need to consider? And what are your thoughts on it?
Oh, CanFD. That's, I think we're going to talk about that a little more today, so I'm not going to say too much.
So when you connect a device like Carista to your OBD, and you can unlock some features like cracking the windows from your key, do you have any messages like that you can use? It's not really related to self-driving, but maybe you can detect that the car is getting hot or something and then just crack the windows.
Well, yes. I mean, we have access to the CAN bus, so we can send any message we'd like. This is not something we'll support officially, of course, but if people are running forks, so modified versions of openpilot, they can certainly implement this stuff.
Great. Do we have any more questions down here? Oh, got it here.
Is there any plans for weather-related or road condition, speed limits or checks? Say, freezing cold mountain pass, and you gotta limit the torque a bit so that your safety increases.
No, I think this is more of a question for the next speaker or research head, because this is more an openpilot question. There's not really any low-level implementation needed there.
So we hear a lot about Tesla over-the-air updates. Do they go deep enough that they would interfere with you? Would they be able to break your connection and break your control over the car with an over-the-air update?
I don't think so. No. I mean, we're just tapping off the bus. They don't even know we're there. So.
Are there any concerns with manufacturers like forking openpilot and creating their own version of it in some way? Or like, are they concerned with you guys at all? Do you have any comments on that?
I don't know if they're concerned or not, but I mean, it's an open source project, it's MIT licensed, so they're free to do whatever they want with it.
Okay, is there another question over here?
Sorry, could you quickly speak to what kind of hardware you use? Are you mostly microcontroller based? Do you have FPGAs on board? And what kind of latency throughput problems do you have between sending and receiving messages to like the core openpilot and back into the system?
I can't really come up with a number about the total latency, but we do run all of our stuff at 100 Hertz, and that seems to be more than fast enough to get the throughput we need. Canon is also not a time-triggered system, so if the message comes a little bit later, like nobody cares about this. As far as which kind of hardware we use, on the Panda it's mainly an STM32F4 microcontroller, which runs all the low-level embedded real-time stuff. And then on the hardware side, we have a phone which runs all the openpilot codes, basically.
There are several features that use OBD ports, like some of the insurance companies now have dongles, and T-Mobile has a dongle. Have you had any thoughts about integrating with such things or ways to make them work? Do I have to pull my comma if I want to get a better insurance rate?
We don't work with these kind of companies. We're a pretty small team, so these are all features that are not really that related to self-driving. So I don't think we'll spend much time in integrating this. But as I said, like, it's an open source project, so if anybody wants to make these modifications, they're more than welcome to.
Are there any other evolutionary changes that you guys are thinking about, like car-to-car communication or anything else?
There's some stuff going on, as alluded by one of the questions. So CanFD is an upcoming standard, which basically makes sure that the CAN bus can handle a lot more data throughput. And this is also something we're looking into.
Great. Do we have any other questions down here?
Thank you. So for combustion cars, you guys probably send a message to VCU first, and VCU is going to send the talk command to the engine. But like for e-cars, the Panda probably can do it can directly send the torque command to inverter. Have you guys tried that?
You mean how do we send the commands to the inverter of an electric car?
Yeah, for e-cars, you can use Panda directly send the torque command to inverter and kind of bypass the ECU. So.
Now, fundamentally, these systems aren't very different. So there's still an ACC system, which is very similar to non-electric cars. And they also still send the command which says like, okay, I want this amount of acceleration or braking. And the inverter will handle this exactly the same way as a regular fossil fuel car would.
Great. If we don't have, oh, we got some more questions on here.
A lot of questions.
Is there any worry as more cars have over-the-air updates that they could roll out something like the RAV4 Prime encrypted CAN bus, where you could have a vehicle that works and then over the air that encryption is rolled out, or is that too low level to worry about that in the future?
I wouldn't be worried about that. If you have a car right now which doesn't have any encryption going on, they're not going to be able to do this over the air. Like most of these cars don't even have over-the-air updates. I think Tesla is the only big manufacturer which really has that at the moment. But also this encryption stuff usually requires a more advanced microcontroller than all of the ECUs. So they can't just upgrade that over the air, so wouldn't be too worried.
Hey, can you also elaborate a little bit on the next version of hardware? What is in the to-do list? Like, what are you guys working for?
I'm sorry, I didn't fully understand.
Like next version of the hardware? What is in?
I mean, what's in the pipeline hardware-wise? Yeah. Oh, it's not
just high level.
It's not my point to talk about today.
Have you considered building like a flash utility in the openpilot so you can actually do updates at the ECU level, like true OTA updates, like for your car's controllers?
Well, no, because for one part, we don't really want to do ECU updates. This touches a lot of the safety stuff, which is internal to the car. And second of all, we don't really need to do this. Like most cars have a pretty good interface as it is. So this is pretty complex, and we wouldn't want to support this for all the different cars, obviously.
Great. If that's it, I will thank you so much, Robbe.
Thank you.
I'm very excited to bring to the stage Harald, our CTO, who runs research. Where did he go? All right. That's important.
Thank you. Good morning, good morning. So I'm Harald from research, and I'm going to give an overview of the kind of work we do at Comma. So our stated goal at Comma is to build a superhuman driving agent, which is basically a level 5 self-driving car. And I'll talk about the way we're trying to achieve that. First, I'm going to test my pointers. Right, that works. Oh. That did something. So before we can talk about how to build a self-driving car, it's important that we have a very clear definition of what it is that we're trying to achieve. So to build a real self-driving car, I think the first obvious thing we want is that it doesn't crash. Crashing would be bad. We can't expect it to never crash because that's very difficult. So crashing less than an average human, I think, is a good minimum goal. Another problem is that you also want it to get you somewhere. If it doesn't get you anywhere, it's not that practical. And for it to be really useful, we wanted to drive on basically all the roads that a human would have no problem navigating. So just your average driver with a driver's license, our self-driving car should be able to do the same things. It shouldn't, oh, I don't know why that happened. It shouldn't satisfy these things just by being super slow and avoiding hitting anything just by driving 5 miles an hour. So it should be somewhat efficient so that humans don't get frustrated by using this. And then the last point's a little bit more nuanced. We want to build a self-driving car that doesn't require any infrastructure at all. What I mean by infrastructure is we don't want to have to change the lane lines or the road or change the traffic signs and change the traffic lights. Also, it appeals a little bit more to our self-driving system. We want something that works exactly on the roads that humans can drive on now. If it can't do that, you're basically just building a train in a slightly different format. So no infrastructure. Okay, so first we'll think about the classical approach that people use when building a self-driving car. It's kind of seen generally as a robotics problem where you have some environment, in this case you've got the road, and then you've got a whole bunch of sensors that tell you things about this environment. You've got cameras, radars, some cases LiDAR, IMUs, and all these sensors go into some perception layer. This perception layer can analyze what these sensors are doing and can process it in some way. In many cases, you have machine learning models running that will parse the camera data and tell us some things about maybe where are the lane lines, where are the other cars, where are pedestrians. All this information then produces some perception output, which is a list of things that you think might be relevant for driving, which is, like we said, lane lines, where everything is, where the people are, where are the traffic lights. And then this would go into another layer, which is the planning layer. The planning layer is generally some kind of hard-coded optimizer that tries to optimize several different goals, which is like, don't hit things, try to get somewhere, follow some traffic rules. And then the planning layer outputs some trajectory that you expect the car to drive, which is then executed by some kind of control system. Robbe talked earlier about what that control system kind of looks like, and here you can see the steering wheel turning. So we'll look a little bit more into what one of those perception systems would be. Here's some examples of things people use for self-driving cars. So you've got a machine learning model that just looks at the video of the road, and it's labeling all these things that might be relevant, which is like cars, people, traffic lights. It's probably also, you've got systems that label all the lane lines and the sidewalks. It's labeling the bus as a different thing as a car. And then you can compile all this information together with some other sensors, maybe like LiDAR, into this 3D representation of the world, where you've got all these cars, all these lane lines, you know where you are, and you know kind of some version of what the environment looks like. Once you have this perception output, let's go back one. If I can. Oh, yeah, there we go. So we have just a classical planning layer. You'd have some objectives that you try to stay, so like stay in your lane, don't hit other things, don't hit cars, stop at traffic lights. And let's give an example here for this scene. How do we do that? Well, it's pretty easy, right? You just drive straight, stay away from the other cars, don't try to go over the lane lines. So this seems pretty easy to write an optimizer that can satisfy those requirements. Then we go to the next scenario. Here, this is a little bit more complicated. Oh, no, let's go back. Where we have an intersection, and let's say we want to turn left at this next intersection. Now, you're trying not to hit things, you're trying to stay in lanes, and you're trying to stop at traffic lights. Now, this all doesn't seem like much of a problem. The light's green, so you can drive through the intersection. That lane's open, so you can just go over there, drive there, and then you turn left at the next intersection. That doesn't seem that hard. We can write some code that does that. But if we zoom out a little bit in this scene, I'm really confused by which button does which on my clicker. The top one goes forward. Yeah. Oh, there we go. All right, so we zoom out a little bit in this scene, and there's a pedestrian standing on the crosswalk. Now, this person looks like he's paying attention, and it doesn't look like he's going to cross if there was a car driving, but we still kind of want to keep a safe distance. You know, our optimizer has a target, which is don't hit people, so we try to keep some distance from all the pedestrians that we're trying to avoid. But what does that actually mean? You want to drive in this left lane, you want to keep some distance from this person, but you also want to stay in the lane. So what's the compromise? Like, are you going to drive in the middle of this lane, or are you going to drive a little offset? There starts to be a lot of these competing costs in this optimizer, and it starts to be very confusing how you tune this to get a desirable trajectory. Personally, I would just drive in the left lane and stay a little bit away from this person, and that'd be fine. But it's hard to actually implement these compromises correctly. And then if we change the scene a little bit, and imagine it's a child that just dropped his ball. For me, this would completely change things. I would not go in that lane, and I'd keep way more distance. But this introduces a new problem, which is that our perception layer doesn't output whether this is a child or a normal pedestrian or a child that's holding a ball or just dropped a ball. So now it's kind of unclear how we can write policy that deals with pedestrians correctly, because pedestrians can encompass all these different things. And the more of these kind of more complicated scenes we look at, the more and more we run into these edge cases that we really have no idea how to deal with. So that's the classical approach. It honestly seems like the back button works and all the other ones don't. So the flaws with this classical approach are that you require machine learning models that do perception based on some camera stream or some LiDAR stream, and generally these are hand-labeled. That's very resource-intensive and not very practical. The planners are some hard-coded optimizer logic, which generally has to have code for a whole variety of different scenes and environments, and this list grows and grows as your system becomes more and more capable, and has some unbounded complexity. And then there's the other problem, which is that the planners need to take in information from the perception model, and any list of things that we can come up with that we think will be good enough for the planner tends to be incomplete. We always run into some new edge cases and actually need to add new information, and this list of things the perception model needs to output also grows endlessly. So the result is you have this stack which is massively complicated, impossible to maintain. And this is why you see many self-driving car companies that use this approach make a lot of progress for a few years, and then they start to stagnate because they're working on this huge stack that is so difficult to alter because of how complex and intricate it is. So what can we do? A friend of mine used to say, every time you get in a car, you show it how to drive. The problem is that it forgets. And this brings up a very powerful idea. Humans don't drive by memorizing some very long list of rules of how to act in every environment. Instead, they learn some basic traffic laws maybe, but in general, they observe how other people drive, they observe how their teachers drive, and from that, they learn how to operate a car. So we can very easily collect data of humans driving. So how can we leverage that in the same way that a human would to teach the system about how driving on a road works? So we call this an end-to-end approach. We can just build machine learning models that take in some raw sensor data, like video or other sensors, and can immediately just say, drive like that. So it's kind of like having video and asking a human, based on this video, where would you drive? So we can very easily collect this data set, and then we can show the model where the human drove and have it predict that. And then you have this system that will tell you where it thinks humans would have driven. And it's actually a very powerful idea because when you have a data set of thousands of users, then the model will predict where it thinks thousands of users would all predict on driving together. So it's kind of some consensus approach, which can be much more robust than just asking a single person where they would drive. And what's really powerful about end-to-end is that all you need to make it handle more complex scenarios is to make the models bigger, give it more data. And it will just become better and understand more. It doesn't require more code, it doesn't require hand-tuning some things, and it doesn't require adding extra logic for every new scenario we support. All we need is bigger models and more data. So given that, we can redraw the diagram and look at the new approach. So we've deleted the perception layer. All we have is raw sensor data. It goes into some big planning machine learning model that outputs where it wants to drive, and then that gets sent to some controls interface and operates the vehicle. It's now much simpler and should be far more scalable to actually dealing with the huge variety of complex situations that appear on the road. So to start, we need data, and we need a lot of it so that the machine can learn from it. openpilot collects data from all over the world in 1-minute chunks. We collect currently over 100,000 minutes a day. Collectively, it's over 50 million miles of data collected, and that equates to a few full lifetimes of driving. Humans can learn how to drive in a few lifetimes, so it doesn't seem unreasonable to expect that under some conditions, a machine learning model can too. On the right, you can see just a couple of weeks of data collection from the United States. You see we have a pretty widespread data collection across the entire country. I think there's some AI in this clicker. Oh, I see. All right, let's go. Oof. Maybe I should just stop for a while and let it catch up. Okay, that's the one I wanted. That's the one I wanted. Great. So just to give some examples of how really diverse this data set is, I just made this quick tool where you can click on the map and it'll show you some video that's the closest. I picked some places I thought would look cool. So we've got the Golden Gate Bridge, Utah, Joshua Tree National Park, San Francisco Bay Bridge, New York City, the Colorado Mountains. And so when it's exposed to all these scenes, our model can learn about how driving works in all of these different environments. This is some international data. We've got Thailand, some rural roads in Scotland, Nigeria, Belgium, Singapore, Taiwan. So you can see driving is really different in all these scenarios, and it's very important that we have this massive amount of diversity in the data set. So the machine can start to understand what's different between driving on some farm road in Scotland where you drive on the left and driving on some cobblestone street in Belgium. So we've got the data, and now we want to start thinking about how we train this model. We want to clearly define what the output of the model will be. We talked previously about how the model is going to output some path of where to drive. This path is going to be in meters. It's going to say, over the next 50 meters, turn a few meters left, or turn a few meters right, and after that, straighten out. Getting this information about where a human drove in this representation for all the video we have is actually not trivial. We need a localizer to do this. So a localizer answers the question, where am I right now? Where am I looking? Where am I going? And where did I go? Once we can answer those questions, we can then generate the ground truth for our machine learning models. On the right here, you can just see some satellite view overlaid with some images we use to represent cameras of video we've taken. So these are just 4 parallel lanes somewhere in the Bay Area. So to build a localizer, we start with GPS, or if you want to call it all those constellations, including the Chinese and the Europeans, who call it GNSS. GPS doesn't exactly tell you where you are. It has these satellites orbiting around the world, and it tells you kind of how far away every satellite is from you. If you know that, and you know where the satellites are, you can then kind of estimate where you are. And this is what most GPS receivers do. The thing is, they use pretty simple algorithms with not that much compute to do that. When satellites tell you how far away they are, there's a lot of error in this measurement. It can be influenced by the humidity of the atmosphere, by the relativity errors in the satellite's atomic clocks. It can be influenced by things in the just ionization in the atmosphere. And so we can get quite a bit more accurate results if we just take these raw measurements and do our own processing. So we built an open source project called Leica, which is capable of doing all this processing. And we can get much more accurate results. One of the cool things that we can do by having our own library is we also get the Doppler shifts to every satellite. Doppler shifts, you can measure the difference in frequency that you're seeing from a satellite, and it will tell you the relative speed of your receiver to the satellite. And this actually gives you such accurate speed readings that the GPS gives you far better speed readings than the speedometer of your car. So this is very useful for the kind of localization we're trying to do. One of the examples of things like I can do is if there's activity on the surface of the sun, this ionizes the Earth's atmosphere and can cause a few meters of localization error in any normal GPS receiver. We can download some reports from NASA that tell us about this solar activity and compensate accordingly, making our localizer even more accurate. So we've got raw GPS measurements that will be processed a little bit, massaged a little bit to get low errors, and we can use that to get a location and to get speed. But it doesn't tell you where you're looking. It just tells you the position, not the orientation. Another problem is that GPS is great, but not always. When you're under trees, in a tunnel, in a parking garage, GPS either works worse or not at all. So to be able to have ground truth in all driving scenes, we want to have a system that always works. So it needs to work when GPS is spotty, and sometimes even when GPS is not there at all for intermittent periods of time. So we want to do sensor fusion with redundant sensors. We made an open source project to do this. It's called RedNose, and it's a pretty large Kalman filter, which is a type of optimization filter that takes in all these different measurements, including GPS, and will output its best estimate of where you are and the orientation of your vehicle. So we use IMU data here, speedometer data, but the most important is actually camera data. So we can look at the video of the dash cam, and we can see how things are moving in the scene, and we can track those with things called orb features. And we can use those pieces of information in our sensor fusion system, and it'll give us accurate information about not only where we're going, but also what orientation we have, how the car is turning. If you have very accurate localization of both your orientation and position across many frames, you can start to stitch things together. So here you can see kind of a cool example of how well our localizer works. We take all these points that it's seeing while driving along this road, and you project them all down, and you see this beautiful top-down view of you passing an exit, but staying in your lane. And its localizer is very accurate, and that's great, but the most important thing about it is that it is robust. Oh, no. It needs to work in all the situations we want to expect our car to drive, which is all of them. So it needs to work when the scene is dark, when there's not many things going on, not many features to tell you about where you're going. In this case, we still have a sign, but once you pass the sign, really, you've just got a couple lines on the road, and this can really confuse the camera odometry system. This is actually an example of a bug we had only a few releases ago, where if the lines were continuous, then it would match features to itself and get super confused and start cutting the turn. But that's now been fixed, and so far the system has become incredibly robust. So now we've got ground truth. We know where the human drove for all this video we have. So all we have to do is we train a neural network that takes in a couple of frames from the video, we just use 2, and predicts a path of where a human would have driven in that situation. Here you can see the system training. It's a little bit noisy at the end, but it's already getting right that you have to go mostly straight. The model we actually use is an EfficientNet B2. Takes in the images here, which are that size, and then goes to some head and outputs this path. No. Okay, so we've trained our machine learning model, and now it's time to find out whether it works. So generally in machine learning, you have some training set of data that you've worked on, and then you've got some other data that you keep separate to test on, just to make sure that it's not overfitting. So we've got all these examples from our validation set, and we look at them, and it looks pretty cool. We've got some lane lines in there as well. That was easy to do, so we just added those. And you can see it turns there, You can see it even gets the 3D parts pretty nicely. Here it's predicting it's going uphill and going over a crest of a hill over there. But in general, this all looks pretty good. This looks like what I would have labeled if I were to say where to drive. So we're ready to try it out on a car. So we take this model, we implement it, we make it so that its output is executed by controls, and it doesn't work at all. We drive on it, it completely drifts out of the lane almost immediately. So there's this quote about software engineering that I think is really applicable. We do these things not because they're easy, but because we thought they would be easy. And so this applies here too. But this brings us to, what can we do now? We thought it would work. It looked like it worked on the day that we tried it, but in the real world, it fails completely. We could keep trying things and then try it on a car, but this is very time-consuming and gives us a very, very slow iteration speed. So we want to have some way to test it offline from our desks before we go out and try it on a real car again. To do this, we would need a simulator so that in the simulator, the model can predict where it wants to drive. We can have some simulated control system execute on that trajectory, and we can then see how it behaves. Hopefully, if the model is driving on its own path, and this is simulated in full rollout, we should start to see similar results we saw in the real world. So what kind of simulator can we use? You can use things like GTA 5 or Carla or Truck Simulator. I mean, there's roads there, and they look kind of all right. But the problem you get with those kind of simulators is very similar to what we talked about at the beginning. The amount of environments and scenarios one of those simulators can simulate is always going to be limited to the amount of scenarios you engineered into it. It's never going to capture the full diversity of human driving. If you want a self-driving system that can work in Nigeria or in the country roads of Scotland, you also need a simulator that can represent that. Otherwise, if it fails there, we'd never know about it. So we want to build a simulator that is based off real data and can simulate the entire spectrum of our data set. So we use a little bit of a trick, which is you just take video and you can just warp it a little bit left and right, make it appear as though you're driving in a different location than you actually did. You can see as it's moving around in the simulator that things are warping a little bit. And obviously, if you go very far from where the video was taken, there'll be nothing left. But this simple trick seems to be good enough to do some simple simulations. And those simulations tend to be good enough. So let's try the system we just trained in one of these simulators and see what happens. So on top, we just have this segment of driving down a road behind a truck, and we have the model that predicts your path, and we try to execute that plan. You can see it kind of already starts to drift out a little bit, but in reality, it started to drift out much, much, much quicker than that. And then we realized this is because in the real world, there's a lot of disturbances that act upon the car. There's little bumps in the road, the tires aren't perfectly aligned, and there's things like wind gusts, and all these things push the car around a little bit in a way that the model didn't want it to. So we can simulate those disturbances too, and this is what you see in the bottom frame, and you see it drifts out in a matter of a few seconds. Now, this is exactly what we saw in the real world. So trying to understand what is actually happening and why just having the model predict what it thinks a human would have done in this situation isn't enough is kind of difficult. It's something we argue a lot, and it's worth the whole discussion in itself. But I'll try to give as clear of an explanation as I can, which is, imagine the car is on the right of this lane, so it's not perfectly centered. What would a human do in that situation? You could imagine that the human would probably correct and go back to the center of the lane. And this is probably true, but when would the human correct? You can see here it tries to correct a little bit at the end, but in the beginning it still goes straight. So if that's what's happening, and you have this car at time t0, which predicts to go straight and then recover, then tells the controls to do this. It goes straight, and it's still in the same position in the lane, and you ask it again, what would a human do in this case? But nothing has changed. So it answers the question in exactly the same way again. It says, go straight and eventually recover. And if we run this in a loop, the system never recovers. It keeps predicting, just go straight for now, and at some point recover, because that's what a human would have done. But with nothing keeping track upon the fact that it's never actually executing recoveries that it had in mind, it just continues to accumulate error, and if there's any amount of disturbance, like wind pushing this to the right, it'll just drift out of the lane. And so this is what we see in the real world, and it's also what we see in the simulator now. Oh, almost. So how do we solve this? Like we mentioned, really the problem is that the model is never learning to recover from mistakes. It gets pushed out of where it wants to be a little bit, and it doesn't recover. So one of the ways we can solve this is by training directly in a simulator, in the same simulator we've been talking about. Push the model left and right a little bit, introduce these disturbances, and tell the model, recover right now. And that's what you can see in these GIFs right here. So we've got the black path is where the human actually drove in this situation. And we push the car around a little bit, and we tell it, that's where a human was driving. Get back there immediately. And that's what you see the white path is, which the model is predicting. So you're seeing we're pushing the car around, and the model is seeing that, and it's shifting this path to where the human was driving. You can see the same in this situation. There's actually a lot of details involved in getting training in a simulator like this to work, and that's the culmination of a few years of work at Comma. We've got some more technical write-ups about the details of that. But in essence, this is what it is. So we've got this new solution, and we think it might work. But how do we know if it works? We already talked about the importance of testing before, because we don't want to test in cars. Testing in cars is super time-consuming. We actually have this rule at research at Comma that testing in cars is not allowed. If you can't reproduce it on your desk, it's probably not worth looking into. So we want tests that work completely offline and give us indications about how the model will perform in the real world. Everything that we don't track or test explicitly will probably regress or break at some point. We've experienced this through a lot of trial and error, and we are now very aware of the fact that every situation we want to work correctly needs to be appropriately tested. So we put the model through a whole series of tests. Give it a little eye exam. So I'll just give some quick examples of the kind of tests we can run that just give some indication about what's going on. The first thing is we can just ask the model how fast it's driving. We know how fast the car was driving. If the model doesn't know exactly its own speed, that's generally an indication of some kind of failure. We can also check the accuracy of how closely it's matching the path that the human was driving, how closely it's matching the predictions of some lane lines. If anything here looks weird or there's a lot of outliers, that's usually an indication of a failure that we would want to look into. We also have this simulator, so we can actually just let the system drive in simulation and do all kinds of tests of how it behaves. We can introduce lag in the steering rack and see how it reacts to that. We can introduce disturbances, such as wind. We can make the steering wheel offset pretty large so that it's just pulling left all the time. And we can see how it reacts to all these situations and kind of get an idea of how it would fail and how many disturbances are necessary for it to fail. So we drive the model in simulation on thousands and thousands of minutes of driving, and we see kind of what the overall results are. We check how often it deviates from the human path. We check, does it cut turns too much? Does it overshoot turns too much? Is it just kind of too aggressive all the time? And all these things we can find out by just doing metrics on thousands and thousands of minutes of simulated driving. So one of the other tests we do is we just check overall, when did the model predict to do something that is completely different from what the human actually did in this situation? So did the model ever predict something that looks like a swerve compared to what the human did? And here are some of those results of those tests. And as you can see, they're basically all lane changes. The human made a lane change, which is the white path, and the model predicted to stay in your lane. This isn't a bad thing, but it brings up this interesting point, which is that we expected the model to always output the right answer, which is what a human would have done, but that's not, sometimes there's more than one correct answer. Whether or not you make a lane change, both making the lane change or not making the lane change is generally acceptable, and it's definitely both safe. So we need to give the model some context so that it can understand how to deal with this. We need to make sure the model understands where it wants to go so that it can make a lane change if it's necessary, or turn right or left if it's necessary. Here's some examples of this happening. So you've got a human making a lane change past this car, and here you've got an intersection where there's a turn left lane and there's a go straight lane. And here, in this case, the person kept left to make the left turn, but might have just as well just gone straight. So to deal with this problem, we just have like a small set of hand-labeled classes, which is you can go straight, you can make a lane change, you can keep left, keep right, you can turn left, turn right, and we label those. We give the model that as context, so it makes sure that when the model's making a lane change, it's doing that when it's told to make a lane change. And then that brings us to there's really only one correct path given this information. So we fixed this problem by labeling that. You'll hear later in the talks a little bit more about how exactly we label that. And so this kind of works. And it more than kind of works. This is an end-to-end system that we've shipped, and since a few months has been running on openpilot. You can go into the settings and disable lane lines, and it will just work completely end-to-end in the way that we've described. This is, as far as I know, the only kind of end-to-end self-driving system that works at all, and it's definitely the only one that you can experience. So we'll just go through some quick examples of kind of the power of this end-to-end approach and things that it allows us to do. I think the button's sticky. I think that's what's going on. Oh, did I do that? Ooh. Wrong talk. But the clicker definitely has a mind of its own. Anyway, so quickly I'll give some examples of lane changes, which are one of the things that's possible with this end-to-end thing. We've told the model about lane changes during training, and so we can also tell it to do a lane change like a human would. Oh. I'll take a drink break while we're taking a break anyway.
The lane changes are too good.
Yeah. It's trying to keep it a secret. Trust me, the lane changes are going to be worth it when they're finally revealed. Yeah, we can talk about it in the Q&A as well, but All right, we'll take a short break. Everyone can think about the questions they're going to ask later. I guess this is kind of a good place to take a break. That was how we build it, and then we'll have the grand reveal of the results. Oh, yeah, I can take some questions right now, yeah. We'll do a couple questions until we've got the laneless results.
Model training takes a long time.
Yeah, somebody's trying to get the GPUs up and running.
Any questions? Harold, we have a question.
Sure. So I saw on the slide you had an efficient net and then a fully connected layer, and that corresponded to vision and planning. Could you go a little bit more into, like, are they separated or are they all trained at once? Is there any separate training of those two model components?
No, it's just the architectural separation. So you've got the convnet, which is, so the B2 is fully conv, and then you've got some dense layers on the bottom. But it's all trained together.
How many parameters on the bottom versus the top?
I don't know.
Or roughly?
Like
Just
a few million in the bottom. And I don't know how much an efficient net is. That's several million too. Oh, we're back. Back. All right, so this approach works. And we've got end-to-end machine learning working for self-driving. Here's the first example of this, is we've got end-to-end lane changes. So this system was never explicitly taught about lane changes, lane lines. It was never told that a lane change is crossing a lane line. We just teach it. These are lane changes that humans did. Try to do them like that. And in fact, these lane changes will work perfectly fine if there were no lane lines. If this was snowy or it was just a badly maintained road, lane changes would work just as well as they would for humans. Next example is just driving lanelessly in a variety of situations. So on the left, we've got a road that's completely snowed in. If there were lane lines, we can't see them. And a classical system would struggle here. There's not really much to go off. You could say that maybe the road ends there and you try to stay on the road, but a laneless system can clearly see this is where a human would have driven, because that's where the tire grooves are, and it can smoothly just do exactly what a human did. This is the power of the end-to-end machine learning. On the right here, you can see there's a turn to the right, and there's quite a bit of oncoming traffic that looks quite intimidating, and the laneless model does what a human did, which is cut the turn aggressively to avoid this oncoming traffic. Again, these are all just features that it can learn just by observing humans. We didn't ever tell it to avoid traffic. We didn't ever tell it to follow the grooves in snow. It's just observing humans and doing what a human would have done. So what about longitudinal? This entire talk has been talking about lateral control of the vehicle, which is just controlling the steering wheel. There's more than that to controlling a vehicle. You also need to control the gas and the brake. We've been working on this for quite a long time, and only the last few months have we really been able to ship laneless models that work well. And so that's been the main focus. But all of the lessons we've learned and all the strategies we apply should work perfectly fine for controlling longitudinal as well. So recently, we just started working on that, and I'll give some quick examples of what some end-to-end longitudinal features would be. So we've got model-based FCWs that was shipped a few releases ago. So we can just ask the model a question. You know how humans drive? Tell me if you think a human would brake in the next few seconds. And so that's what you see here. When the FCW pops up, the model is saying, whoa, whoa, I think a human would have braked hard here. And so this is shipped in openpilot. If you're engaged and you're in a situation like this, you'll get a warning from the model saying, you might want to brake pretty hard here. Here's another example. So again, this model, we're never told it about cars explicitly or anything like that. We're just asking it, tell us when you think the model would brake, when a human would brake hard. Another thing we can do is we can ask the model, tell us where you think a human would stop. Again, that's basically the same ground truth as the paths. We just check where the velocity becomes 0 and a human driver becomes stationary for a while. So here you can see the model is predicting a stop line, which is where the human would stop, right by the red traffic light. And here you can see it by a stop sign. So this is completely end-to-end, seeing the traffic lights because it knows that's where humans generally stop. And the same with the stop sign. It's not explicitly looking at the stop sign. It just looks at the scene and knows a human would probably stop here. So what's next for comma research? Stop lines is one of the features that we haven't rolled out yet. That's the only thing in the talk that's kind of still experimental. We might want to ship that soon if we can get it to work pretty well. In general, we're really just looking at making this models bigger and smarter and understand more and more complex environments. So this is going to keep improving end-to-end lateral control. And then we also want to move more and more to end-to-end longitudinal control. Currently, openpilot still uses lead car detectors and just normal ACC commands to control the longitudinal control, and we want to start moving that to exactly the same full end-to-end architecture we're using for lateral. Questions?
And I don't think it's currently used in operation when openpilot is engaged, correct?
It is used for some parameter estimation of the vehicle controls, yeah.
So do you think that with your longitudinal control, you'll be placing a larger reliance on GPS in the future?
Not really. I'm not sure why that would be necessary. The model shouldn't require GPS for anything at runtime. Are you saying because you want to make a map of the places to stop or something?
Well, I don't want to be restricted to only where we have GPS mapped out roads. You know, one of the benefits of openpilot is you can drive on any road.
Right. So we do rely on GPS for ground truthing, but like I mentioned, we do support spotty GPS, and so the system should work completely without GPS. And so currently our data set should capture all the situations where GPS doesn't work. Just because if you had GPS 40 seconds ago, then that's enough to carry through to the entire chunk of data we analyze. So that's not a requirement.
I'm going to start with questions down the row here.
I want to ask how you look at training data and decide this is good driving. And by that I mean, what happens if in your training set, you look at night and the driving in the area of this bar at night after 3 a.m. is kind of weaving all over the place. Or a human tends to roll this stop sign, or somebody's just weaving on the highway, or quite frankly, you drive like I do when I'm not driving on openpilot. How do you get rid of all my driving data and train on the chill people?
So we kind of think about it as, you're not just looking at mimicking one person, right? We're looking at this whole data set. And we make the assumption that when humans make mistakes, they tend to do it in noisy, uncorrelated ways. And so if you have a system that behaves like it would the average or the median of thousands of different drivers would, that's generally a very good approach. If you ask 50 people to look at a video and exactly what they would do, the consensus of that should be very stable and I think good driving. If that ends up that the average driver is perhaps too aggressive, what we want openpilot to be, we can start doing some basic things to differentiate some aggressiveness and tune it down a little bit so it's a little bit more conservative.
I can see how that would work for most things, but just how would you control for saying rolling a stop sign, which quite frankly the average is going to show that a fair bit?
So right now we're just really not at the stage where it makes sense to think about things that detailed, I think. Okay. We first want to get to what an average human would do, and if for some reason we want the system to behave differently, we can think about that then, and there's some tricks to do some filtering of certain types of human behaviors, but I think average human behavior would be a massive victory for the entire self-driving space.
Hey, thanks again. Question here, how do you train out unwanted behavior? One thing that I've seen with this end-to-end approach is sometimes car tries to follow what driver in front of you does. It kind of ignores lane lines. It just, if that car goes right or left, it just follows it.
Yeah, so that's kind of similar to Jason's question. And like you said, generally mistakes humans make are very noisy and uncorrelated. And so if you take the average of lifetimes of thousands of different humans, the behavior should be very consistent and should be pretty desirable.
It's not really about mistakes, but if you look at it when human drives behind somebody, we pass it.
Yeah, I mean, like I just said, I think average human driving would be a huge victory for the self-driving space. No system in the world is anywhere close to that. So that would still be much better than anything in the world.
Part of the following problem is big model, I think. Why it follows cars
Yeah.
Yep. So in regards to end-to-end lateral control, if you, let's say, had a camera on both sides of your vehicle, so you had a wider field of view and you were training on that, would the AI start to learn to move over to the left side of the lane if there's a semi on the right side like a human would, assuming there's no car on the left side? Or would that kind of get washed out in the training?
No, I'm pretty sure that would. Consistently, I think humans try to keep distance from cars next to them in highways, and so I'm pretty confident that model should learn behavior like that. You can actually see, in some cases, if there's a semi on the left side of the lane, the end-to-end planning will deviate slightly.
Awesome, thank you.
Yeah, so first of all, thanks again for the presentation. Super informative and amazing technology. Kind of like inverse to the two bias questions that came before, have you found either any places where it's relevant or where it's useful to have explainability backwards? Like if the model does something that's particularly weird one time, like it swerves out a particular type of lane or it takes certain types of exits, are you able to go back and tell what influenced the model to actually behave this way?
Yeah, so that's, I think, a very interesting question and something that I, when I started working on these things, was much more worried about than I am now. I think generally these models are seen as kind of these black box things that can behave in unpredictable or weird ways, and there's no way of explaining it. But so far, every case that we've seen of it behaving something that initially looked weird, we've been very easily able to reproduce and explain. To give one quick example of an issue we used to have is everything was fine, the roads looked fine, and it would sometimes randomly start predicting lane lines in the center of the road. And this was a bit of a mystery for a while, and then you start to look at the ground truth that has, lane lines in the middle of the road, and you find there's some person that had like a fluffy thing at the front of his car, which was kind of colored orange, which was detected as a lane line. So this kind of made it into the data set, and then the model sometimes behaved that way. But so far, every single weird behavior we've seen, we've been able to explain. Same, yeah.
What's your intuition on continuously making use of larger models and keeping just sort of taking the traditional ML and just scaling it forward? Because in the case of real world, you have distributional shifts. In that case, examples that occur very rarely it would be unlikely for the model to make any sort of generalization on that sort of data. So how do you sort of augment the data, so make use of examples that occur very rarely?
I'd say so far we haven't really seen much of the issues with that yet. If there have been issues where the model struggles in rare cases of that, it seems to be that generally the model is just limited by the quality of our ground truth. If there's 0.1% of data that looks completely broken because of some bug, this will usually manifest itself in the model not being that smart in the end and not being able to see rare cases. But as we've improved the ground truth quality, even with the same size of model, we've seen the model become smarter and smarter and can learn more and more rare events. Maybe someday some kind of sampling would be necessary, but I think so far we're making very good progress without that.
Yes, so my question is specifically in regards to driver alertness. So one of the things that I've noticed that as I'm driving, there's some scenarios that I run into that I'm particularly on high alert. So I was wondering if there was any consideration with the comma team into developing a predictive model. Maybe you have different levels of alertness that could either be communicated to the driver or that you recognize as like high risk scenarios.
Yeah, so currently we actually have the model tell us how likely it thinks that openpilot would be engaged right now and how likely it is that a user would take over from openpilot in the next few seconds, either with the brake pedal or the gas pedal or with the steering wheel. So the model already completely outputs all this information. We've thought about communicating this somehow, but just really haven't gotten around to it. But we do have tons of introspection in how much confidence the model has in that the situation is weird or that a human would start to feel uncomfortable.
Have you, and one follow-up question, have you thought about like creating a project for, kind of like a take-home project type of thing for where you could, let's say, you could export a CSV file and ask a few questions, and ask someone to like predict to develop a model like based on 10 data points or 20 data points that like, oh, if you think this would be more likely to be a high impact scenario. So like say for example you could go to an insurance company, look here are the top 10 reasons for car incidents, and then you could have like specific questions based on that. So just
not entirely sure if I understand the question.
Well, just in the same sense that you have like, if you look on the website, you used to have the $500 bounty.
Mm-hmm.
So I was asking, like, was there any consideration, or would you consider like potentially having something where you took just some general instances and then you gave that as a project to the community that we could potentially work on?
I mean, if you're talking about developing on the model, that's kind of infeasible for anyone that doesn't have access to all the data and all the infrastructure that we use. So that's not something that's easy to distribute development on.
We got a question upstairs?
Hi. A question regarding the evolution of this approach. I mean, my impression that it can bring you so far, like what you do in building like a very nice L2 lane keep assist.
Mm-hmm.
But at some point you probably want to go to, like end-to-end trained, unprotected left turns and go into the L4. And do you think you can push this approach where like you may like use the imaging data and the trajectory of the actual driver for training, or you'll have to do some like paradigm shift where you go to mu-zero approach and like where you have to rewrite the whole training pipeline?
So I think in general, this end-to-end training scales much further than any other approach. I mean, you mentioned things like mu-zero. It might be possible that a distribution shift of that level is necessary, that we can't use the simulator the way we do now and need something a little bit more advanced with some kind of learned simulator or other more advanced machine learning techniques.
But
Something
like
that.
But it's still like ideation. There's nothing like roadmap where you think, okay, I probably go do it this way like in 5 years.
We've got some internal discussions about that, but nothing concrete. Really.
Okay, cool, thanks.
Great, thank you.
All right, I screwed up my last question. Luckily, somebody else asked the right one, so this time I took notes. So 2 quick questions and 1 thought. First question, so with your human example on the crossing, do you consider the bounding box movement? If you makes sense if not, because even Tesla, I don't think it didn't do that.
Wait, I'm just looking for where you are, actually.
Oh, I'm here. I'm
here.
Okay.
Yeah, so
sorry, I'm like the voice.
So what did you mean by the bounding box movement?
Oh, yeah, so your example of the human on the border crossing.
On the lane line crossing.
On the lane line crossing, yeah. Would you consider the bounding box and the movement of it, like the acceleration or
what do you mean
velocity?
by the bounding box?
For predicting, well, you make the bounding box of the human. You see that there's a human there, right? So you make a rectangle around him.
Oh, okay, yeah.
Like now the movement over time, right? So would you consider that, for example, as to better predict, like with stopping or going, right, down the line, something like that?
No, so we don't want to do anything like that. Yeah. So we really want a fully end-to-end approach. The system should completely learn that a human would slow down or avoid a human, and that behavior will come into the end-to-end system.
Right.
We never want to explicitly track these things.
Okay. Oh, okay. So that goes with my second. That was the thought, like of thinking differently. Instead of like finding out if it's like a kid or adult, you could like do maybe pose estimation, right? Like you could train a model like using epic mega games, meta-human stuff, right?
Right. So that's the kind of stuff we want to avoid. We really want a system that is very simple architecture. You take in training data, behave like a human, so that we don't have to write any of these code or scenarios to deal with any complexity.
Right. I figured you could kind of just make a model that extrapolates like the movement, right, the skeleton, and
yeah, sure. But the problem is there's an endless list of these things, right? And it never ends. So.
Yeah. Okay. And then last question. It's more for me. Like I work on a VR operating system kind of thing, and the SLAM stuff is really not great. The open source SLAM stuff in some ways. Your system, the sensor fusion SLAM tracking system, would that work also for like lower velocity and like VR kind of systems, or is it more? For
yes, it should completely work. So we haven't really been able to spend much time into documenting or putting effort into really making this library accessible, but it is open source. You can see how we use it, and I think it has a lot of compelling features compared to other solutions.
Great. I'm going to move to the back of the room. We'll come back to the front. I feel like we had a lot of questions down here.
Hi. So you mentioned kind of the machine learning mantra of more data, bigger models, and you've been working with these models for a while. Do you have any sort of kind of estimation of how big these models are going to have to get in order to reach that goal of driving as well as a human? Or are we not even at the point of estimating that?
I think it's difficult to estimate that, but internally we talk a lot about, what kind of animal would be able to drive a car? Would a cockroach be able to drive a car? Probably not. I think that's kind of the scale that some of the large models people use these days are at, like insect level. I think pretty confident that like a bird or a small mammal would probably be able to drive a car. So if you want to have some very rough estimation, I think that makes sense to think about how many neurons do these animals have that seem to show complex enough behavior.
Great. We also should have plenty of time for everyone's questions, so just be patient.
Hi. So you described that the end-to-end approach is essentially predicting the trajectory that the human would take in the picture, right?
Mm-hmm.
Isn't that, strictly speaking, not fully end-to-end? Because fully end-to-end to me would mean that you record all of the inputs that the human took in the car and then predict those raw inputs from each frame a number of steps into the future.
Yes, so it's not fully end-to-end. I think I glossed over that a little bit too quickly, but we still make the separation between planning and controls. What you're saying is you could skip that as well, just take in video, output the car commands. The problem with that is that it makes it very difficult to abstract different types of cars. So we support all these different types of cars. So we already need some kind of common interface there. That's one reason. The other reason is some level of introspection is useful. If we're just seeing the steering inputs and the gas and brake inputs, it becomes harder to see what the model is thinking. And we really don't think that much is lost in this abstraction layer between planning and controls. It seems like it's reasonable to think that some trajectory is planned, and then you should just always be able to execute that with controls. I don't think there's that much nuance.
Okay. We're back here. All right. Similar to a couple questions, but as far as the level 5, and somebody mentioned the model, but I was curious more on the hardware. Do you think the camera and the sensors that you have now is sufficient, or is it going to require like mimicking more like a human, like binocular vision, or only cameras? Or is there any kind of idea of hardware-wise what the future is going to hold?
Yeah, I think there's some limitations to the current system, and there's some reliability concerns, but in general, this isn't the limiting factor. Given the video that the system is getting, it can do much better, and this is true for all self-driving systems. They're limited by the compute and by the software, not by the sensors.
Hi. I'm curious if y'all been thinking about this, or if it's even appropriate, using data visualization or dimensionality reduction techniques to try to peek into the black box of the model, so to speak, a little bit, to see what features of the world your model is starting to learn and pick out for its processing.
Yeah, we've done various experiments with this. At some point, tried to train GANs that try to kind of reconstruct some representation, and we can see what things it thinks are important and stuff like that. But like I mentioned in one of the earlier questions, we've never really had issues trying to understand what the model is doing. With just a little bit of effort, we've always very easily understood why the model is making a certain mistake, and extra introspection wouldn't really help us that much. If it was necessary, we could build more tools, but it's not a huge part of the way we work right now.
Hello, so a quick question. As you're ingesting data into the knowledge base, are you capturing video for all active sessions, or is it simply a sampling of the population? And then secondly, how does my active session benefit from the contents of the knowledge base?
I'm not entirely sure what you're asking. So you're just saying, is all data being used to train the model? No, so we do some kind of diverse sample with some basic logic to enforce some level of diversity, and then we train on that. If we see benefits from training on larger data sets, then we can move to larger data sets, but currently that doesn't seem to be the limiting factor.
How do you plan to gather the context of a curvature?
What do you mean by the context of a curvature?
Whether that curvature is going to, say, do a full 90 degrees, or I don't see how you can understand a curvature unless you have a top-down view like a map.
I mean, you're talking about the ground truth, or how does the model see this?
I could think that you could ground truth end-to-end longitudinal by using OpenStreetMaps and then using a test track with
No, so this is all just ground truth by using a localizer on human data. We know exactly how a human moved through the world from the localizer. And so that's the ground truth, and that's what we make the model predict.
Does the localizer see the context of the curvature, like the future of it?
Yes, the localizer knows we use the whole future of the drive. So we do know that, yeah.
Hey, has this been tested on pedestrian crossings? Like, does it stop if someone's crossing the street?
So we, as I mentioned, longitudinal currently in openpilot isn't that end-to-end yet. We've done some basic experimentation with end-to-end longitudinal, and we haven't gotten that far with it yet. It does react to some things, and it doesn't react to other things. We're still working on that. We only just started really working on end-to-end longitudinal. But I imagine it would react pretty appropriately once we start working on it actively.
So my question is more related to the switching of the lanes. So does the model take into account the state of the blind spot monitoring? Is that input data taken into account in the model?
That's not taken account into the model. I think openpilot on some cars, it will just prevent you telling the model to lane change if there is a car in the blind spot. Yeah.
Did I have some questions in the middle? All right, I'm headed back front.
This is a question about the simulator. So you train off policy, and this induces distributional shift, and to account for that, you throw in some noise, which you do with your warping.
Mm-hmm.
For richer, more dynamic multi-agent scenes, like going through an intersection, do you think this approach will scale? What will this work? And if not, do you have to have a multi-agent dynamics model, like Wave AI, where they predict the trajectories of other agents?
Yeah, I mean, well, like we were talking about earlier, it's possible that we need a little bit of a paradigm shift away from this type of warp simulator that we're using now. But I think just right now, it's not really a limiting factor. We have quite a bit of ways to go. And then maybe after that, we can see if there's different strategies that can simulate some more dynamics, for example.
Do you guys use some sort of like self-supervised learning setup? Like, I guess Katharpe in his talk, CVPR, he talked about like how Tesla's like building sort of self-label annotation engine on training examples where the model didn't predict, the accuracy of the prediction wasn't that high. Do you guys see that as some sort of useful pruning of data?
Right now, we don't use that, and I don't think we have a need for it right now.
So in this new, like, what would a human do type of training for your models, are you still like hand labeling for like anomalies, right? When you have a dog that runs in the road or maybe an obstruction, does this new model remove the requirement of that? Like, is there still a use case for comma pencil, or is that legacy now?
So comma pencil has a very important use in the localizer. The localizer assumes that everything in the video is an static environment, and by how that moves, it knows how its camera is moving. So that doesn't work if you assume that moving cars and moving pedestrians are part of the environment. So comma pencil is incredibly important there to filter out the things that are moving through the scene, which are not static, and the static background, which can be used for localization. So comma pencil will always stay for that. Comma pencil also, we get lane lines from that, and lead cars, which is currently still used in openpilot, and we can conceive being useful for at least some level of filtering and introspection forever. But the policy will rely less and less on these kind of things as we move forward.
I think you touched on it a little bit, but when your model is making a mistake, I guess I'm just wondering, is generally the confidence high when you're making a mistake? And is there any kind of approaches that you're taking to try to anticipate whether I'm going to make a mistake or I'm more likely to fail?
Yeah, so like I mentioned earlier, the model does predict the likelihood that it thinks a human would disengage or take over, and the likelihood that you are engaged. It's very rare for the model to be confident and still make mistakes. Generally, if that does happen, that was due to some crazy data bug that we've fixed. I can't remember seeing any cases like that recently.
This is a bit of a philosophical question because from what I've gathered, it seems like you guys are trying to build a model that behaves like a human more than just like an object prediction model. What impacts do you think this will have on AGI in the future, say like 5-10 years from now? Do you think it'll help out with that at all? Or do you think it'll make it more possible?
I mean, I think this is just a step towards AGI. I think this is more, more generic machine learning that will scale and sometime might create superhuman AIs.
Hi. So first a comment. I work at Wave AI, and we have end-to-end lateral and longitudinal. But
Okay.
you're right that yours is the only one you can buy and try yourself.
I appreciate that.
I don't know if you could have seen the videos in the CVPR workshop we had.
I think I've only very briefly seen things. I don't think I really looked into it.
The question, you mentioned that most of the stuff you've been doing to improve the model is improving the ground truth. But if it's end-to-end, I'm not sure what ground truth you're improving. Is that just failures of the localizer?
Yes, pretty much. So the localizer failures, they can fail in many different ways, mostly because how much of it relies on video, and you have all these different types of driving scenes. So we didn't talk that much about the localizer, but we started 2 open source projects based on it. So it's clearly a big part of what we do. Probably spent 2 to 3 years really iterating through the localizer, making sure that it's robust. You have other SLAM systems like OrbSLAM, stuff like that, that is very accurate and works most of the time, but they tend to fail in rare cases, which are still not that rare and need to be fixed. So we spend a lot of time working through that.
We've got another question upstairs.
Hey, I'm just curious if the self-driving models that you're using primarily seem to be used on highways, and I think of driving in general to kind of really be split into highway driving and sort of city driving with stop signs and people and stuff like that. And I see those as 2 kind of distinct problems. Do you think that the models that you're building now actually can work safely in city environments, or do you see any challenges looking ahead to level 5 in that regard?
So we currently focus on highway driving just because it's the most useful. We want to make self-driving cars, but we do want to ship cool and useful things along the way. I don't think there's anything in this strategy that's inherently limited to highway driving or any specific scenes. I think it will scale perfectly fine, but it is significantly harder to drive in the city, I think, than on highways.
Hello. I have a bit of an open-ended question. Do you guys see any differences in the average of the way that people drive in Tijuana and LA and San Diego?
I can't say I've ever looked at the differences between cities, but there's certainly a difference between continents.
Hi, I have a question. Since you say you finally let a human kind of teach the agent to learn how to drive, so when is the day plan to let us to teach it when it's not working?
I mean, implicitly that already happens because when a user disengages from the system, that's a signal that the user wasn't happy with the way it works. So there's already this kind of feedback loop. We have very good ground truth for when a user didn't think the model should drive. So we actually have very accurate metrics on how confident people are in what it's doing.
Great. We're back here.
Hey, Harold. In your blog post on lateral planning, you talk about ways that the model will cheat in the simulations. Could you go through some of the ways that y'all detect and mitigate against the model cheating?
So just quickly on that, when we move around in the simulator, the image warps, and this can be detected by the model, which is what the cheating is. So one of the ways we can detect that is by introducing warp without actually having real data. So we can have fake data, introduce warp, and seeing if the model reacts. And so we have tools like that that allow us to measure some level of cheating, and we had some introspection into that.
Great. These are our last 3 right down here.
I wanted to ask how your model training process scales or doesn't scale, and this is my ignorance on machine learning in general. When you iterate on your model, are you throwing away the previous model and starting again from scratch? If I had a new human driver, 16 years old, and they had a collision, they would learn from that and move on. And become a 17-year-old driver instead of a 16-year-old driver. But I'm curious if you have to start that over, and if that has implications for scale and the kind of long tail of weird little problems you have to figure out to reach true self-driving.
Right. So yeah, so that's an interesting question. Currently, we train everything from scratch most of the time. It doesn't cost that much time, so it's not really a reason to try to avoid that. Maybe in the future, the training is so costly that it makes sense to start training incrementally. But I don't foresee that happening soon. We don't seem to be that limited by the size of the models right now. But if we do have to scale the models to get the performance we want, then maybe incremental learning is what we want to do.
More GPUs.
Yeah. I know that eventually you want to get to level 5, and ideally you would be there tomorrow. And then on the other hand, some companies seem like they'll maybe never get there, like Waymo. What's what primarily is influencing the velocity of your model improvements right now? Like what work inputs do you find are like the biggest barrier to like getting to that next major milestone for you right now?
I think if I were to list one limiting factor, it would just be the infrastructure to test the models in how well we can predict that they perform. So if we have tests we can run immediately on a trained model and immediately says it messes up in these ways and it's good in these ways, then it's very quick to iterate on that. And I'd say it's building these tests and building these metrics that is very time consuming, and if you mess it up, it costs even more time because you find out later and you have to go all the way back. So I'd say the quality of how well we can evaluate the driving offline with tests, I think, is one of the limiting factors.
So you mentioned this bug that you had with the mapping continuous lines to themselves in the visual odometry. How did you fix that bug?
So we fixed that bug in particular by doing some basic filtering on the orb features that are tracked. So we do have a gyroscope which tells you how the car is turning, and we have some GPS data. Neither of those are accurate enough by themselves, but they're accurate enough to just do some basic filtering, throw out really bad orb features, and then the ones you have left are good enough to deal with the rest of it.
I'm coming. So Harald told you guys a lot of things today, but there's one thing that he didn't tell you guys, and that it's his birthday today. So will you all join me in singing happy birthday to Harald? Happy birthday to you. And Wire too. To you. Happy birthday, dear Harald. Happy birthday to you. Okay. I think we're going to say goodbye.
I was going to try to eat this with my hands, but that seems like a mistake.
It's a cheesecake? That's really hard.
I'm going to go find a fork.
All right, I think we're going to say goodbye to the live stream for an hour. Just a little bit of logistics. There's burgers in the back. Anyone with special dietary needs, there should be everything for you. If you find someone to help you if you have any questions. There's soft drinks all day and water at the bar. Help your. Just waiting for the thumbs up. All right, great. We're online. Hello, world. Obviously, this next speaker needs no introduction from me. George is the creator, the visionary behind Comma, and I'm beyond excited to introduce him to the stage. Woo!
I did make a presentation. It's going to maybe be up in a bit.
I worked hard on it. I made it in Keynote. Everyone else made it in Google. Present. Oh, Comic-Con Keynote. There we go. And that's my name, and that's today. We have a laser pointer, and you can go backwards. Oh, and we can go forwards, but can we go backwards? Oh, wow, we can go backwards and forwards. That's pretty cool. So we'll start at the beginning. This is me about 5 years ago. See a Bitcoin mug. I wish I bought more Bitcoin back then. That's the comma UI up on the screen. You can see we're detecting lane lines and kind of making it work. It's still the Engage logo from Star Trek. This was the original comma system. It's been a long 5 years. Had I known what this would have ended up being, I probably never would have done it, to be honest. Starting a company is absolute hell. But when you start out with things, you don't know this, right? Go into a full tilt, right? There we go, man. Comma.ai on the back of an Acura ILX, license plate, right? Fuel on, man. It just means like keep the gas going, bro. Or F you, we put this together and you go for it. It's like, yo, let's go to the Silicon Valley VCs, man. I was watching that show, Silicon Valley. That's why it's called Comma. Hey, if we're not having a good time, there's really no point in doing this. This is the original Comma team. Out at an event, self-racing cars. This was 2016, and a lot of the companies back then were way more honest and open. I think that this self-driving space is incredibly sad. I said this back in 2016. We are going to win self-driving cars. Still kind of holds true. Because, I don't like losing. Why do you keep doing it, right? There's no point. There's nothing you can buy with money. There's no amount of, I live a nice life. But I like winning. And I want to win, so that's why we're here. And I appreciate that you all came out. I remember before this TechCrunch disrupt, I was talking to my sister, and I was saying, what I really want to do is get up on stage, pull my pants down, and take a shit. No, really, because there's no other way. How do you compete when everybody's just lying? Right, so I'm like, all right, we're going to go completely over the top with it. This is all you need to solve self-driving cars. Look, it's in a neon green, it's a phone in a neon green case. It's kind of a joke, but it's kind of not. I think most of you have used that phone to drive a car. Right? It's kind of a joke, kind of not. Well, Nishta wasn't in on the kind of a joke, so I'm like, you know what? Canceled, no comma 3. Sorry, no comma, whoa. No comma 1. The comma 1 was canceled. Alex Roy wrote this article. He got a test drive in the car with the comma 1, and the canceled comma 1 would have embarrassed the car industry. Prediction, there will be a comma 2. Well, this was in October. 1 month later, we released openpilot open source. Really, all the ideas start to come together. It's like, we're going to be the Android of self-driving cars. If Tesla's the iOS, we're going to be the Android. So this is openpilot 1.0. You can see it has a lot less directories. I didn't think I knew how to put pictures and readmes back then. We figured it out. It's pretty nice now if you go to openpilot on GitHub. And as for Alex Roy's prediction, well, the open source software included the Neo. How many of you had Neos? All right, we got a few Neo people out there. How many of you had Eons? All right, and then how many of you have comma 2s? All right, nice to see. So it took a little bit for Alex Roy's prediction to come true, but we did ship a comma 2, and it did embarrass the car industry. This is Consumer Reports. If you guys didn't see it, openpilot is good. You know how I know openpilot is good? Like I said, I don't do this for money. I'm rich. I used to drive a Mercedes S-Class. What other car are you going to buy, right? But if you ask me today, would I rather have a Mercedes S-Class or a Hyundai Sonata with a comma 2? I think that one's actually better. Right? Like, that's how I know it's good. How much more does that car cost than that car? Even with the, egregious price of $10.99. Wow, these things are priced way too cheap. We got to raise the prices. What does it mean to be good? Right, so what's our slogan? Make driving chill. So we like to say that Tesla's slogan is, look at this crazy feature. I mean, again, maybe it appeals to a different kind of audience. But what does it mean to be good? Does it mean things like turning right at an intersection? Well, not really, because you just don't turn right that much in your drives. It happens every once in a while, but it's not that bad to do. And I've been in demos where the car's made autonomous right turns. It's stressful. It's stressful watching that wheel fly in front of your face. You're like, do I touch it? Do I not touch it? Is it going to do it? I don't know. I'm stressed out, right? Our slogan is make driving chill. So it's not things like this. It's things like this. So if you look coming up to that exit, you can see that the lanes widen. And what almost every manufacturer lane keep does is it places you in the middle of those two lanes. And you have an okay time right up until you get to the fork. Right? So what it should do is if you're going left, it should hug the left, and if you're going right, it should hug the right. But this stuff is really hard to program in ways that are reliable and repeatable. And you saw some of this in Harald's presentation about okay, let's say there was a dashed line there, right? It's just, there's so many variations. And what makes a system good isn't the crazy things that it can do, but it's the things that it can do over and over again, repeatedly and well. That's what chill means to me. So, yeah, that's what it means to be good. I remember I was 2008. It's like the nights of Whoppers. I would drive to Burger King and go get Whoppers. Asked my sister if she wanted to come and go to Burger King, and we're just talking about things. And I tell her, it's impossible to make a computer recognize whether there's a chair in an image or not. This is a task that a 5-year-old can do, and in 2008, computers just couldn't do this. And it was because they were using a lot of this sort of stuff. They'd run something like a Harris corner detector, detect corners, compute some orb descriptors, and then come up with some hacky definition of what a chair was based on some weird nearest neighbors thing, maybe. It just doesn't work, right? So how do you actually detect chairs in images? This is a trivial problem. I think even a 5-year-old can write the code to do it now. Import torch magic vision. Torch magic vision.predict, and there you go. And the way this, of course, works is they took lots and lots of images, and they labeled where the chairs were. And then they trained a neural net, which uses this algorithm called backpropagation, to improve the weights or the program that's actually detecting the chair. The program is learned. The program is not hand-coded. Now, you say, no, but Waymo learned this lesson, right? They're not doing the stuff on the left, they're doing the stuff on the right. Right? They're getting neural nets which put boxes around cars. They're fully deep learned. Yeah, but can these people think a little higher in abstraction space? What's the meta lesson here? Right? For the task of prediction, it's end-to-end, but the task of prediction is not the task of driving. Right? It's unclear how you go from prediction to driving. Why is this lesson still not learned? And why are these companies hiring cone guys? Well, really, right? You're gonna gotta dive into the taxonomy of cones. You have small cones, you have large cones. What does it mean if a cone is squished? What about the big cones like this? What about the thing outside with the, is that a cone? I don't know. Gotta hire the cone guy for that, right? So yeah, the lesson's really not learned. One of the things we say at Comma, one of the questions we ask all the time is, will this be in the final system? I find that people are by the way, we're proud level 2 at Comma. And we're proud level 2 for 2 reasons. One, because the higher levels don't say anything about capability. They only talk about liability. And we don't want liability, obviously. But you don't want things higher than level 2 either. Do you want to tell the machine what to do, or do you want the machine to tell you what to do? right? What the higher levels mean is you're no longer in charge. You're no longer driving the car. And like, some people might be okay with this. Like, I'm not. I prefer that machines work for me and that I don't work for machines, which is kind of, but that's long and philosophical. But, we're level 2 forever. But there's no reason that a level 2 driving agent should not be a superhuman driver. There's no limit to it. It's like, well, it can't be too good. It's only level 2. No way. So we always ask the question when we're building something, and you saw this morning with the end-to-end stuff. It's like, will this be in the final system? So this is a real story from a secret internal source at that company. They had these cars, and they were driving this little loop around Pittsburgh. And they really got the loop working well. In the winter, it could drive the loop most of the time without a disengagement. But in the winter, well, the bike racks looked like this, right? And the car drove by fine on the street, and it was all good. But then spring came, and the system stopped working. The system stopped finishing the same loop that it could do in winter. And they checked all their HD maps, and they were all good. It wasn't a localization issue. The bike rack didn't look like this. The bike rack looked like this. Now, if you're trying to build a system that individually picks out each bike, then runs a complicated prediction model on what that bike is going to do, how big is your computer? This, of course, isn't how humans do it at all, right? Humans just look at those things and they're like, oh, it's a bunch of bikes in a rack. So, well, what did Uber end up doing? They put that area in the map as an area with a bike rack, and they said, don't detect any bicycles in that area. We all know. All right, we won't talk anymore about that, but will this be in the final system is a real question, and a hand-coded, this is a bike rack, don't detect any bikes in this area, would never be in any sane final superhuman driving system. Another question we ask is this how a human does it, right? So when we think about, we're trying to do some task, we think, hey, let's think about how a human does it, because humans are the only implementation of driving today. People talk about how humans are bad drivers. Humans are so much better than every self-driving car out there, available or not available today. Do you know how I know that? Because the second that flips, everything's going to be self-driving. But we're nowhere near there yet, right? So people are like, oh, humans crash cars. Humans almost never crash cars. I saw a good graph. I probably should have put it in here. It was a pie chart of during your commute, how many times you crash. And it was 1,000 times, no crash. Maybe one time crash, maybe. Maybe 1,000,000 times no crash, one time crash. Humans crash cars very rarely. So there's only one safe policy for driving. And it's not just ask how a human does it, because a human probably does it in a good way. Everybody in self-driving understands that you want to build systems that are capable of predicting what the cars around you will do. But you do understand that humans are running that exact same algorithm. Humans are trying to predict what all the other cars will do. And they're assuming implicitly that humans are driving them. So driving with an inhuman policy is dangerous, right? You can say, oh yeah, but technically you rear-ended me, you have the liability. Yeah, but if you slammed on your brakes in the middle of a highway, you can make that argument, but you still crashed. There's only one safe policy for driving, and that's the human policy, assuming you want to interoperate on roads with other humans. Now you're going to get some wacko utopian people who are like, we're going to replace all the humans with bug people, and we'll put the bug people in the cars, and the bug people will drive according to these very, very rigid rules, but this is, well, I don't know. I like driving. Take it away. Right? There's only one safe policy for driving, and that's the human policy. This is our mission: solve self-driving cars while delivering shippable intermediaries. A cool test that I like to use about whether somebody is saying something is ask the question of what else they might be saying, right? Does the opposite of this make any sense? If some politician gets on the stage and says, we care about the children, could you ever imagine a politician getting on a stage and saying, well, the children aren't that important to us? No, of course not. So what's in this mission is very clear about what we have to do, but it's also clear about what we're not trying to do. We're not trying to deliver a return to our investors. Sorry, investors. We're not trying to aggrandize ourselves with self-importance by throwing big events with lots and lots of people. Wait. No, we're here to have a good time too, but fundamentally, this is the goal of our company. Right? And it makes it very easy for everybody to be aligned. The amount of political, how are we winning? If you believe we're winning, how are we winning? What are these other companies doing wrong? And they understand some technical stuff wrong, but I think they also understand some philosophical stuff wrong. This is our company mission: solve self-driving cars while delivering shippable intermediaries. And that brings me to the next slide, business. So comma is a business. That is our goal, and that is the mission of the business. But comma is a business, and we do have to operate in the business world. This is a quote from my self-driving, my 100x investment blog post. It's so sad. It's really so sad how, yeah. And it's because business selects for psychopathy. Maybe you guys saw the Nikola founder was indicted. Yeah, you know, he told the world that his truck fully worked, but actually what he did was he tilted the camera a little, towed the truck to the top of a hill, and had it roll down and didn't put a motor in it, right? Even boomers understand that's a scam, right? So, you know, it's always nice to see that, but it's these scams that are much more intricate that you don't exactly, you know, it's not exactly clear to point to the scam, but when you just look at a company that's raised $10 billion and has no revenue and now is like, we're going to do an IPO. Like, it went from companies aren't profitable to companies don't have revenue to companies don't have users. Right? So I promise this is the downer part of the talk. The stuff that I really like talking about is coming up. So the fundamentals of us as a business, we've raised $8.1 million. We've made $9 million in revenue. The next milestone here is to have over $8.1 million in assets, and the next milestone after that is to have over $8.1 million in cash. Because then undoubtedly we've created something, right? And I like that. I like that from a business perspective. Like, figure out how to, you know, make money. We sold 5,000 comma 2s. This is now the majority funding source of the company. And it's great because we're aligned with you. Comma wants the same things you do. We want openpilot to be better. You want openpilot to be better. We want to build better products. You want us to build better products. This is the beauty of capitalism when it works, right? It's like you have 3,500 weekly active users. This is a wild statistic in the context of how many we've sold. Over 50% of every piece of hardware we've sold is still being used every week. The only thing that I know that competes with that is like appliances and mobile phones. This beats laptops, this beats game consoles, and this crushes virtual reality headsets. The average use for a virtual reality headset, the average number of times people use a virtual reality headset is 1. Right? 50% still in use over a 3-year, we've sold about 2,000 eons. So it's over 50% still in use. These are our Shopify numbers. I challenge other businesses out there to start doing this. Post a screenshot from Shopify. You can see our sales going up. You can see our average order value is going up, and you can see our total orders are going up. Average order value is an important one that I like because these things are going to get more expensive as they get better. A lot of companies, if you're really talking about the kind of smash and grab approach or like the exit scam you see in a lot of companies, what they'll do with their hardware pricing is they'll price it very high at the beginning, capture the early adopters' money who will pay whatever they want, and then lower the price over time. I'm not doing that. We price it, and then we raise the price, and we've done that with every release. You know, the comma 2 went up a little bit in price. So yeah, the order value goes up over time, but we also think the value that openpilot delivers has gone up over time. Do you guys agree? Yeah. So weekly devices by type. So you can see our weekly active users is about the 3,500 we talked about. One of the things that I like here is this yellow line here is the comma 2. So most of our users are on comma 2s, which to me signifies that we've actually delivered enough of a better experience for people to upgrade. We did sadly deprecate the original Eon, but we offered free trades to everybody. Just pay shipping to Eon Golds if you wanted to stick on the old system. We do want to support this stuff for as long as we feasibly can. But remember, I'm not a No Child Left Behind guy. I'm a gifted program guy. So, we do want to push the high end, and we especially want to push the experience for, all the majority, right? The needs of the many outweigh the needs of the few. That's a Vulcan quote. We are comfortably in control of our own destiny. This is nice. This took some time. We're not IPOing. We're definitely not speccing. We're not selling out to bankers. I'm the majority shareholder. I'm the sole board member, and I am 100% committed to the company mission. I've never sold a share. My salary is $78,000 a year. I don't care. It doesn't really matter, right? And this is an important thing to realize, right? Like, I think about how good my life is. I live in a beautiful apartment in downtown San Diego, and my life is good because I have things like HVAC. You're the king of France, you couldn't get HVAC. You could order all your minions, build me an HVAC system, and they'd be like, oh, you want to invade Poland? What? So we're comfortably in control of our own destiny, and we are committed to making better and better technology every year. Why don't we work with car companies? We get this question a lot, and sometime I'll give some flippant answer about how they're hard to work with. But there was always just something that never sat right, and I think I can put some good business terms on it now since this is the business section. So this is the gross margin in automotive. It's 18%. Automotive is mostly you're going to grind out for these little margins. The dealers take their cut. It's a very protected industry. That's look at Tesla trying to get their direct-to-consumer model working. The dealerships are protecting their little cut. And you don't want to be in a place where everybody's fighting over a small piece of the pie. You want to be in a place where a large pie benefits everybody. You want to be in a space where the gross margin is high because it gives you room to experiment and have fun and build cool things. So the gross margin in automotive is 18%. The gross margin in consumer electronics, 58%. We're an aspiring consumer electronics company. No, this isn't comma's transitory business model. Look, we're not going to be selling dev kits forever. But, well, let's talk about our total addressable market. More business terms, you guys. We support over 130 cars. That's over 50% of all new cars sold in the US. In numbers, that's about 8 million compatible cars per year. There's about 25 million potential existing users. This is in the US alone. That's 0.02 market penetration to date. We have a huge addressable market. Right? Is it always going to be a dev kit that you self-install, that you have to know what a Panda is? No. It's going to be a consumer electronics product. It's going to be let's just say, if we build this, I can easily see a 1 million devices per year market. That's 5% market penetration. That's nothing. At a minimum of $1,000 each, you guys know what 1,000 times a million is, right? Yeah. I'm bringing back an old comma slogan. We're going to be so rich. We also briefly made comma gym wear, like a tank top. It said, we're going to be so ripped. This was a good pitch to the investors, but it's kind of true. Comma is defining the next device class of consumer electronics. Right? The smartphone, the tablet, the portable media player, the laptop, right? The advanced driver assistance system. I don't know if there's a better name for it, but we want to be the Android. I don't want to be the only company building this hardware. openpilot's open source. I think in the next 5 years, we're going to see a ton of these things start to pop up because the total addressable market is huge. The potential for profit is huge. And like I said, our company mission is to solve self-driving cars. The more people we got thinking about this stuff, the more people who want to, it's not working with us, right? It's not a partnership. It's not a sketchy backroom deal. It's like, here's who we are. Come play in this beautiful ecosystem. We're paving the way for you, right? Maybe one of you out there is making, action cameras or some, again, there's another consumer electronics device class, right? Build an openpilot compatible device. Let's live in a world where there's 10 of these to choose from, right? And I've seen a few cool things. I'll give a shout out to Blue Box. They launched a Kickstarter. I think their device is a little too cheap and a little underpowered, but it's the right idea. I'd love to see a world where you can, just like Android phones, you can pick from a whole lot of these to choose from. All right. That's the business section. Now the stuff that I like talking about. I told you to get more upbeat. That's a picture from a comma 2. You know what question I get asked all the time? George, how are you going to solve self-driving cars with one camera? Well, this is the comma 2 camera, and it's pretty good. You can pretty much see what to do on that road. But what if there's a car next to you and it's a little hard to make out what's going on in the distance? So no, the comma 2, now we can say it, the comma 2 is not good enough to build a level 5 self-driving car out of. I hope you all knew this, right? It's a driver assistance system, but we do want to get better. Like I said, we're not stopping. Oh, they're going to stop. Comma.ai only does highway. Do it all. There's no distinction. But we are going to need more cameras. Who's ready to count? One. Two. Three. Man, I always wanted to do one of these, you know? All right. So this is the comma 3. You guys can see a few changes. It's nice and slim. The display is stunning. I don't want to talk about how much I'm paying for those displays. It's more than the whole Lego. You can see navigation on the right. You see the basics of the openpilot interface on the left. You can see down here we have, this is an 185-degree lens, infrared. These are the same 2 infrared LEDs that are on the comma 2, so you get that same great nighttime driver monitoring. This is what the device looks like from the back. Yes, we finally made injection molded cases. They look nice. You'll see that we have 2 eyes, but not for binocular, not for stereo vision. Stereo vision at long distances is relatively useless, although this does exceed the human baseline, so if any of you, we're wrong, we got the hardware for stereo. In here, again, like I said, it's useless, but what it is useful for is you can see the 2 cameras on the back have different lenses. So that's a 185-degree lens on the right, and that's like a 45-degree lens on the left, so you can see objects that are really far away. Speaking of the cameras, they're really good. 1080p. Oh, but George, the Eon has a 16 megapixel sensor. And it does, so why is this only 1080p? The Eon's lens can resolve about 0.5 megapixels. It's not about how many megapixels you shoved into your sensor. It's about how many you can reasonably use and resolve. This sensor has, what's the benefits of less pixels? Look, I'm paying a lot for these sensors. I could put a 16 megapixel sensor in there, but you're not going to get better pictures. Your picture quality has a lot to do with how good your lens is and how good how big your pixels are, right? Bigger pixel, more light equals less noise. So yeah, these are there. You can also see that the lenses are fixed focus. So one of the big problems with the comma.2 data is it's kind of blurry, especially when you're like braking hard or when you're, the way that it works is the lens is on this tiny spring and then you have like a piezo, a little like actuator to press on the lens. Here we don't have any of these. We focus these at the factory at infinity. The depth of field is plenty to capture everything you need. Woo! All right. So about 1080p, 120 dB of high dynamic range. So that's up from 85 in the comma.2. 285-degree lenses for full 360-degree coverage. Yes, we can see all the way around the car. Narrow cam for far away. The human eye actually doesn't have sensors equally distributed throughout the eye. You have a center of the eye called the fovea, which is a very dense area. Digital sensors aren't like this. Digital sensors are in grids. But you can mimic this by using two cameras. And that's why the device has two cameras on the back. It has a fovea, and it has a outside the fovea. I'm sure there's a word. Some optometrists would know. It's an AR0231 automotive sensor. There is a 0233. You cannot buy it. This is the best sensor you can buy. It's 2 generations ahead of Tesla's. Let's take a look at some pictures. This is me and Alex chilling on the 5. Look at the upper left. You can really see, look at that road texture that we're now capturing. Full 360, you can see that down here, you can see that front pillar. We didn't consider this when we did the balloons. Don't pop the balloons. Yeah, you can see, the driver monitoring. Captures a whole lot more, so there's no more fiddling with your device to like aim it in the right sort of way to make sure it sees your face. It always sees your face. It even sees whether your hands are on the wheel. Oh, by the way, it also sees next to your car, right? So if there's like a semi next to you, we see it now. We see everything. This is its performance at night. Yeah. That's what those big pixels get you. Look at how in the narrow picture you can't even see that car right there. The gamma curve on this, I don't know about the gamma curve on this screen. It seems pretty harsh, but you can easily make out that car on a computer screen. So that means the net can as well. Driver monitoring at night with that infrared. Yeah, nighttime pictures. It's not a cell phone. We used 0 cell phone part. Well, I mean, it depends what you mean. We used a Snapdragon 845. Qualcomm's chips are half the price and more performant than NVIDIA's. A lot of people don't use Qualcomm because the software is nowhere near as, there's no easy SDK to use Qualcomm. So the Snapdragon 845 uses a completely different camera. The hardware is completely changed from the 820. Yeah, we reverse engineered that one too. It's in camera 2 in openpilot. So it's great that we can use the Qualcomm chips, and we plan to stick with Qualcomm really all the way till the end. Wi-Fi and global LTE connectivity, so it has the same connectivity as a cell phone. Of course, that works with Comma Prime. It's got Wi-Fi. It has Bluetooth too. We don't really test it, so what good is Bluetooth? But no, I'm sure the Bluetooth works. We did test the antennas. We got this device FCC approved. The device has an FCC ID. 2160 by 1080 OLED display. No more issues with sunglasses. And did you polarize it diagonally? No, it's not polarized. It's an OLED. I hear it actually might still be polarized, but it works great with sunglasses. No, the display is really stunning. You guys know the beauty of OLED. The blacks are actually black. There's no bleed. There's no local dimming. There's nothing like that. It's actually we went above and beyond. I should have included the video. We calibrated each OLED display. Like we had all this code to calibrate the camera for colors, and it was pretty easy to also just do the display. So every display that goes through our factory, we put a little camera on top of it and calibrate it to have the exact same color response as every other comma 3. I believe even Apple doesn't do that. Apple, you can, and Apple's very good about this. Apple has some of the best displays in the industry, but we actually take the time to calibrate it. That's the cool thing about having 58% gross margins. We can do things like this that are just kind of, above and beyond. Another thing that's above and beyond. We put a real gaming SSD in there. Like why not? It's almost the same price per gigabyte as SD cards. But why would we use a crappy little, did you buy a class 7 or a class 9? No, we bought a Samsung 980 NVMe SSD. You guys will see, we have some interior pictures coming up. High precision GPS, same one as the comma 2. And OBDC port, same as the comma 2. The harnesses are compatible. So it's the exact same harness. If you do buy a comma 3, you do not need to buy another harness. It has a right angle cable. The cable's a bit nicer, but that's included in the box, so you don't need to buy a harness if you're upgrading from a comma 2. It also has a USB 3.1 Gen 2 port. So finally, we have real expansion capabilities on this device. You're actually going to be hearing, we already have one expansion device being also maybe announced later. This USB port is capable of streaming out the entire sensorium of the device. So the 5 gigabits of bandwidth would allow us to stream all the cameras in full resolution if, say, we wanted to attach an external, GTX 3090 to it to run some really huge models. Also, just because it only cost $1, that's also a display port, so you can connect it to a big screen. Some of you guys want the comma screen? You can do it. You're going to have to get the Weston and a little software, but the hardware works. So yeah. This is the front of the motherboard. You can see this is the 845 SOM. We have a heatsink which sits on top of that. One of the problems with cell phones, the comma 2 runs hot. The comma 2, it's very hard. So the processor on the comma 2 faces the screen. In a cell phone, it's really hard to deal with heat because the only place really to dump that heat would be in the user's hand. So they try to dump it out the screen, but it doesn't work that well. It's glass, it's not metal. No one would make a glass heatsink. So we can put the heatsink right on top of the memory, which is right on top of the processor. But in the stress test, the comma 2s get up to 90 degrees Celsius. In the stress test for the comma 3, which is when we run it at full tilt, they range between like 60 and 65. So they run 25 to 30 degrees Celsius colder at full power than the comma 2. And it's because we can shove the heatsink right on there. We'll get to this in a minute. There's still a little Android in the device, but we keep it in that metal box there. We keep all the Android in there. Don't worry, there's a cover on it. It holds the Android in. It's the only way to get an LTE modem. We stuck a great LTE modem. That's the global edition. We've done some speed tests. You're getting, I think I've seen it up to like 80 megabytes a second, 80 megabits a second. It's LTE and it's good. Part of the reason it's good also is, a cell phone has these like crappy little antennas that have to go through your hand. We have 2 big antennas on either side, with ground planes behind this, and users not touching it. So the LTE reception is great. That's the front of the motherboard. This is the USB 3.1 port. This is the OBDC port. There's a daughter board which sticks on top of here that I don't have a picture of. It has supercapacitors on it. So you have about 5 seconds of power after you pull the thing. This lets us write the logs to disk in a safe way. It also gives us time to alarm if the device does immediately lose power. So it's the best of both worlds. It's not a battery, it's a capacitor. And you still get some power after. If say your car catastrophically loses 12 volts, you still have some, you don't immediately kill the device. So yeah, that sits right on top of there. There's a speaker also. I should have gotten pictures of it. 2 digital microphones. You know, maybe they're like little people. 2 eyes, 2 ears, a mouth, a brain, an LTE rate. Well, this is the back. There's that NVMe. That's the display connector. Underneath there is the IR LED driver. This is a Panda. So you guys know what the Panda in the comma 2 was called, right? Does anyone know the code name? The Uno. This one's the DOS. That's a DOS. You got a SIM card right here, RTC battery, audio codecs, sourcing for these things. You know, you guys know about the pandemic sourcing and like we got it. But yeah, these were one of the parts that was tricky to get. openpilot at launch. If you guys have been watching the code base, this is TC. It's already better than the comma 2 with 087. And this is for 2 reasons. It's not due to training. We've barely trained on any comma 3s, but the fixed focus of the camera means that it never goes blurry. And the processor is 8 cores instead of 4 cores, so every openpilot process practically has its own core. So your timings are much more consistent, your focus is a lot better, so openpilot is already a better experience out of the box. Agnos, a great new operating system, no more NeoS, it's Ubuntu 2004 based. apt-get just works. I did on one of these devices, I'm like, how did that work? Don't we have the system partition mounted read-only? And like the reply on Slack is like, no, we added a hook. It mounts it read-write, and then it lets you apt-get something, and then it mounts it read-only again. I'm like, that's so nice. This is like a nice development environment. This is a Ubuntu 2004 computer. As far as I know, we're the first company to ship a Qualcomm device with Linux. And Navigation Alpha is ready. That's not a mock. This is the whole reason we built Comma Prime. You think I wanted to deal with carrier I can't name and sign a contract to like resell? No, but we got to ship navigation to you guys. I mean, you need navigation if you want to solve level 5 self-driving or superhuman self-driving or anything, no liability. And you know what? I'll be honest about how good the navigation is, right? So if you kind of rank these like CarPlay, Android Auto, how many of you use that for navigation? And most of you, it's pretty nice, right? Then maybe sometimes you'll rent a car and you'll use phone and cup holder navigation. And then sometimes you use the, actually I don't know, you'll never use the built-in OEM navigation. You'll always use the phone and cup holder, right? The Comma 3 nav is better than phone and cup holder. And then once we do ship Navigate on openpilot, I think then maybe we can jump that. But there's no way to jump that right now. It is. I'm not going to lie to you and tell you it's better than CarPlay, but it's a very usable experience, more so than your phone and a cup holder. You'll be hearing more about this in the next presentation. Want to stand up? Everyone who was in EPOT? I think 7 of the EPOT people made it out here. These people have had the device for 4 months. They've been testing it. They've given us feedback. We went through 2 revisions. I now release you from your NDA. So feel free to talk about your honest experience with the device. Is it perfect? No, but a lot of the bugs are software. And it's now it's good. 4 months ago, it was kind of meh. 6 months ago, maybe 50% of the time it would work. Now, we don't even have comma 2s in the car anymore. You guys saw, maybe some of you saw on the stream, our leaked user admin screen where all the cars had comma 3s. So this device has been tested in the field for months. We've done way more testing on this than we did on the comma 2. We also ported over all our factory test infrastructure from the comma 2 to the comma 3. So these devices all, for example, have a 24-hour stress test. We test every sensor. We test the microphones. We test the speakers. We test everything in this device. Our goal is really, as we go forward, to drive reliability of these things up to the point that, someday, hypothetically, if you ever have a comma 7, the thing's never going to break. But the comma 3 should be a good bit better than the comma 2 on that front. So yeah, thank you, EPOT. Now, who knows what this slide is? What do you think's on it? 69,420, yeah. This is the price slide. $3,000? Nah, they start at $21.99. Double a comma 2, starting at $21.99. Now there are 2 variants of it, so before you go on your phone and place your order right now, you may want to wait to hear what the other variant is. So yeah, these devices are not. It's not a pre-order. This is pictures from our factory this week. They're already in production, and the first ship date is Thursday. Now, if you want to be in on that first ship date, well, you want to buy the cross-country edition. The cross-country edition has 1 terabyte of storage. It's the high trim. So if you guys like that, like King Ranch F-150, it's like this is the cross-country edition. It comes with this sick-looking boot badge, and it ships first. So all orders are first in, first out, but there's a bit of a priority element to that. We fulfill all 1 terabyte orders, and then we start fulfilling the 250 gig, which is the $21.99 base model. This one's $27.99. So yeah, those are the 2 models. The site should be up right now. First in, first out. And this is the comma 3. Yeah. Thank you, everyone. Really, I'm super impressed with the team that built this. We have really, the people on the comma team now, I mean, you saw some of them this morning. It gets harder and harder to beat us every day. I'm starting to think we're going to win. I'm starting to think, I was in an FSD beta. I'm starting to think we're going to beat them. I'm starting to think we're going to beat everybody. Yeah. There's a bunch of comma 3s in the back for you guys to actually go and check out and touch. Actually, I think I might have one right here. It comes in this beautiful stealth black box that it will ship in. So when it shows up on your doorstep, it doesn't say $21.99 on it. You can see the cross-country badge is included on the leaflet as well. This is the most complicated text we've ever shipped. It shows you how to mount it. And then, whoops, right under here, you'll see an actual comma 3 in the box. Yeah. In here, you'll find the accessories bag. Just get this open. I'm sure someone will do a much more beautiful unboxing of this device than I can. And you'll see that the accessories bag here, which is what includes the harness if you order one, or if you don't order a harness, it's just the mounts, a bunch of stickers, adhesive, and this right angle cable. This bag doubles as a carrying case for the device. So if you do want to take it off your windshield, you can put it in this beautiful little microfiber cloth. So that's it. That's the comma 3. And now I think it's time for questions.
All right, guys. I picked the wrong day to wear shoes covered in spikes.
It's not my birthday.
All right. It begins. All right. We got a question up top first. Great.
Looks terrific, George. Congratulations to the whole comma team. My question is, are the harnesses the same for the comma 2 as they are for the comma 3?
Absolutely. If you have a comma 2, we even made a special video, or Chris made a special video for upgrading from the 2 to the 3. It's super easy. It's the exact same harness, so all you need to buy is the device.
I will say that the site is now live.
Sweet.
And we will be shipping first in, first out. So
Cool.
now's your chance to get first in line. We got a question up there. Go for it. Yeah.
That sounds so boring. What am I going to get up here and show you sexy pictures of auto insurance?
I can't believe that's the first time we've heard that.
Listen. That's great, and they can do that. They're welcome to. They're welcome to play in our ecosystem. We're not going to tell them not to. But after we solve self-driving cars, let's solve home robotics and AGI. I don't know, insurance sounds boring. The Comma 3 it's a little head, kind of, you know? I'll take it out. It can be touched.
All right, I got a question back here, George.
You guys see the similarities? 2 eyes, 2 ears, a mouth, a USB port. What power goes in, right?
I got a question back here.
Hello, what are the biggest challenges with building a world-class team, and how do you and Comma overcome these challenges?
Basically, we do very little outreach, mostly reach in, and you can ask yourself this question. Do you want to scam for the rest of your life, or do you want to come here and actually build something? That's it. And people show up, and they want to build something. They got skills. They're motivated. Welcome to Comma.
Is there anything different about the cross-country edition other than the storage and the badge? Like, do you upgrade my car's warranty, or?
I would, cross-country is also included right here. The cross-country edition has enough storage for an entire drive across the country. That's why it's named the cross-country edition, and it ships first. And yeah, the cross-country edition. They're both great. They're both a great choice.
Hello. I already ordered my Comma 3. Thank you.
Great.
Persuaded.
This is who funds our company.
So I'll preface this with, I also think he's completely insufferable, but why so much shade for Elon?
What shade did I throw at Elon? Look, no, I actually have a lot of respect for Elon. I seriously do. Elon is a man who has a positive vision for the future, and that's what we need more of today. Elon can talk about the future in such a way that it's a future that I want to live in. So, we're just playing. You got to have a worthy adversary, right? If he's Sherlock Holmes, I'm Moriarty.
All right, we got a question upstairs.
But Moriarty respects, Mr. Holmes. Otherwise,
Hi, George.
Why play,
Hey, George. Nice product. What's the kind of benefit of having more storage, like practically speaking?
Oh, it just stores more stuff.
Like porn?
The driving performance is the same on both devices. You can choose which one you want to buy.
Yeah. Another question, is there any trade-in program for existing users or some sorts?
Not yet. So we made...
I'm going to say never, but probably not.
Yeah, so, it's not like we have a warehouse full of thousands of these. We are building them as we speak. So, maybe someday if we have excess capacity, but they're kind of hard to make, and we make them, we test them, we reject all the ones that fail even one test. So, they're going to be probably fairly limited supply for a bit. Maybe after that changes, we'll see. Oh, with respect to the Comma 2. So we still have, I think it's 791 Comma 2s in stock. We're not going to stop selling them. The Comma 2 from today is going to be supported for 1 more year. So there's going to be 1 more year of openpilot updates. It's not going to get features like navigation. Navigation's hard to make work on the comma 2. The processor just doesn't have that much more power. But things like end-to-end longitudinal will likely come to the comma 2 as well. No promises, but we're not going to artificially, things that are easy for us to make work on the comma 2 will also work on the comma 2. And there will be at least 1 more year of core openpilot software support.
Thanks. I got a question all the way in the back in the center.
What's up, George? Awesome products.
Thank you.
Is the C3, so is the storage replaceable and upgradable by the user?
Well, we gotta go to the picture. Oh, these take, yeah. I will warn you that actually these drives, the reason we use the Samsung drives isn't just because I'm a nice guy. It's because most of them are egregiously bad at low power modes. So, I mean, you can change it, but when your device, kills your car battery, you can check it all. You can check it all. It's not as easy. It's not like you have a desktop where power is effectively unlimited. So yeah, you do want to make sure that whatever drive you put in does work with low power modes. But that's a PCIe slot. You can put anything in there. We tested it with a Google Coral as well, if hypothetically we want to put an accelerator in there.
Great.
This is a question about the driver-facing camera and the sensor fusion stack. So it seems like the car frame is going to be possibly a factor that's invariant or not invariant across car designs. How do you intend to get around that when fusing the cameras?
So probably the same way we do everything, which is big data. As long as we have
So sorry.
As long as we have enough data from enough users, the models will become invariant to this. Maybe we'll rehash back to one of the things, how does a human do it? Right? It's not that big of a deal.
Let me just say, so I also already ordered my cross-country edition.
Woo!
My laptop right here. Do you see there being plans for some kind of Sentry mode of way of with that expanded storage?
Next talk will kind of get into some of this stuff. So remember that every resource comma puts on something that's not self-driving is a resource that's taken away from self-driving. So it's not high on our priority lists, but this stuff does still have to be usable. We have some cool announcements in the next talk.
Hey, George.
Yep.
Congratulations. And just wanted to ask you to touch on the boot time.
Oh, the boot time. Well, it's not, guys know I'm just a cheerleader, right? I'm just a guy who comes up and presents these. So, it's really congratulations to the team. The boot time is, it's been a while since I've used a comma 2, but I think it's better. It's not too much better, and there's a lot more that we can do here that we couldn't do on the comma 2. So, for example, the comma 2 is a Leica with a locked, you can flash whatever kernel you want, but the bootloader is signed. There's no signing enabled on the comma 3, so we can go all the way up the stack. And our goal is to get boot times down to 5 seconds, but that's not hardware, that's software. So it'll get better over time. I would say now it is at least as good as the comma 2.
All right, I'm coming for you.
One of our things at comma is always no regressions, no regressions, no regressions.
Yeah, so I was wondering about the, if you look into the commercial use case for this, because it seems like it would be very interesting for fleets. Mm-hmm. And also given that it seems like people are asking the self-driving CEOs about crypto, I'd be much more interested to hear your thoughts than someone else's.
All right, so what was your first question? So it's limit 2 per customer right now due to limited supplies, but that will go away. I think we'll do the same sort of bulk discounts. Look, I'm not working with them, but can they buy them and use them? Absolutely. I'm not going to say no, right? You know what? One of the things that I really like, You know, one of the things that during like the PlayStation hacking, I would say stuff like, when I buy this PlayStation, it's mine to do whatever I want with. And I feel the exact same way about comma products, right? Like if some fleet wants to buy them and use them, we're not going to tell you no. Nobody asks you what you're going to use it for. You might get banned from our servers if you make unsafe changes, but that's our servers, right? Your device is yours to do anything you want with, and I really believe in that. Yeah, can fleets buy them and use them? Absolutely. And what's my take on crypto? Oh, well. Pump, 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 pump. Pump, 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 pump. Die to $2. Tether to the floor, die to $2. Cheap ETH.
So on the business side, you kind of covered the U.S. market and the potential there, but I was kind of curious if you could share some on the European market or other markets in the world.
I'll ship it to any country that doesn't ban me or charge insane import taxes.
So you are in those markets and you see growth?
If someone from another country orders and pays the shipping charge and pays the import charge, again, I'm not going to say no. I'm not a no kind of guy. We don't track any of that. Okay.
All right. I guess I get to be the third to say I've ordered mine. So.
Cool. All right. Things are looking good for how many we ordered.
So it runs Linux, so probably it could be used as a hotspot with great antennas. It sounds like that'd be nice in a car to have like good reception maybe or something.
Oh yeah, I mean the Comma 2 could be used as a hotspot too.
Right,
I think we have the same feature. You can toggle tethering, it works. You can also, so our SIM is not that fast. The Comma Prime SIM is half megabyte.
Cool.
The upload is faster though, but it's supposed to be half megabyte symmetric, but it's actually like 1.3 if anyone benchmarked it. But that's a nice LTE modem. If you stick a real SIM in there and turn it on, yeah, it works great.
Sounds awesome. And are you also aware that you probably build a pretty great baseline? You're heckling VR a lot, but that's a pretty great baseline for kind of another case, and it'd be a nice VR device as well.
Yeah, VR has a bunch of challenges. I can talk about this stuff at length some other time. It's unclear what the beauty of the Comma 3 is when you buy it, when it gets to you, you're going to be able to use it to improve your life tomorrow, right? No waiting for anything. I mean, you guys use openpilot. If you like openpilot with the Comma 2, you're going to like it even more with the Comma 3.
So you said beautiful product and great presentation. You said something to the effect of level 2, the machine, you tell the machine what to do, and higher levels, the machine tells you what to do. Can you say more and maybe give us a glimpse into your roadmap?
Well, when you get in a Waymo and when you touch the steering wheel, it pulls over and locks you out. Who owns that machine? I like owning the machine. In openpilot, when you take the wheel, you turn it. It's your wheel. You paid for it. Does that answer the question? I'm not sure what else there is. What is our roadmap? Get to superhuman as fast as we can. Win self-driving cars, right? I don't know. Look, if I was betting, I'd still probably bet on Tesla, but we'll be close.
All right.
Question on the navigation. So do you expect me to reach for the screen and just type it in there, or is it going to be through the app?
God, what, am I trying to build an OEM navigation experience?
Savage.
Yes, please scroll through each letter. No, go on your phone, type in the destination, and it goes over Prime, and it's sent to your device. It's real nice. We do have shortcuts that you can program in from your phone. You'll see more about this in the next presentation. But you think I'd design something terrible like that? I'm telling you, I use it. I want to use these things. I drive around that Hyundai Sonata with openpilot. I use the nav. I'm not using it if I'm typing in, oh no, I hit the D. Oh.
My question is, does nav integrate with like auto lane change or suggested lane change?
Soon. So we need to gather the data first. So remember that the way Comma works is we gather the data from all our users, and then we use the data to train the models. So once there's a whole bunch of Comma 3s out there, all the Comma 3s will get better. And we put it this way. Navigate on openpilot is a simpler feature to build than end-to-end longitudinal. We know how to build it. I'll tell you guys. You see that nav screen? We racked our brain for a while about well, what's the API? Right? We have the Desire stack. You'll hear more about that. Desire is cool for things like lane changes, which aren't covered in nav. But for all the rest of it, well, we just asked the question, how do humans do it? Well, humans watch Waze, right? Or watch a nav system. So we're just going to take the picture from the nav system and shove it in a CovNet and put it into the model, and I think it's totally going to work. Why would it not, right? If a human can learn from that information, so can the machine. So navigate on openpilot is, look, I don't like being Elon and making predictions I can't keep, but I'm sorry, I'm ripping on Elon. You know I got a lot of respect for the guy. I don't even rip on, who's the COO? I don't even know, right? Oh, there's two, the co-CEOs. Yes, that's a great sign, guys. He's CEO. No, he's CEO. Oh, she, all right. That diversity is good. Yeah, I would say that there's an 80% likelihood that we ship Navigate on openpilot within the next year.
Okay, so you talk about how you want comma to kind of become like an ecosystem, like Android is.
Sure.
You know, what products do you think, or are you excited to see, you know, for, you know, the ecosystem as of now?
Yeah, so we're focused on the high end, and this is a decision that we had to make as a company. We talked about building lower end, cheaper devices, maybe the kind of like tiny device without a screen. And then again, you run into the same car insurance problem, which is like, that's kind of boring. Right? Like no one's going to get up here and clap if we talk about the iPhone 5S or whatever it is, you know, not the S. What's the, no, the SE, yeah, the SE. It's like, oh, and it's a little bit cheaper and it comes in 10 fruity colors. Like, while I don't personally want to build that, I would like to see those things exist, right? I'm very much a believer in like the big pie mentality of economics. So I would love to see people who are capable of, you know, building and managing like large numbers of devices that maybe comma right now can't do, kind of getting in on the low end. It's going to be hard for them to build a high-end device, right? Because they don't have, you know, the high-end devices work great because they integrate really well with the software. You see this with Android. But there's some people who just want any kind of LCAS system, and they'll buy up the low end, right? And you see this exact same thing with Android. The Google Pixel is a high-end phone. The Motorola J7, well, it's $60, and it comes with a Boost Mobile, you know, month, right? So like that's what I want to see from people in the comma ecosystem. But hey, if people want to compete on the high end, I love that too, right? I just want to see all this stuff get better because self-driving cars are just the tip, right? Like self-driving cars are just the beginning of what all of this technology can allow. I want robots that clean my house and cook me food, right? It's the same tech.
We got a question up there.
Hello, George. Good to finally meet you in the flesh. Quick question. Can you touch on what the microphones are for in the comma 3? I mean, can I use it for nav, or what are they going to do?
We put them in because it was easy. The comma 2 has a microphone as well. We're not recording you. You guys can read the code. One of the first things that I'd like to ship with the microphone is something that adjusts the volume of the alerts based on the ambient noise level. Right, so we can use like a service to estimate how many, you know, if you have loud music playing, the alert should be louder. If you're in a dead silent car like a Hyundai Sonata, the alert should be quieter. If you're in a Toyota Corolla, a little louder, right? Like it should be, so that's one of the first uses of the microphone. The like voice nav stuff, again, the OEMs kind of try this, and while I think we could build something better than the OEMs, there's still nothing that compares to just copying the address in your phone. So they're there because the hardware would just feel incomplete without them.
Right on. Thank you.
Got a question in the front?
Yeah, very excellent. I feel embarrassed to say that I own 2 Teslas that have already paid for full self-driving.
Well, they're nice cars. The software.
$14,000 spent on what I could have bought. But I saw in the thing on the website that you're offering this for the Tesla. Will it plug in? Because I've been waiting for full self-driving beta, and I'm wondering if I buy your device and plug it in and it works, maybe they'll send me the full self-driving beta.
Well, so Robo, who was up here earlier, has a Tesla. He's done a lot of the work pushing the Tesla port forward. There's a whole community of Tesla people too. Collude, MacGyver, it's a lot of community stuff. So will it work? Yeah, you have to make one line change to the code. The reason the Tesla actually isn't under community supported features is we can't do the same kind of steering on the Tesla that we can on the other cars. It's very hard to make the Tesla steering wheel overrideable. It has that kind of Tesla feel where it's locked and then it disengages. We just don't think that's really an open pilot experience, but it's relatively easy to do this. We should sell the Tesla harness. Yeah, we should, you can do it, but it'll take a little bit of work now. It will get easier over time. Remember that, like, also, the stuff that's live now is not, I'm not selling anybody full self-driving. I'm selling this on the hardware specs, right? Like, you're buying this for hardware specs. Don't expect it tomorrow to put this in your car and it's going to make a 90-degree turn. It's not. Right? I'm not even that interested in that. What I am a lot more interested in with this hardware, and the places where you're going to start to see disparities between the 2 and the 3 are things like trucks in the neighboring lane, like moving over for them. Right? The comma 2 just can't see them. Another place you're going to see a disparity pretty soon, if you don't already, is detecting a far-off car at a stoplight in a distance. Right? The comma 2 camera, it's the lens. It just does not have that much. Yeah. As soon as as soon as we sell like 1,000 of these devices and we start getting the data back from them, we're going to be able to train models that significantly outperform the comma 2 just because the raw data is better.
Great. I think that's it. Any last questions? One more, Logan?
Could you speak a little bit more on the dynamic range of these cameras and their ability to see into like harsh lighting conditions and things like that?
It's a lot better than the comma 2 in Tesla, I'll say that. Their AR0231, you can look up the data sheet of that sensor, multi-exposure, 120 dB. I think it's probably the highest dynamic range camera you can reasonably buy. There are some in pre-production that have a little bit more. It's not quite at the human eye level yet. But the human eye has absurd dynamic range. But it is the best thing on the market today for that, and it should be a big step up from the comma 2. I think the human eye is like 150. This is 120. The 2 is 85. The Tesla's 95.
I think that's it. We did it.
Could be yours.
I'm very excited to say there's 3, if you guys look back, set up back there, you guys can take a look at. I'm so excited. We finally could talk about the comma 3. The team has done an incredible job. We've had them in the cars for months. They're unbelievable. I know George is like an epic salesman, but like as a regular person, they're a life-changing experience. I'm beyond that you guys will get to have them in your cars. Willem, who runs openpilot, unfortunately cannot be here with us in the flesh today. So we are, you guys, going to do our absolute best to bring him onto the screen for you, all the way from the Netherlands. We're going to do our best to try to maybe squeeze in a Q&A, but no promises. There he is in a tiny box. Hi, Willem. I mean, as you guys know, our live streams are not always great. Like, we really tried here. This looks great.
So I'm head of openpilot. My presentation will be about openpilot. So the responsibility of the openpilot team is basically all the code that lives on your device, so your comma 2 or your comma 3. From the research team, we get this nice blob of weights from the neural net, and then it's our job to run this as stable as possible, to interface with a whole bunch of cars, and to do this reliably. We're basically trying to build the most stable robotics platform that's possible. So in my presentation, I'll be going over some openpilot features. I'll be taking you on a history tour. But I'll start off with this. Solving self-driving cars is a software problem only. Some people think this is what a self-driving car looks like. It's a car filled with computers, because otherwise, yeah, you can never build a self-driving car. Of course, we don't think this is true. If you would ask someone at a traditional self-driving car company what you would need, they would say you need a lot of cameras, you need a LiDAR, of course you need a LiDAR, you need a radar, you need IMU, so a gyroscope, an accelerometer, a GPS, and definitely a trunk full of computers. Well, everyone knows that LiDAR's a scam, so we can immediately cross that off the list. So people use this to make their HD maps and then localize themselves in the HD map to do their planning on. Yeah, that doesn't scale, so definitely no LiDAR. I can also say confidently that a trunk full of computers is not going to be necessary. We can run openpilot very comfortably on the Comma 2, and the Comma 3 is even better. So yeah, and it's not a problem of compute. I'll get to that later. Definitely not CPU. Then we can also cross radar off the list. We've been using radar for quite a while. I looked a lot into the data that the radar gives us, but the data is actually pretty shitty. You get this like one line, you get all these false positives. It's really hard to tell apart like a stationary car or like a manhole cover. So we very quickly switched to a system where we only use vision to tell if a car is there or not, and then we still use the radar to give us a speed, because the radar gives us a Doppler shift, which is an instant measurement of the speed, which is very nice, but we're also moving away from this and just trusting the model to give us the relative velocity of the car. And Tesla is doing this now as well, so this shows us this is very, very possible. And I would say an IMU and a GPS are kind of optional for the driving part. Over time, our models have become very good at estimating the motion that the car is going through. It will tell us the rotational velocities and the accelerations and the velocities. And the GPS, of course, you can drive through a tunnel. So without a GPS, it's very possible to drive. But yeah, for ground truthing, those things are very nice. So we definitely put those on. And then the most important part is the cameras. If you have some very good cameras, which the Comma 3 has, this should be all you need. This is what a human drives with their eyes. So yeah. Good cameras are very important, and the cameras on the Comma 3 are really amazing. I worked quite a bit with them already. George talked about the 120 dB of dynamic range. They do HDR, they do full 4 exposures at the same time. So you have 4 exposures, and each successive exposure has a 16x shorter exposure time. So in this way, you can see very dark but very bright areas at the same time. So yeah, this is kind of what represents openpilot over time. We've been running on the LAE code or the 1+3, and basically openpilot has always filled all the available CPU space, but it was always fine. Like if we wanted to try to ship a new feature, we would free up some CPU, we would rewrite something in C++, make it faster. And then in the end, we always had the CPU available to write the feature we want. So yeah, we've been running on 2016 era smartphone for quite a while. And actually we downclocked the CPU a couple times just for thermal performance because the cooling is really terrible. But still we're only using like 65% of the CPU. I mean, the GPU is a different question, but CPU, there's definitely plenty of. So yeah, now I'm gonna take you on a tour of openpilot features, some nice milestones, basically from version 0.1 to the upcoming release version 0.8.7. This is between 2016 and 2021. So this is basically pre-release. This was the Acura ILX with still with a computer in the back and the joystick to engage and disengage. This is what George took the Bloomberg reporter on to Vegas. So this is kind of the shape of openpilot. You can see the openpilot UI in the bottom left. We still have that debug UI around, so happy to see that code still exists. And then it was time for basically the initial open source release, which ran on the Comma Neo. It's like this whole DIY, the 3D print a bunch. And this is also where the neon green color came from. We got a bunch of 3D printers. And when you buy the 3D printer, it comes with a little bit of free filament in the most hideous color you can imagine, of course. So that's why a bunch of our stuff was neon green. think we still have quite a few spools of that left. This is what the UI looked like back then. So very engineering, hackery with all the green boxes, all the lines. But over time, that got a lot nicer as well. Then I want to talk about a feature in 0.3.7 about model predictive control. I mean, the feature itself is nice, but this was my first feature I shipped as an intern after I joined Comma. This basically made the controls way more smooth instead of some it turned it into an optimization problem. So you put in like the position of the lead car and the velocities of the lead car, and then you try to optimize the brake and the gas and the steering to get the most smooth maneuvers possible. And a lot of this code is still around, which is very nice. Harald made some tweaks to it in the meantime, but the basic stuff is still around. So it was pretty cool to see that at Comma, when you write a feature and then in a few months you have this running. I mean, at the time I had a few hundred users, but now it's like thousands of users that run your code. Another feature I worked on as an intern was forward collision warning. This is when I kind of realized that the power of all the data that Comma has. So when you, at the time, this wasn't no machine learning, but I used the model outputs to see what the car in front was doing. And then I made some rules to come up with when to show the forward collision warning. Then I could use all the data to see if this had any false positives, to tweak the algorithm. And this really showed the power of the data. And this is probably something the OEMs can't even do. They have to go to a test track and some testing. 0.4.4 was the big flippening. Thought it was pretty funny. So when we designed the original Eon, we actually put the selfie camera on the right side of the device, which turned out to be a mistake. When we wanted to start gathering driver monitoring footage, we wanted to put the camera on the left. So we just flipped everything around. Luckily, the Eon case was symmetrical, so with a hex screwdriver, you could take it apart, flip the mount around, and then put it back in your car. Chris even made a nice video about that 3 years ago. So this was the first step towards driver monitoring, which is very important. When I was going through the release notes, I also noticed this pretty funny thing in version 0.4.6, which said fix all memory leaks. I don't think that was actually true, but it was very optimistic at least. In version 0.4.7, we shipped the first model with our improved ground truthing stack. So before we tried to recover the path that the car took, we mostly used the gyroscope for this, and then all gyroscopes have a bias, which we didn't remove properly. So before this point, all the models had like this bias that would point you slightly towards the right. If you looked in the distance, the model would always do this. So we had this fixed offset of 1.5 degrees, which we always subtracted before we sent the angle to the steering controller. But after this, it was finally gone. So just close, cool to mention. Then in version 0.5.0, we shipped driver monitoring. I'm sure Weixing is going to talk a lot more about the driver monitoring. But yeah, as openpilot started getting better and better, like in the first version, we had this bar that took 6 minutes to count down, and you had to touch the wheel. I mean, 6 minutes now, in hindsight, is a very long time, but openpilot messed up so often that you felt very proud if you actually hit the 6 minute mark and you're always paying attention. But then as openpilot got better, it made less mistakes, and then it became very important to make sure that the driver was paying attention. And yeah, you can just make the wheel touch time shorter, but at some point that just becomes too annoying. So we actually want to make sure that the user is paying attention. So we look at their face and see if they're looking at the red. Then in version 0.5.8, we open source VisionD. We always joke that we were probably one of the first companies to actually ship a neural net on the edge, on like a device in the field. Back in the day, we wrote our own OpenCL kernels to do all the neural net stuff. But at some point, we shipped to the SMP, which is a Qualcomm library, to do it as well. And they have all these nice OpenCL kernels. I reverse engineered their library once, and they're super tweaked for what the Snapdragon can do. So they're super good. So we switched to SMP. And then, so we just decided to open source Vision D. And at that point, all the code in openpilot was open source, which is a pretty cool milestone. Then in version 0.7.7, we actually started driving on the localizer, so to speak. So all cars, of course, are different. All the tires have different grip on the road, and this can depend on like how wet the road is, how the temperature, and there's the steering. There's like the manufacturers list some end-to-end ratio usually, but this is not true for all driving. So we tried for each car, we tried to estimate the vehicle model. And with like 130 car support, this is very important because you can't be measuring this for every car. So we actually estimate this offline. We look at how the car drives, we look at the steering angle, the speed, and then we predict how we think the car should drive, and then we could tweak the vehicle parameters a bit so it matches our expectation. And this is very important for things like banked roads. So if the road is a little sloped to the left or right, then you would start hugging. But this actually takes care of that. It sees that the car is not driving as expected and then compensates for that. In version 0.8.0, we shipped the first full 3D driving model that would not only output lanes and paths in X, Y, but also in Z. And this was mostly useful for the discussions the openpilot team had with research. We would look at like a replay, and they would say, no, this model is overestimating the turn. But you had to be very careful because of projection errors, that if the road would slope up or down a little bit, it would completely throw off how the lines looked. And the research team always said, no, it's not overestimating. It's just a projection. And then, well, it turned out usually, in a lot of cases, we were right. And this is one of the bugs that Harald was talking about with the yellow lane lines at night. And then in version 0.8.3, we shipped the first end-to-end lateral model, which is a very big step, which is something that the research team has been working on for a very long time. And I'm very excited to see what the future of this will look like. And then in the same release, we also switched to a UI in Qt. We had this massive code base in React Native. All the UI was an Android APK. And then with at the time we were already working on the comma 3 as well. So yeah, we moved the whole UI to Qt. It's super responsive now, and it's all lives in the same openpilot code base. So we didn't have to rewrite all the messaging stuff. In January 2020, we also made a very important change on how openpilot is developed. So openpilot used to be developed in a Cathedra-style open source, which means all the development happens behind the scenes. And then when there's a release, you get this dump on GitHub with all the source. But of course, you want to get contributions from the community. So people still make PRs for things like car support. This kind of became like a pain to merge because like the code base, the public code base was already behind. People couldn't see what we're working on. We started running all the CI behind the scenes, but then we couldn't run the PRs on the CI. So in January 2020, we just decided to develop everything in open source. By the time we also didn't need to test in cars anymore. So we could be pretty certain that if our CI passed, that the code probably wasn't broken. So if people started running that on their device, it wasn't such a big deal. So this was our old mono repo. It was called One. Everything was in one repo. Yeah, and then this grew over like the 3 years that we used it. But now everything is done in the openpilot repo, and you can see this in the graph. The number of commits went up significantly, and now all the development is done in the public. No secret stuff. Even the comma 3 stuff has been developed in the open. Some people notice, but yeah. So yeah, I think this shows us very nicely how far we've come from version 0.1 to version 0.8.7. Sometimes progress feels slow, but it's always good to take a step back and see how far we've come. And I think this is very promising for what the future will show us. If we can get this much out of a 2016 era smartphone, I think that proves our point that this is just a software problem. And if we just keep chipping away at the software, it's just going to keep getting better and better. So what's next? I think the most important part is stability. It's definitely a few features that still need to be developed, but yeah, stability is very important. So we're targeting 1,000 hours between failures. So it means unplanned disengagement. So this can be anything from a hard reboot, which is very rare now, but also like communication error between processes. So if you don't meet the real-time deadline or other unexpected like planner failures or model failures. Of course, we're going to start to keep supporting more and more cars. And the openpilot team is also going to prepare running larger models. It's mostly a bandwidth problem with the GPU. So just by writing all the processing stages of the video, so it's like all the debayering, all the conversions we do, just to make sure that all runs on the GPU, stays on the GPU, do efficient messaging. So yeah. And of course, we're going to talk about navigation, but I'm going to talk more about that later. And I also want to usually thank the community who also make, especially all the 130 cars we support possible. You can see this is just past month. We had over 200 pull requests merged, which is pretty cool. I think a while back on Hacker News, someone made a tool to see how fast PRs were merged. And it's also cool to see how quickly we were processing all these PRs with quite a small team. But yeah, this small team forces us into certain things, like not writing a lot of code. But these are usually good things. Like we see this in research too. It's like, yeah, we're not hiring a code guy. We're a small team, so we have to make sure that we have as much leverage as possible. So yeah, this end-to-end approach makes a lot of sense. And if you have a lot of people, you're tricked into these approaches that don't scale well, and even with all those people, still will never work. So I think this is true for the number of lines of code as well. If you can do a lot with not a lot of code. So yeah, like the pseudo project, it's like over 200,000 lines of code. Yeah, and with openpilot, we're trying to keep the number of lines of code below 100,000, and so far we've succeeded. Now we can also plot this over time. So yeah, you can see version 0.5.8, there's a big increase when we open source Vision D and Camera D. And then in version 0.7.7, we started to get awfully close to the 100,000 line limit. So we did a big cleanup, started to remove all unnecessary code, and that got us comfortably down to 60,000 again. And this is still an amount of code that one person can keep in their head. I know what all the moving parts are, and this makes it a lot easier to develop on openpilot as well. But as you can see, the number of cars that support it keeps going up. And Robin mentioned this as well nicely, that we only need 45 lines of code per each supported car, just because we have very nice car abstraction layers. Also want to talk briefly about the hardware that's needed to run openpilot. So in the past, it was the comma.ai, which was this DIY project. It's like we had this manual on GitHub, you had to 3D print some parts, order a board, and you had to like solder a connector to your car. You lost all stock system capabilities, but that's luckily no longer the case. Then we shipped the Eon with the Giraffe, which had some nice switches. But even as a comma employee, I could never remember what all the switches did. Always had to look it up, so it's not great for usability. And then that was fixed with the comma 2 and the car harness. And this turned out to be the future, and this is still used for the comma 3. I'm also going to show a bit of the UI progress we made. I think this very nicely shows how much openpilot has progressed as software. I think the UI quality really nicely shows the state of the self-driving code as well. So this is the original UI with the nice hacker font. This is what something in a movie would look like. But then started to become nicer and nicer. This is all the React Native stuff. It's turned out to be a mistake in the end. But, and now we have this beautiful Qt UI, which looks really slick. To develop openpilot, we also had to develop quite a bit of tools and libraries, which I'll go over briefly. So we developed Cabana, which is used to reverse engineer the car. Robbe also talked about this a little bit, which produced OpenDBC, which is this big GitHub repository with all the reverse engineered signals. We also added openpilot support to plot juggler recently, which is this very smooth, nice plotting library. So you can plot all the signals of all the openpilot modules and how they're communicating with each other. It also parses out all the data from the canvas, so you can plot those together. Yeah, and it can also do live streaming. So if you're testing something in the car, then you can see it live for tuning. This is so much better than all the one-off Jupyter Notebook scripts we use to Riot, and it's so much faster to debug stuff with this. We're also added support for Carla, which is a great way for new users to experience OpenPilot, where they can try out OpenPilot without a supported car. I mean, Carla is not the most realistic simulator, but I use it from time to time to see if I'm writing a new feature, just do some sanity checks, make sure I didn't mess up a sign or anything. It's not steering left when it's supposed to go right. We also made Explorer, which is a nice way to view all your drives, all your dashcam footage, but I'll talk more about that later. So we overall, we made quite a bit of progress. Went from a proof of concept to well over 3,500 weekly active users. We went from a 3D printed case to an injection molded case. That's like a real product. We built some nice developer tools in the process. And we also built some very nice libraries. So we tried to keep the number of dependencies low, but they also need to be resource efficient. So we wrote message queue. So we used to use 0MQ, which is a nice socket library, but I used quite a bit of CPU. So we wrote our own library, which uses shared memory. Research team wrote Leica to do GPS processing, and we developed OpenDBC in the process. I also want to talk briefly about my time at comma. I've had a great time at comma so far. I was looking for an internship, and then I saw the program. I got sent a programming challenge, which I thought was a really cool way to hire at the time. So I chipped away at the challenge for a weekend. I was like, well, even if I don't get the internship, at least I had fun for a weekend. And I think that's the attitude that gets you into comma. I did well enough to get an internship, which is a great start for my time at comma. Made some great road trips in the US with my comma devices. It's really fun. We spent some days in the field as well. This time we're testing AB. We're making sure that all the forwarding of the AB still worked. So we went out with Ricardo and Adeeb, and we printed out this VW Golf, stuck some aluminum foil to the back, taped it to some boxes, and then we rented this piece of empty track, and then we just tried to drive into it. It was this game of chicken with the boxes, and as you can see in the bottom right, it didn't always go successfully. I also learned how to hack cars at comma. So this is the time I guess we wanted to show that FlexRay wasn't so insurmountable as people thought. So the plan was to rent an Audi A4. So Rob and I went up to LA to pick up the A4. And the person who rented this to us really, he said it had all the driver assistance features we needed, but it didn't. So we had to give it back immediately. And then we went to a McDonald's and we started looking for other Audis with FlexRay. But the only thing we could find with the driver assistance features was this absurd Q8. So we picked it up in Compton. And then we went back to San Diego for the hackathon. And we immediately filled it with wire, started hacking away. And then after 2 very long days, we finally got it to steer. So it was very nice to see that was possible. I also showed how absurd the use of FlexRay is in these cars. I don't know, some manager probably decided that they needed FlexRay, so they put in this whole FlexRay stuff, and then they sent the same exact CAN messages as on any VW Golf, but then they sent it on this super expensive bus. So not sure why they did this. This is the comma.ai. This was back in San Francisco. We decided we wanted to do RTK GPS, where this is where you build like a base station and you can do very accurate GPS. It was a complete waste of time, but we had a lot of fun building the comma.ai. So I guess it's the predecessor of the Comma 3. So we put this big GPS antenna on the roof, got some 2x4s, attached it to the outside of the house, and I had some cables running through the bathroom. So sometimes when you're taking a shower, like the floor got wet and then the GPS antenna went down. So I guess that's the startup vibe. I want to talk about some announcements. I think a lot of it's already spoiled by George with the navigation. We're going to start with Connect. So we used to have Explorer and the mobile app Connect, but yeah, we decided it was not worth it to deal with Apple and the App Store anymore. So we decided to just all integrate this into this super nice web app, which is now live at connect.comma.ai. It has all the features that the phone app used to have and way more. So yeah, it's really cool. You can see your battery voltage, you can take snapshots. And with the Comma 3, you can see your live location. And previously, it would just show the position of the last drive you took. But now, if your car would get towed, you could actually see the car in real time. And we have now this nice unified experience between desktop and mobile. So yeah, no longer in the App Store. It's a nice progressive web app which you can add to your home screen, and it will always be up to date. And this change to Connect was also very important for the next feature, for navigation, because we needed a good way for users to enter their destination, to manage their favorites, and like typing a destination on the device is not really a nice user experience. So yeah, so we have Connect, and then we have navigation on the device, which is just turn-by-turn navigation, but then integrated into the openpilot experience. So you can go to Connect, you type in a location. So if you want to go to a Taco Bell, that's very nice reverse geocoding. We'll show you all the Taco Bells in the area. And you can add favorites, you can add home and work locations, which will then show up on your device like this. So if you're just starting up your device, you can click home and it will just go there. You can also use the Connect to set up a destination. So you type in your destination, it will preview the route, and then when you click navigate, it will actually go through Athena. So all the devices on the Comma network have a WebSocket connection open to our server, and then if you're subscribed to Prime, you can use this to send the location over to your device, and this is really smooth. Like within a second, the map pops open with your route loaded. It's a really smooth experience. This is all based on mostly Mapbox and other open source stuff. So the routing is, I think it's basically based on Valhalla. And then we use the Mapbox driving API, which is built on Valhalla with some traffic information sprinkled on top. A lot of Mapbox users send their real-time location to Mapbox, so they have all this real-time traffic information, which is really nice for us to use. And then we render that on top of some very sharp vector tiles, and they have like this nice OpenGL library to render these, so it's very smooth, and yeah, looks really nice. So you just get this turn-by-turn navigation. You even get lane info if that's available. So in this case, we'll tell you to be in the leftmost lane, and it will also tell you the traffic, so we know how long a route normally takes, and if it takes longer than that, we can see for each segment. If that's the case, and we can show that as well. But then the big question, of course, is what the future will look like. So it's important that you have Comma Prime. This pays for all the tiles and all the routing requests we do, and pays for all the infrastructure. So yeah, sign up when you get your Comma 3. Just sign up for the trial immediately and enjoy this for a couple months. And see it, experience the navigation experience. And then the question is like, how are we going to build this out to navigate on openpilot? So Harald already talked about Desire, which is this way to signal to the model that you want to make a lane change or keep left and keep right. And of course, this is going to be the first step to see if navigation tells you to keep left, what will happen if we tell the model to do that. But then we're also going to this is why it's very important that navigation is an on-device experience. We can render a nice view of the map and the routes that's specifically meant for the model. and the model can take that in as like a fourth camera, and then actually can make decisions based on that. And I think if we all put that together, train this with all the data that's coming back from the comma 3s, I think this is gonna feel like a magical experience. So yeah, that was my presentation. I hope you guys all saw what the nav looks like in its current state. And I think once you try it out for the first time, it really feels like a magical experience. And I think I've also shown how far we've come with openpilot, how we've come from version 0.1 to version 0.87. And I think this just shows how much more is possible and how good openpilot is going to be in the future. So yeah, that was my talk.
No Q&A?
All right. Do you want to put the timer up? Yeah. All right, guys, it is my absolute pleasure to welcome Adeeb to the stage next. He works on openpilot endlessly every night when I leave. I don't think I've ever, Adeeb, I've never left after you in the office, ever. He's an unbelievable machine. And you know, when we were planning the event, we were talking about, you know, the developer community and what we could do for the community. And I just want everyone to know that at every team dinner and lunch, Adeeb is talking about, is literally a ticker of all the information going on GitHub. And he stands up for the community, and he has some really exciting announcements about pricing, products. You can thank him afterwards. Come on up.
Which clicker is it? Alex, this one?
Yep.
Okay. This one?
Backwards. Laser.
This is confusing. All right. So I'm Adeeb. I work on openpilot, and I'm going to talk about mostly testing, but as Alex said, there's going to be a couple of fun announcements at the end. So we're going to talk about quality and how we don't break stuff, because openpilot's getting to be a big project, and we support 2 hardware platforms now with 2 different operating systems, one based on Android and one based on Ubuntu. We do roughly monthly releases that are fairly large. This one in particular was a recent one that was pretty large. This one. So these are a couple of releases that we did recently. They're pretty big. We have a small team. We support 132 cars as of today, various brands. And we have over 200 plus contributors in the last, well, since last January, since we changed the development style, and we develop publicly now. So how do we not break stuff? This is a commit from 2016, and we had a dream back then. One day we'll have CI. And then here we are, July 2021. So these are some randomly sampled desks at the office. And you'll notice there are no common devices on these desks. They're just computers. They're Ubuntu workstations. And this is largely our development workflow now. We sit at desks, not in cars anymore. And the answer to how we don't break stuff is we have automated regression testing and unit testing. We do hardware in the loop tests. We do offline checks for anomaly detection, and we do online checks on the device. So the testing goals for openpilot are enforcing quality, reducing the time spent in cars, as we showed with that picture on the desks, and efficiently scaling a small team. Because the openpilot team is about 3 full-time people with a research team that is now 4 full-time people. And we have a very concrete goal of 1,000 hours mean time between failure for 1.0. So some of the automated checks we do, these are the public ones at least. We have a GitHub Actions test suite that runs unit tests, this test process replay that's fairly important, and we do these car unit tests that are also pretty important. Then we have a Jenkins server that runs our hardware in the loop tests, where we have comma 3s and comma 2s going on road, running real segments, doing replays, and enforcing things like, are the timings as good as we want? Is the CPU usage exactly as we expect it to be? Things like that. And then you guys have probably seen the online checks if you've used openpilot. Sometimes you'll get a fan malfunction. Sometimes you get a GPS malfunction. It'll say contact support, and then what do people do? They go to Discord. But when the alert works, you should contact support. And we try really hard to make these alerts and be very aggressive about it, but also prevent the stuff from going out in the field. But yeah, we do some pretty extensive checking across all the different services in openpilot. We make sure that all the services are live, they're healthy, and their sources for data are also healthy. So if like one of the sensors is bad, for example, this will propagate all the way through location D, through the planner, and controls will say, okay, we can't engage now, or we have to disengage now. And then this is one of our more important tests that runs in GitHub Actions. It's called process replay. And we can deterministically replay segments through routes, or through processes. And we can take the same set of inputs and assure that we get the same set of outputs. And if we don't, we generate these nice diffs, as you can see here. So this is a diff for one of, for actually the new model that we just tried to ship in 087, but we had to revert, which will hopefully ship soon. But this is the diff that it generated. We switched to some different lead packets and stuff. So you'll notice the difference here. It tells you exactly what changed. And we can know, given 2 different commits, what will the outputs of this particular openpilot service be? Did they change in the ways that we expected, or did they not change? So a lot of times we'll do a refactor where we expect that nothing changes. And this is pretty important because we can do things like we can review PRs really quickly. You read the diff, you make sure the diff is reasonable, you do your diligence there. But if the green check mark is there on GitHub Actions, you can be reasonably certain that this did not change any behavior of the tested openpilot processes. And this runs on all the driving processes. So there's 6 critical driving processes, and this covers all of them, and some other ones. Then we do some car unit tests. And these car tests are super important for scaling to these 132 cars that we haven't really touched. So we have 6 cars at the office right now. We've probably touched somewhere in the neighborhood of a few dozen cars over the lifetime of the company. But all the other ones come through pull requests. Pull requests that are fairly small, but it's still important to make sure that these cars work because we sell devices, we want to ensure quality, and there's really no reason not to. We invested quite a bit of time in making these very reliable unit tests, and now we can be reasonably certain that every car that openpilot has a test route for functions to some degree. We don't necessarily check driving behavior, but we check system behavior. Will this car throw a canner? Will the frequency checks work on this car? Will Panda Safety agree with openpilot? Because if this isn't true, as you heard in Robbe's talk, the Panda will just block the messages. So this asserts some very basic behavior and allows us to effortlessly scale to the next milestone in cars, which maybe is 250, 1,000 cars. And then this is part of our suite of offline anomaly detection. So we have a pipeline stage called Find Interesting that runs on all the incoming data. And this runs on those Q logs that anybody who runs openpilot uploads. And these are some tiny logs that we get a lot of information about all the devices in the field. we can, so this is like a real screenshot from our dashboards that we have up in the middle of the office. So you can see right now, some of the top errors are with, there's some Panda stuff, there's some camera D stuff on the comma 2, there's a little bit of poor model timings on release, and we have this cool iteration loop we do with Find Interesting where we aggressively log everything that we expect to happen with openpilot, and then we look at it and Find Interesting, and we look at the data that comes in, and if this isn't happening, it's going to show up and Find Interesting, and it's going to be one of these top things. Oops. Clickers are hard. Oh, yeah, there we go. So you see that these Panda errors are dominating right now. A year ago, it used to be overheats, CAN errors, all these other things. But every release, we look at the top few things, and we fix them. And then you just end up with a way more reliable system when you're tracking the things that you care about. Because if we don't track these things, they're going to regress. And this is our testing closet. You may have heard about it. It's a little bit of a strange name. But the name comes from the closet it was originally housed in the original comma house. And you can see some comma 3s here running different branches. You can see some comma 2s. These comma 2s are running a NeoS update that was supposed to ship in a previous release, but that didn't make the cut because of some things we found and Find Interesting that I'll show you in the next slide. But this is how we verify something like the long tail reliability, in that there's no reason openpilot shouldn't just run if we connect it to what we call a jungle. And this allows us to essentially emulate the behavior of being in a car and driving around. There's no reason it shouldn't run for days and weeks and months. And these comma 2s here have been running for a little over 4 weeks so far. This was with, obviously, a version of openpilot from about a month ago. But we update these devices fairly often, and we're able to be reasonably confident about the reliability and behavior of these devices and openpilot because of the data we get back from the testing closet. Here's some plots from the testing closet. These are diffs of consecutive messages from different openpilot servers. So we have calibration D's message, we have one from demodeling model D, we have one from the planner, and we have one from demodeling model D. So these are 4 different openpilot processes that we're looking at messages from. And we can see that the timings are, they're pretty good for the planner. They're a little bit worse for demodeling model D. And then you'll see demodeling D and demodeling model D follow because they're driven by each other. But we can assert some timings, as we can see in the next slide. So this is the timings of board D. So board D is a process that talks to the Panda in your car. So that's, you have, if you remember from Robbe's talk, you have your comma device with a comma 2 or a 3 now, and you have the Panda, which is built into the device, but nevertheless, it's a distinct device. And we talk to it over USB on both devices right now. And this timing is super important because it drives the rest of the stack. The camera and the Panda drive the stack, essentially. And that's why camera D and board D are super important for latency and real-time performance. So if board D is performing poorly, the rest of the processes that rely on board D are going to perform poorly. So it just controls which is what actually talks to your car. So we worked really hard to get these timings to the point where it doesn't miss a cycle anymore. And then this is why we didn't ship that NeoS update a couple releases ago. There's still a PR open for NeoS 18. About a year ago, we wrote this daemon that fixes these random CAN errors where you would get lags on comma 2s randomly, where it would seem that board D just wouldn't run for dozens of milliseconds, and then you get these lags because of our strict online checks. So you can see out in the long tail here, you have it lagging for almost 100 milliseconds. And it does this quite a few times. And if we go back to the previous slide, it never does this. So This is some of the behavior we assert in the testing closet. So it's pretty important for assuring that we don't ship regressions and that we're hitting the targets that we aim to. And this is pretty cool. So all of the GitHub action tests that we run on our repo, you can run on your repo too. We've put the effort in to the point where you can click the fork button, and then you click allow actions, and you will have a large portion of our testing infrastructure running on your fork. There's many popular fork maintainers out there who have sometimes hundreds of users. And you have all this testing infrastructure that we've built up. You can, if you support cars that we're never going to support, for example, the Mazdas that have the steering lockout, we don't intend to support these cars, or at least claim that they're an open-pilot experience. But you can reach as much as you can. Like, you can support the car to almost the full extent that we can by using the test infrastructure that we have. And it's really, you click this one button, you go into the settings for your forked repo, and you enable GitHub Actions. Now we're going to talk about Panda testing. So we have two goals for Panda. It should enforce the functional safety that we've defined for openpilot, and it should enforce the hardware functionality. So, you tell the Panda to send this canned message, it just sent the canned message. So here's an overview of the testing infrastructure for Panda. We do unit tests, again, in GitHub Actions. We do replay tests, where we take a segment, and it's very similar to process replay, where we assert that the behavior hasn't changed from commit to commit. And then we do some static analysis. Robbe talked a little bit about MISRA, I think, in his Q&A, and ISO 262. So our unit tests and our static analysis go a long way to cover the code rigor that we uphold in Panda. That isn't necessarily a goal of openpilot. And then we have hardware and loop tests that run on the whole zoo. So they run on every Panda that we've ever made, from white, gray, black, uno, dos. So our safety unit tests are pretty cool because you can write all the functional safety you need for a brand new carport, and you can write a test for it. And on average, the test is about 165 lines, which is something you can reasonably do in an afternoon or a weekend. And you can develop functional safety for your brand new carport and verify functionality without ever going in a car or even doing a replay. So I think this is incredibly cool. And we have tests for all these cars, all these safety modes that ship an openpilot release. And this runs for every hardware combination of every car we support. So we support 132 cars. We support quite a few Pandas. That's a lot of combinations. And then we do hardware in the loop tests. We assert things like can latency, can loopback. This essentially maintains that if I send out a message, do I get it back? And we can do this with multiple Pandas. We use something I'll talk about a little bit later, the Panda Jungle. We also do some checks with the car harness, that we're correctly detecting ignition, all this other kind of stuff. And then I want to talk a little bit about production, building devices, because this is also pretty cool. George talked a little bit about screen calibration. This is some of the stuff we've just gotten to do because we've gotten really good at testing these devices that we can do the fun stuff. We'll go back. So after your comma device is built, what happens? So we flash it with NeoS or Agnos, depending on whether you have a comma 2 or 3. We do some initial checks to filter out defective units. And then we have this provisioning stage, which runs quite a few tests and asserts all the hardware functionality that we design our comma devices for. And then we have a 24-hour stress test that George talked a little bit about in his presentation. And this is how we're working towards building these really incredible devices that I think you guys will get, hopefully, after the first shipment on Thursday. So this is our provisioning stage. So this is what happens after flashing, and we do that initial check. We make sure there's nothing obviously wrong, like does it have all the sensors or is it missing the modem? After it passes those basic checks, it goes on to final provisioning. And these are some very early comma 3s. And we started writing these tests fairly early on. We wrote these tests a couple months ago, and we've really iterated on them in the last couple of weeks. But These are some old revisions of the comma 3, and they, you can see some of them failed, some of them are still running the test, and some of them passed, but it's cut off. And we verify things like sensors. Is Wi-Fi working? Is LTE working? Are all the things the right firmware versions that we expect? Is the camera in focus? This is becoming more important with the comma 3 because we focus the cameras ourselves. We have a lot of control over the process, but this means there's a lot more that can go wrong. So testing becomes a little bit more important in some aspects of the comma 3. Then we also do some testing with the Panda, the internal Panda, so the Uno and Dos in your comma 2s and 3s. And we can basically be confident about all the hardware that we're shipping out just based off this quick test. This test runs in a couple minutes, and it asserts all the instantaneous functionality we can check. We do some, there's in the daughter board that George talked about in his presentation that goes on top of that modem on the comma 3. There's a beeper, and that fires when device powers off, essentially, while it's still engaged. And we do tests like that. You hear these all throughout the office. We go through a lot to test these devices. We have some really cool tests with that. And then it also does the server registration. Then we do the stress test. So this one's pretty cool because we have all sorts of different failures we caught on the stress test. We check for temperature. This one used to be super important in the comma 2 because the device would fail a lot. We check for GPS accuracy now. We do a lot of camera checks, like are we dropping frames? Are we getting any errors from the camera at all? This indicates some kind of assembly defect where a screw isn't screwed in all the way, stuff like this. And we have these very strict checks. And it runs for continuous 24 hours. No, like, if it happens 2 times, we'll let it pass. These are super strict tests. It turns red when it fails. It's alarming. We pull it off the rig, and it goes back in the production process. And then this is a pretty cool chart. So we ship the comma 2s with some testing that we could think of beforehand, but there was a lot of unexpected failures with them, and a lot of the tests were written after things happened in the field, and then we found out that this is something we really need to test for. This is something that varies quite a bit from device to device as we still establish these production processes. So this kind of shows how we improve these devices over time and how every device that has been shipped also benefits from the improvements from the devices that we make in the future. So we used to set aside all the comma 2s that failed. This is our first serious time doing production, so we'd do the tests, and if it failed, either final provisioning or the stress test, we put it to the side, and it goes in a bin, and we just have walls and walls of particular failures, ranging from very minor things like we need to fix up some solder joints or something, to the CPU's too hot. This is some kind of device failure, or we need to do something more major to fix this. So CPU too hot around, I think, September, October of last year was by far the biggest and most common failure for the comma 2s. So we reduced CPU usage in openpilot, and then we downclocked the CPU fairly significantly to get these devices to pass the stress test. And we went a little bit above and beyond here. We did a more extreme downclock, and the orange part of the histogram here is the devices that were too hot and failed the stress test after the downclock. And the blue ones are all the devices we shipped before that with the current clock frequency. So the devices that were too hot actually ended up being running even cooler than devices we shipped out before that passed the test. And then every device in that blue category also benefited from this because we shipped an OTA update to the kernel, and all the devices got cooler in the field. And then this is pretty cool. Here's a GIF of the screen calibration. So we've thought about comma 3 testing for a long time and how we're going to test them in production. And we got to do some fun stuff. before we shipped out the first units. So I think this kind of shows how far we've come from the Comma 2 a couple of years ago to where we are at with the 3 right now, where we can do things like this, and you look at them, and the stress test is, let me go back to stress test. The stress test is pretty big. This is a small part of it. And you can see all these devices on the stress test, and their screens look exactly the same. This is, we put a Comma 2 next to the Comma 3s yesterday. And the difference is incredible. These devices are really beautiful, and we have time to do things like this now in the capacity. So I think you guys will be really happy with these devices. And then now we're going to take a trip to the Comma Zoo. Well, to the premier San Diego Zoo, which is the Comma Zoo. And we're going to talk about the Panda Jungle. So the Panda Jungle is what most of us who have a device on our desk use to do replays and to debug and develop openpilot. So Panda Jungle essentially has a Panda on it, and it has 6 OBDC ports. So you can plug in 6 Comma 2, 6 Comma 3, 6 Pandas, whatever you want. And this is how we do our hardware-in-the-loop testing for Pandas. This is how we develop openpilot on desks. You can essentially emulate being in a car on your desk. And it's an incredible debugging tool. And then now it has a working ignition button. We shipped 9 of these devices in the last, well, since we started selling them. We shipped 9 of them. And we just got the ignition button working. But we have an announcement. It's going to be $199 now. All right. So hopefully we'll get another 9 people to buy them. And we have the next-gen Panda, red Panda. So the red Panda is based on an STM32H7. The previous generation of Panda was based on the STM32F4. We've been doing work in the last 3 months to develop this device and bring it up. It's the future of the Panda platform. It supports CAN-FD, has a 4x faster CPU, and it's red. So it's the same Black Panda form factor in a red case without GPS. You'll be able to connect this to your Comma 3 directly into that USB-C port. And then you can buy one today, $299, and it ships in 2 to 8 weeks. And we're optimistic we'll have support in openpilot in the next release, 088. All right. Questions?
Hi, my question is about testing.
Yeah.
So you did a great job describing the system level post-production tests with the test closet. It sounds like when you have failures, the device is going through a rework process, and that's expensive not only from a time standpoint, but others as well. I imagine you'll be selling hundreds of thousands of these devices. Can you talk about the testing that goes on during production so that reworks don't need to happen to increase your yield?
Okay, so there's a couple things there. We're not quite at the scale of selling hundreds of thousands. Yeah. Yeah, maybe. But as far as reworking the devices, it costs a lot of time. But it's really clear now that this time is really worth spending. It made every Comma 2 we ever shipped out much more reliable and a much better product. So I think right now the time we invested in, and we do this kind of in stages. So we do the production process, we build devices, we set them aside, and then it's kind of like the find interesting loop. We look at the top failures, we fix them, or we evaluate what can we do about these. Can we improve processes? Can we improve the software at all? Like, where can we do better? And it turned out for the Comma 2, we fixed all the common failures, and this made all the devices that much better. You buy a Comma 2 today, and it's incredibly well tested. So yeah, it is worth spending the time, but we do it in stages. We don't just immediately rework them. Was there another component to your question? I think I covered everything.
I guess since you
How can we catch them earlier?
Were the tests upstream during production, that would just reverse redeem that, like catching the module level failure before it gets assembled into the device, and then the stress test is the area that it's caught.
Yeah. So we try to push tests downstream as much as possible into the earliest stages, and we've gotten really good at this with the comma 3s already, actually. We catch almost all the failures in final provisioning, which takes a couple minutes. You build the device, you flash it. There's a couple stages of flashing, actually. So we flash just the boards themselves, then we build it into a device, then we put Agnos on it, and then we do some final provisioning. And we've gotten really good at this, actually. So we add these tests when necessary, and yeah, the final provisioning tests are really quick. We catch these super early in the production process, actually.
We have another one up here, actually.
Oh, yes, thanks. Thanks again. Nice presentation, nice work on testing. One question I have for you guys, maybe like for improvement. Are you guys planning on doing like some thermal cycling of the devices?
Some thermal what?
Cycling, like freezing them basically like to -10 at -20 and then heating them up pretty quickly, because that's what really happens in practice. And my device actually had a problem, comma 2. After Whistler trip, when it stayed outside and cooled down to -10, screen just stopped working.
Okay. So I think your question about thermals, I couldn't quite understand.
Yeah,
the
like
last part of
thermal testing. Like, do you guys plan on doing like thermal cycling?
Yeah.
Of new
So
devices?
I think we plan to we cover all the hardware right now pretty thoroughly, but there's a lot of room. There's a lot of depth to go into in the testing. Our testing will get much better. We'll go through the same process we did with the comma 2. The comma 3 testing is where the comma 2 testing it kind of picked up from there. We didn't start over. So I think the comma 3 testing will be really, I think it's quite incredible right now. I think it's going to get, you saw the screen calibration.
Yeah.
This is.
But then what I'm saying is that comma is not really, it's a little bit different from consumer electronics, because its operating condition can go from -10, for example, Celsius to, I don't know, 80 degrees pretty quickly.
Yeah.
So that's not your PlayStation like use case scenario usually.
Yeah. Yeah.
So, yeah. Just something for improve. Thanks.
So with the Red Panda,
yeah.
in the new car or in the comma car configurator, when you're trying to see if your car is supported, if you need a Red Panda to support your car, is that going to show up in the configurator?
Yeah, so this is something we could easily do. No cars require the Red Panda right now, but I think some cars are starting to ship, like some Genesis cars are starting to ship with CanFD. When the first CanFD carport comes in, we'll handle this all nicely.
Gotcha. And can you maybe speak to what's on CanFD and why it's important to have that support in the Red Panda?
Yeah, so it's just an upcoming standard. It's kind of the next step in CAN. The FD stands for flexible data rate. You can get more data through faster. So this is what the cars are going to be shipping with. We want to support it. It's also just changing one chip. So this is pretty cool.
We have one up here again.
I'm trying another question on the Red Panda. Since there's a Panda in the C2 or the C3 already, how does that work? Do you bypass one? Do you switch one off? How does?
So you won't be able to use it with the comma 2, unfortunately. This is a hardware limitation, the comma 2. It's the same reason you can't use a comma smaze on a comma 2.
Okay.
So I guess if you have an Eon, you can use the Red Panda, but an Eon Gold.
So
but it'll use the USB-C port on the comma 3.
Oh, the spare one. Okay. Okay.
Yeah,
Cool.
we have one of our cars. We have a Red Panda in one of our cars driving with the comma 3.
Okay. Cool. Thank you.
So one of the things you listed was MISRA C2012. Is that being applied to the Panda and also the openpilot?
No, so openpilot is considered QM in terms of our functional safety analysis. Panda is where that kind of code rigor happens, and this is where we designate the safety being enforced.
Okay, and are you applying anything like then CERT at all to the for security, another coding standard? Considering making sure that the code is written a certain way so there's no vulnerabilities or anything like that. MISRA does that in some sense, but wondering if there was any other standards that you're applying.
MISRA, you mean as far as coding standards,
Yes,
or as functional safety? Okay.
Coding standards.
So we, on the C code, we just run some generic static analysis tools like CPP check. So we use CPP check, we use some of their static analysis stuff, and then they have a MISRA add-on. And then we keep up to date with their MISRA add-on. We even, we fix a couple bugs in there. So we pretty actively work towards MISRA C 2012.
And for functional safety standards, are you then applying like ISO 26262 process standards for?
Yeah, so you can see, it's pretty cool. If you go to Panda, you'll see we have two projects. We have an ISO 262 project and we have a SIL 2 project from when we did in-depth functional safety analysis. And we made a bunch of issues, and then you can see the progress. All the ISO 262 stuff is almost done. All the cars that we officially support have full ISO 262 in Panda.
And you self-certify as well the code or for safety standards, like?
Yeah, there's no certifying body.
There's no, okay.
You said something about declocking one of the chips to reduce the heat.
Yeah.
In Comma 2. Are all the Comma 2s that are out right now with the declocked?
Yep.
Okay, thanks.
Yep, and running at about 55, 60% overall CPU. So this is well below our target for 09, openpilot 09.
Thanks for the presentation. So the one question I have is, what will be the operating temperature for the Comma 3? Will it have the same limitations that the Comma 2 has, as far as maximum temperature that it can be run at?
So the active cooling in the Comma 3 is quite a bit better. The thermal thresholds may be a little bit stricter because from what we've seen on our stress test, thermals are significantly better. We see about max temperature of 65 C. You'll never see a Comma 2 with 65 C, and this is the max for the Comma 3. We might be a little bit more strict, but it's because we have more room to be strict, and you'll see the active cooling is quite good in the Comma 3.
Hey, how's it going? I'm curious what yield you guys tend to get on the production units, and when production units fail quality control, what tends to be the sort of common culprits?
Yeah, so like I said, we do it in stages. So we kind of establish processes, we write tests, and then production comes back after some period of time, a couple months or so, and they're like, okay, here's what failed a lot. We have a lot of logging around this. That's why we're able to make these cool histograms and stuff, comparing like all the Comma 2s we shipped up until now, and then compare with the down clock. So some of the common ones we saw with the Comma 2 were like CPU too hot. Some of them don't have an IMEI. So we're able to filter out a lot of the raw eco phones. There was tons of failures in those. That's like kind of a cost we just had to eat. So we do a lot of filtering at every level, and each kind of stage had its own common failures. Stress test was CPU too hot mostly. Final provisioning usually catches things like, oh, this device doesn't have a microphone, stuff like that.
All right, Adeeb. Thank you so much. That was great. So we started with Robbe. He told you about how we control the cars, and Harald talked about our research. George announced our new hardware. Adeeb talked a little bit more about openpilot and testing, and now I'm very excited to bring Greg to the stage. Greg is our head of infrastructure. You are gonna, I mean, unbelievable. You're gonna see inside our servers, how we build things, how we store the drives. I'm very excited. There's a lot of questions that come in, and I feel like today, Greg is gonna answer them. Please welcome to the stage, Greg.
on. Oh, it is on. Can you guys hear me? How loud should I talk? Louder? Okay. Tell me if I'm making you go deaf. All right, so I am Greg Hogan. I work on infrastructure here at Comma. Yeah, let's see if I can figure out this clicker. There we go. All right, let me turn this a little bit. That's better. All right, so who's excited to hear about infrastructure? Wow, I didn't think it'd be very many people. That's good. I guess it's a lot of pressure though now if I feel like people expect a lot or something. All right, anyway, we'll see what happens. So the goal of Comma is to solve self-driving cars. We're going to do it with machine learning, and we're going to need really good infrastructure to be able to accomplish this. We got to be able to iterate fast. We got to be able to train models, with reasonable speed, and so forth. So at Comma, we call everything supporting our customer-facing applications and model training infrastructure. So that's hardware and software. We call it all infrastructure. So what do we need? Well, one thing we're going to need is data. And so luckily, we have thousands of users every day collecting data for us. And somehow we need to get this data to train models. So we have devices out in the field that have this data. And they upload it to a storage account in Azure. That data, when it comes in, we throw it into a queue. And then it goes into, it gets picked up from, things get picked up from that queue from virtual machines that run in an auto-scaling group. And then we do some processing on it and decide what's good for, what data do we have, where are we getting that's good for training, and we save some metadata about it off. So we want to minimize the cost of processing this data. We get a lot of data, and we don't want to spend a fortune processing it. So what do? Well, these cloud storage providers, pretty much all of them now, have this great feature where they have all this spare capacity, and no one's using it. So they have something called spot instances or low priority VMs. And so you can use their infrastructure that's kind of spare for 20% of the normal cost. So, but what's the downside of this infrastructure that's super cheap? Well, they can pull these VMs back anytime they want. When some other customer says, oh, hey, I would like a VM of that size, well, then they kick you off and they give it to someone else. So how do we manage this? How do we keep our processing costs low and keep our latency low? Because we need to get this data processed so that we can give our users access to it, and we want to do it in a timely manner. So what we do is we spin up multiple sizes of these scale sets with different CPUs, different memory configurations. And the probability of us losing any one of these scale sets, losing all the VMs in one of these scale sets, is independent of the other scale sets that are the same size. So what's the probability of us losing all of them? Well, it's exponential as we add another scale set of a different size and another scale set of a different size. So, so that's why this works, and it works really great. So now that we have all this data, we need to be able to use it for different things, like some different applications that we have. The data isn't public, but the API we use for our applications, we made it public so that people can get their own data. So you can go to api.comma.ai, for example, and you can see the documentation so that you can, if you wanted to, build your own application on top of your data. We also have some nice tools that have been in some of the other presentations. Kibana, for example, it uses that same public API. Connect, or it was previously Explorer, it also uses that same public API, and this gives you, nice dash cam type functionality for reviewing your data. And another nice thing that we offer people is what we call an SSH proxy. So we sell a dev kit, and it would be nice if you could SSH into your device from anywhere if you're doing like development type stuff. But normally, like if your cell phone is on a cell network, mobile data, they block port 22. Because there's actually been problems where like people accidentally leave port 22 open, and then people can get into devices because they did shady like the same username and password for every device or something like that. So how do we get around this? So what we do is the devices, whenever they have an internet connection, they open a WebSocket connection to a server that we have in Azure. And then when you want to connect to your device, what you can do is you can SSH into the hostname ssh.comma.ai from your computer, and your username is your device ID, and you have to present a public key that you had previously already set up on your device. So then what our proxy server here does is it looks at your connection, and it says, oh, you're trying to connect to this device. Let me go ask that device what public keys are allowed to connect to it. It pulls those public keys. It then sees if you can successfully authenticate against the proxy server with that public key. And then if you can, then it lets you tunnel an SSH connection through the proxy server, through the WebSocket, into your device. And then the device it's literally port 22. Like then your device then is going to authenticate again with that same public key. This is like what they call like an SSH jump server. We just tunnel it through a WebSocket so that everything's making incoming connections, and it doesn't matter if you're on a mobile network with your device where port 22 is blocked. So in case anyone's wondering, Comma doesn't have SSH access to anyone's device. SSH is off by default on your device. You have to turn it on. And then you have to set up, what public keys you want to have access to your device. And all the authentication, happens on the device. We can't, the way public key authentication works is, even though the traffic is passing through our proxy server, it's still encrypted with your keys, and so we have no way to be able to look at any of that data. So all of that infrastructure we just talked about, it's hosted in the cloud. And it's hosted there because, the cloud has these great features, and we're willing to pay a premium for high reliability, scalability, and availability. All right, so we got a little sidetracked there. We're talking about, training models, but we needed some good stuff we needed a good pipeline of data coming in, and that's kind of all the stuff that supports that. So let's get back to training models. So what kind of hardware do we want to train models? Do we want to run it in the cloud? Well, the most important thing to us is that we maximize the compute we get per dollar we spend on that infrastructure. And we can tolerate some failures. The cloud is great, because it's so scalable and reliable. But for research, we don't really need all of that. There's a lot of data that we can regenerate if we needed to, and so forth. So what meets these requirements? So it turns out that refurbished equipment running in a garage actually it's really cheap, and it works really well. So if you consider the cost of just the cloud data storage for all the data that we hold for doing model training, the cost of that cloud storage that we would need to have equivalency, we would recoup all of our costs in 10 months buying all the hardware that we've bought. So our return is so good. This here is a DGX SuperPod. This thing's brand new, probably. Looks super clean and nice. So let's see if our servers look like that. Okay. So we started in an office in San Francisco, and at some point, someone bought a rack and put some servers in it. And then that rack turned into 2. And then it turned into 3. And the power wasn't very stable in the house at this point. We had like a lot of voltage swinging going on. When like GPUs would hit really hard, model training, or running the SegNet or something. And so we needed a lot of power conditioners. So you can kind of see here our ratio of, you actually can't see the GPU servers here, but you can see our kind of ratio of power conditioners to actual use of compute. It's kind of high. Another funny story. So we actually, when we were in this house, something kind of weird happened. We had like a water leak at some point, and so they were in the front yard digging up the water line, and all of a sudden, like the 2 phases on the house, one went up to like 300 volts, and the other went down to like 100 volts, and we're like, what in the world is going on? And so all of a sudden it went away, and it kind of correlated to when they buried this water line, this copper water line that was going into the ground again. And so I take a clamp-on amp meter, and I'm going around the house. I'm trying to figure out, what the heck is going on? And I clamp this clamp-on amp meter onto this copper pipe going into the ground. It read 30 amps. 30 amps of power getting dumped into the ground through the copper pipe. So why is this happening? Well, it turns out that on the pole, not even in the house, the pole where the house gets power, the neutral was completely disconnected. Like corrosion had completely electrically disconnected the neutral. So when you have an imbalance in between your 2 phases, where's the difference go? It goes through the neutral back to the transformer. Well, we had no neutral. So what's the next best thing? Well, it might have actually been the copper water pipes, which the ground is clamped to, through the ground to the neighbor's house, which also has the neutral clamped, or the ground clamped onto the copper wire. And in your panels, the neutral and the ground are bonded together in your main panel. So that's why we had 30 amps of power going down into the ground. So that was pretty funny. I don't know how, gosh, I remember just like scratching my head for days, like really frustrated, like what the hell? We got these nice power conditioners and all this weird stuff's going on. But anyway, it's a good story. I'm glad we figured it out. So right now we're running these servers in this garage in the basement, and eventually the garage that the servers are running in, well, the garage doesn't have enough power anymore to power these servers. So we need to find power somewhere else. So what do? Well, there's more circuits in the basement, so we start pulling power from other circuits. But eventually, the bottom floor of the house doesn't have enough power. So, well, kitchens have a lot of circuits, a lot of 20-amp circuits. So you can kind of see here there's a black thing going down from that window to the garage. That's a bundle of really heavy-duty extension cords powering some of our servers in the garage. We also had a bunch of 3D printers in there too, so that didn't help. Those things, the heated beds can obviously draw quite a bit of current too. But so, this can't go on forever. The house wasn't going to have enough power. We really wanted to buy more servers. Like we always want to buy more servers. And so we get a real office. We moved to San Diego. We got a big garage. We got 3-phase power. Everything's great. Well, when you're using 60 kilowatts of power, you're generating a crap ton of heat. And you got to get rid of that heat somehow. So there's a few ways you can do this. The obvious one is if you run a data center, you have like climate control, right? You got HVAC. Well, air conditioning is really expensive if you want to, get rid of 60 kilowatts of heat. So, what do? Well, we're in San Diego. The temperature doesn't swing that much, right? It doesn't get super hot here. So we put in two 10,000 CFM fans. We got an intake fan and an exhaust fan. Put in a partition for separating the hot and cold aisle of the servers. And that worked pretty well. But then we had another problem. So it turns out that we started seeing signs of corrosion, like this fried capacitor. This is a backplane on the server. So there's a lot of dirt here, and we got this capacitor that's fried. So what's going on here? It turns out there's this thing called equilibrium moisture content, or EMC. And it's really important. So it's basically, so equilibrium moisture content is the amount of moisture that a material will hold, and it's neither releasing moisture into the air or sucking moisture out of the air. So there's no such thing as dry or wet. There's a continuous scale. And depending on what the relative humidity and the temperature together are, determines what this equilibrium moisture content is. So you got to manage this, or else all that dirt from this dirty garage, it holds moisture, and that was kind of a problem. So to manage this, basically, you can look around and find numbers. You want to keep it below this 10.5% number. Generally, if you go above that, it's considered corrosion, or it's considered a corrosive environment. If you keep it below, you're in good shape. So how do we stop this corrosion? So it's this scale, right, where as the relative humidity goes up, the temperature goes down, the EMC goes up. So how do we keep the relative humidity down and the temperature up is the question, or how do we keep this number low? And so the obvious solution here is, again, air conditioning, but that's kind of expensive. Do we really want to do that? No, we don't. There's a cheaper solution. So instead of sucking moisture out of the air, instead of lowering the relative humidity by taking moisture out of the air with something like air conditioning, we can just raise the temperature. So when we buy these used servers, they've got metrics, from whoever owned them last. So this here is a picture of, you can see the black and gray on the far left here is what temperature the server was running at before we got it. And then there's a dead zone where it wasn't on because no one owned it, and then the temperature after we start running it. So they ran it around 21 to 23 C. It sounds like a nice life for a server. But then we get it, and it runs 35 C to 42. So our goal is to keep it under 43 C. 43 C is 109.4 degrees Fahrenheit. So we kind of abuse them, but everything in the server can handle this. The lowest temperature, I think, of anything, the lowest operating temperature of anything in the server is probably the spinning drives and the ones that have spinning drives, and that's 55 C. So 43 is not that bad. So we also decided, this is a lot of dirt. Maybe we should try to keep some of the dirt off the servers. So now we put this filter material just right on the front of the servers because, to get a 10,000 CFM fan with a filter on it is 10 grand or something crazy. So that seems stupid. We've got all these servers that got all these fans in them. The only place they take in air is right on the front of them. So we just throw the media filter right on the front of it. We also decided, we want these backplanes to last a while. They're still going to get dirty. And this isn't going to filter out all the dirt. This garage is, pretty dirty. So we put 10 layers of conformal coating on our backplanes, and we use a potting compound to seal up these exposed leads on these drive connectors. This is a picture of a backplane that's been all sealed up so that we don't have this corrosion problem. And this is really only a problem in the front of the server because the temperature needs to be kind of low for the EMC number to be high. So in the back of the server, it's always really hot. But in the front of the server, that's where you're going to have problems. And so, that's kind of what we saw. The backplanes, catch a lot of dirt, and it's the coolest part of the server generally. All right, so what do we have in these racks? We've got 1,888 CPU cores, 72 GPUs, 2 petabytes of spinning drives, and 516 terabytes of solid-state drives. We've got basically 2 classes of servers. We have servers that we use as compute nodes, and we have servers that we use as trainers. So here's what our compute nodes look like. This is a rack of them. Every one of these servers has 10 spinning drives. They're 1U servers. They were new back in like 2015 or 2016. But they work great. We have 3 racks of these. Here's what our trainers look like. They're also old servers. Basically, lots of RAM, lots of GPUs, and lots of network bandwidth. We also buy used networking equipment. So it boggles my mind how cheap you can buy this stuff. This is a 100 port that you're looking at here, this picture, 100 port 100 gigabit 64 port switch. This switch costs us $2,800. That's 6.4 terabit of switching capacity. And I remember at one point I bought a new Netgear 48 port switch for comma. And that Netgear switch was only 10 gigabit, 48 ports. It was almost $4,000. And I can get a 64 port 100 gigabit switch for $2,800. So we have multiple of these. And then we also have an InfiniBand switch for the trainers to get even higher network bandwidth between them. So how do we use this hardware to train models? Well, we've got all this data, and now we need really high bandwidth, high performance file system for the different servers doing the different tasks to pull the data and work with it. So originally we used NFS for a long time, and yeah, that doesn't scale. It's pretty bad. So we looked around at distributed file systems that existed, and everything was way more complicated than what we needed. It's crazy how complicated Ceph is and all these things. So we built this distributed file system called mini key value. It's open source. It's on GitHub. It's less than 1,000 lines of code. It has an HTTP interface, kind of like S3. And one of the reasons it's such a small amount of code is because we use Nginx for the volume servers to serve up the files. So let's take a look at this. This is kind of a picture of kind of like our infrastructure in our garage. And let's see how, for example, you write data into mini key value. So the first thing that happens is the client trying to write a file into mini key value makes a put request to the mini key value master. The mini key value master then takes that, and depending on how many replicas you want, it then makes that many copies across that many machines. So each of these machines we call them volume servers. So there's the master handling the requests initially, and then there's volume servers that hold the data. So these are our machines with 10 spinning disks each, and basically if you have 3 copies of your data, it's going to put a copy on each of the servers. So if you've got 3 copies, then you can lose like 1 or 2 entire machines, and you haven't actually lost any data. So that's what we use for our raw driving data. We use 3 copies, and so that's how you put data into mini key value. The volume servers, again, are Nginx, so basically it's just using HTTP requests passed through to Nginx to write out these copies of the data. So now how do we read data back out of mini key value? Say you want to pull a file and you want to run through the video or something like that. So the first thing that happens is the client, again, makes a GET request. It hits the master. the master then looks at the list of, it maintains an index of the list of volume servers that have the data that you're trying to request. It then picks one randomly, and it returns a 302 redirect to you. So then what does the client do? It just follows that redirect, which hits an Nginx server directly that is hosting the files, and just returns it. And so our master is really simple. Like our master is just a level DB index of all the files on all the servers. The files on the servers are actual physical files, and they have a name that is the hashed key, or the base 64 encoded key. So if our master ever disappeared, if our master ever failed for some reason and we lost our index, we can actually regenerate the data that was in the master very easily just by spinning through all the files, base 64 encoding them, and repopulating that master index. All right, so now that we have a high performance distributed file system, let's run some tasks that are going to generate our ground truth for training models. So the way that this works is a workstation. We have some software libraries custom built that we have that we use for submitting jobs to all of our servers. And basically, it builds up a list of tasks. Each task can run independently in parallel of all the others. And it kind of manages dependencies and gets results and so forth, and submits them as they can be submitted. So then all of these 3 racks of compute nodes that we have, they're all pulling tasks out of consumers. And they then read data from our spinning drive mini key value. We have a mini key value instance that's just spinning drives. They then, to run tasks, they need to read data from, so let's say the raw driving data that we have. And then they write the results back out to the mini key value instance that is solid state drives. So that way, our model trainers have really high IOP, really high bandwidth file system that they can pull the data from for training. So let's see here. I'll go back one. There we go. So our spinning drive array here, it's 40 machines. It has 400 spinning drives spread across 40 servers. And so that's our 2 petabytes of storage that we have, which is about 10 million minutes of driving data. And then our mini key value solid state drive, or mini key value that's all solid state drives, is 20 machines, and that's our 516 terabytes of SSD. All right, so now we've got our ground truth generated. Let's train a model. So how does that work? So we have 10 servers here that are model trainers. We can run a lot. We have 10 of them, so we can run a lot of experiments in parallel. Each of these model trainers has a 100 gigabit Ethernet network connection to one of those 100 gigabit switches. And then one of our racks has another 400 gigabit per server hooked into an InfiniBand switch, so we can do things like RDMA and do parallel training and so forth. Let's see, I went too far. Okay, so when we kick off model training, it's something that's running on one of the GPU servers. This is our mini key value SSD instance. It pulls data from there. Each of those machines has 20 gigabit of network connectivity, so it's a really high bandwidth. And then each epoch, it generates some metadata, and it writes it out to what we call our reporter server, which I'll talk about in a minute. So you repeat this about 1,000 times. and then we've trained a model. So this is our reporter server. This is what it looks like. One of the screens in our reporter server. It's kind of like TensorBoard. It has a lot of charts and images. It's pretty simple, something we custom built just to hold all of our experiments. We looked around kind of at like the other options that were open source and available and free, and they didn't really have all the features we wanted. So that's why we ended up building something custom. And it really wasn't like, this wasn't a big project at all. Another screenshot from our model reporter. This is example of like where you can pull up worst losses for an epoch. And so that's pretty much all the infrastructure that we have that we use for training our models. So our user base grows like 50% every 6 months, at least on average. We need to scale up a lot of our infrastructure as it doesn't take us too long to grow another 10x at that rate. So we've got a lot of work to do. There's always ongoing work to really scale things up. We want to build a 10x larger data center. So we've got all kinds of exciting things we would love to do to train on maybe 10 million segments of driving data, and running the ground truth for that takes a long time. Would take a long time on our current setup. Let's see. So yeah, if you I don't know, you think this stuff is exciting to you? You think that's cool stuff? We're hiring, and so it looks like I'm pretty much out of time here, but yeah, I'll be around, and find me if you have any questions. Oh, hang on. If we have... Oh, I thought I was going to be really cool and I didn't get any questions. Like does Steve Jobs take questions after he talks? I don't think he does he?
Okay. Hi, I'm in the back on the first floor. Hello.
I can't see anyone. What's up? Oh, hey. Go ahead.
Thank you for the mini key value presentation. It was very interesting. Okay, maybe there's not a good answer to this, but how did that not exist? There must be other companies trying to build their own training pipelines and their own data centers on, right?
Yeah, I mean it's pretty the functionality is pretty limited, right? A lot of people want super high availability and more a lot kind of better assurances than what we have. We've got mini key value has this kind of bottleneck for writing data, which is the master. I've got ideas how we can improve that. We've got some pretty specific. How do I say this? We don't need a lot of these crazy features that these other distributed file systems have. So, for example, our data, our mini key value instance that has 3 copies of the data. This master is a bottleneck. All the writing goes through the master right now. It manages getting 3 copies out to 3 of the volume servers. So that can obviously be a bottleneck, right? So other distributed file systems are oh, well, that's never going to work, right? But for us, it actually does, because the amount of data we take in, if we could generate, we have 1,000 users. If we could generate 10 times as much data today, would that actually be good data for us? The answer is no, unless we have 10x more users too. We need diversity in our data. So our data comes in slowly, and we don't need a ton of bandwidth to this mini key value instance that has a bunch of redundancy. But on the other hand, we do need really high write performance for our mini key value solid state instance, right? Because that's where our reporters read data and write. Well, we need to be able to like massively write out our ground truth from all of our consumers. And so there's a solution to this because there's a good solution to this because we don't need multiple copies of that data. We only need one copy. Because if we ever lose a drive, that's like a small portion of our data, number one. Like, we don't really care. But number two, if we did care, we can just rerun the ground truth and regenerate it. If we have a disk fail, like who cares? We'll replace it and we'll rerun the ground truth for that. So what we can do is we can actually use redirects to write data. If all the master is doing redirects, like it's we don't have any performance problems. So when you only have one copy of your data, like our mini key value SSD instance, your writing can be redirects too. You don't have to funnel all your data through the master. We could also do like crazy stuff like have the client write out multiple copies, but like again, like when you're really focused, when you understand your own problem well and you're really focused, you can come up sometimes with really simple solutions to those things.
Thank you. That gives me a lot of insight.
Yeah, no problem.
You mentioned that humidity is a problem. In San Diego, it's about 60% on average. Would it be beneficial to move the compute cluster to somewhere like 29 Palms where the humidity is half?
I don't know. Like, why do I care if I run my servers at 43C? Do servers have, I don't know, is anyone like advocating for server rights? Like, do they get, like, is there what is it, like, child, whatever, like children can't work in like hot conditions. We're gonna have that for servers someday too. Yeah, I don't know. Yeah, I mean, we wouldn't have had this problem. That'd be nice, but it's kind of like, it doesn't really matter.
What's been your largest challenge in terms of growth and scalability of this hybrid cloud environment? And then also, second question is, why did you decide Azure when there's more mature cloud environments out there like AWS?
Oh, okay. Yeah. Okay, I got answers for those things. So the biggest challenge, I think, in scaling any of this stuff is like finding simple ways to do it that doesn't require us to hire like a team of people to manage it, right? Like why do we care that mini key value is under 1,000 lines of code? We care because like George wrote it. I can sit down and look at it and like fix bugs in sometimes a matter of minutes, and I can read the whole code base in like an hour, right, and understand everything that's going on. And so finding good solutions to these problems is less code is always better, and I think a good example is we used to spend a lot of money transcoding video, processing video files as they were uploaded to us. And we were doing this, and I'm always trying to figure out how do we lower our cloud spending. And I'm like, well, this is obvious. Like, it should happen on the device. Why are we transcoding in the cloud? So that's what we did. We didn't like build some crazy stuff to like do caching and be smart about, oh, someone requested the first video of this file, let's start transcoding it, and then the second and the third and the fourth 1 minute segment, You could go really complicated and build something that probably works really well, but, finding a simple, that's like writing a lot more software and scaling that thing sounds like a nightmare, and, it's still probably kind of crappy. So, that's the real challenge, I think, finding a way to do it really cost effective. Second question you asked. So why are we in Azure? So we weren't always in Azure. I don't think I've ever really told anyone this story. So before I started at Comma, everything was in AWS. And why were we in AWS? Well, the reason we were in AWS was because if you run a startup, these cloud providers, they'll give you so much money. Yeah, and why do they give you all that money? Well, they give you all that money because if you build this really expensive system with all those free credits that they give you, well, you got to keep paying for it when the credits run out. Even if they give you hundreds of thousands of dollars, it comes with an expiration also. So if you don't spend it really fast, it's like they incentivize you to spend the money really fast because it expires. And then once it expires, well, how much is your cloud bill every month now? And you got to start paying that. So we got, I don't even know how much money we got from AWS. That money ran out. So we shopped around. We said, who else will give us free money? So number 2 was Azure. And I want to say they gave us $360,000 of credits. That was also a little bit before I started. And after I started, I needed to transfer this subscription to my email address. I'm like, this will just be so much easier, so I'm going to do it. Well, it turns out Azure's ridiculous. You have to, they can't transfer a subscription. They have to cancel your sponsorship with all these credits, and then they have to set up a new sponsorship with the new email address. So guess what happened when they set up the new sponsorship after we spent most of our money? We started back over at $360,000. I didn't complain. Actually, there's a little more to the story than that. Actually, what happened was they did it, and we didn't have enough money. I'm like, what the heck? You guys are screwing us over. They're like, oh no, we'll fix that. Yeah, they fixed it. So anyway, that's why we're in Azure. So we didn't now we're trying to run our infrastructure in a way that's maintainable, and so we're just decreasing our costs.
It worked. We pay them now.
Yep.
Hi, awesome presentation. Really love your passion about the subject. Question.
Thanks.
What about backup, and what is your DR plan? Do you have one?
For what, right? For the data that we use for training, there is no, the disaster recovery is bottlenecked by how fast worst case, it's bottlenecked by how fast can we collect new data from our users, right? So we back up some data, like our reporter server, we send it, to cold storage or whatever, inexpensive storage in Azure. We run on-prem the reporter, just like the trainers and everything. In the cloud, it's just kind of the same thing. One of the first things I worked on was really making everything infrastructure as code, deploying things in an automated way. So a lot of our disaster recovery from an infrastructure perspective, not from a data perspective, is you just redeploy things. And I'm huge on putting everything in scale sets. So your recovery is built in, right? Every time you scale up, you're practicing your recovery, which is great.
Thank you.
Yeah.
So you mentioned the spot instances and stuff, and kind of balancing between instances of different sizes. Can you talk a bit about how generally particular workloads fit within particular instance sizes? I don't really know what your compute needs are, but how do you balance that out if you have certain memory compute sort of ratios that you're trying to maintain?
Yeah. So one of my goals at one point when I was one of my first goals at comma was to get our processing time, the latency from when we receive a file from a user to when it's available in Explorer, Connect, Kibana, to be under 10 minutes on average for 99.9% of our data or something like that over the course of a month. So I worked really hard on that, and I'm happy to say that our data now is processed on average under 10 seconds after we receive it. So we used to do heavier stuff like processing video files and so forth. So a lot of the solution to this was eliminating that stuff, pushing some of it back to the device, using the Q logs for really pushing people hard to use our Q logs for our processing needs, for customer-facing stuff. Figuring out what data we can train on. I always tell people it has to be based on the Q logs because we don't want to pull the raw log files to figure that stuff out. So we need the short of this long story is basically we need very small VMs. we spin up the smallest possible VMs, which helps, right? Because when we're outbid and we lose instances, we lose these spot instances, the more cores we're using, the more likely it is that someone is going to steal our VM. Like say we use 4-core machines versus 2-core machines. Well, if someone needs a 2-core machine, there's only 4 cores, well, then we're going to lose the 4-core machine. But if we're doing 2 2-core machines and someone needs 2 cores, we only lose one of them. So we use like the smallest. I pick the least expensive, the least expensive SKUs, and always do like the Azure has this great thing where you can run the operating system out of the super fast cache. So then the VMs come up like we scale up and down really fast. So yeah, we use the tiny instances, and yeah, that's all we need because we really squeeze down the processing as much as possible. Obviously, there's very little processing happening if every file we process is done in 10 seconds.
Got any more questions? Nice hat.
Quick question about infrastructure as code. Do you guys use like Terraform or Ansible, or what does that tech stack look like?
Yeah, we use Terraform. Like in my previous job, things were also in Azure, and we used to use the ARM templates. I think those are great too, but I mean, if it's not broke, you don't change it, right? We just always use Terraform, and it works great. Yeah, so we use Terraform, and then I guess you were asking like Ansible. So we use Terraform, and then I really try to use Cloud Init to bring up the VMs. Basically, I try to keep those VMs as simple as possible. So most of our VMs that run in the cloud, it uses Cloud Init to install the Azure CLI so that it can do like integrated authentication to do things like pull keys for storage accounts that have been given like role-based access. So we need the Azure CLI so that the VMs have access to things. And then Docker. So everything that we run runs in a Docker container. So we just need to basically install Docker in the Azure CLI.
Hey, so I guess I sort of wonder, in the long run, how much data do you guys keep? Like, I guess it sounded like you weren't particularly concerned if there was a case where you have like some video or other piece of data you want to train on and it gets lost, because I guess one, you can get it back, but like, do you guys store all the video you've ever collected from customers, or do you clean it up as time goes along and you like upgrade the cameras and it becomes less useful, etc.?
We don't store all the data that's ever been uploaded to us. We retain the raw data that we get for only 14 days. Because like the data, I mean, again, like keeping our cloud bill low, like I mentioned at the beginning, the storage is so expensive. Like that's how they get you. And you really can't separate things from the storage very well. Like who has crazy high bandwidth for free to cloud providers, and then they charge you if you want to pull data out of the cloud, outrageous rates, like 8 cents per gigabyte. So if they get you hooked into that storage, they really got you hooked. And so, so we just keep the data for 14 days because otherwise we'd be, even now, even keeping the data for only 14 days, our storage is by far our biggest cloud expense. And then the lower quality stuff we keep for at least a year. So like if you have Prime, you can watch your low quality video in like Connect. You should be able to back a whole year.
Great. Thank you so much, Greg.
Yeah, no problem.
All right. How many of you, with a show of hands, use openpilot? All right, now how many of you have driver monitoring upload on? All right, pretty good. Well, I'm hoping after this talk, that'll be everybody. Please welcome Weixing to the stage. He's our research engineer who's the genius behind driver monitoring.
Okay, so this one's been the elephant in the room forever. Most people love it. Some people hate it. But let's talk about it. And it's the driver monitoring in openpilot. I'll just call it DM for the rest of the talk. Which one? Does it work? All right. So here are the topics I would like to cover today to hopefully demystify comma's camera-based DM approach. Let's start. Let's start with the basics. So what's the goal of DM? What are we trying to achieve with it? As we all know, comma is proud about shipping a very good level 2 system. And as the system is getting better and better, we need to remind people that they always need to pay attention in a level 2 system to your driving surroundings. Therefore, the direct goal of the DM is to keep the driver engaged. And
This one.
oh,
It's this.
thanks. Using the wrong one. Right. And obviously, by using the camera only, driving now becomes more chill because the driver now doesn't need to touch the wheel every now and then when the system is engaged. When we say keeping the driver engaged, it means to make sure the driver is always paying attention to the role that they should be always to be ready to take over. Some examples of not paying attention includes being on your phone, falling asleep, or even simply by just looking at the car nestling for too long. Now that we have the problem in mind, let's fast forward and take a quick peek at what comma DM has achieved so far by looking at some numbers. Got here. The first one is a comparison plot between having DM and no DM, showing the cumulative. The plot shows the cumulative distributions between of distraction durations between current data and the data we had before we shipped openpilot DM. The green line is from recent fleet data, and the orange line is from running the same model on the data we had before DM was shipped. Both lines show data when the openpilot is engaged only. If we zoom into that section there, in recent data, 99.7% of the distracted events are less than 5 seconds, while in the old data, this number is 97.4%, which means DM has managed to reduce distractions more than 5 seconds by 90%, which is substantial. Here's another interesting stat. So at runtime, DM is only active when openpilot is engaged, but how about when it's not engaged? By assuming DM is always alive, we can rerun the policy and the model applying on all the logs to compare the amount of DM alerts each user will have gotten per minute, both engaged and not engaged, as shown here. So the results show that when openpilot is engaged, drivers get 60% less alerts on average when compared to when they are driving themselves. Thus, we can say that when engaged with openpilot, people pay 60% more attention, in the sense that DM helps to remind people that they need to be paying attention. It's not the fact that it beeps. It's the fact that you know it would beep at you if you don't pay enough attention. In a way, it's similar to speed limits. Say it's not about it's not about the consequences. It's mostly about the presence. Which brings us to this graph. To sum things up, DM basically achieves two things. One is that it reminds people when they're getting distracted without actually knowing being distracted. The other one, more importantly, is that it keeps people from involving in distracted behaviors in the first place. So how does everything work? We start by looking at what happens in openpilot, from sleeps to beeps. So we have the driver-facing camera that takes the picture of the driver, say here with this beautiful comma-free camera. And then the picture is fed into a neural network to estimate some parameters of the driver We call these parameters driver stage, which includes things like whether there's a face, where's the face, where are the eyes closed, where the face is looking at, stuff like that. Then we have a classical state machine that takes in the driver state, all these parameters of the driver, and process them in loop as new pictures come in. It also takes into account things like the speed of the car, and also how the camera is mounted, or even like how complex is the scene to adjust all the things. Then the system will use all these information to determine whether the driver is being too distracted, and if they do, an alert will be shown. You get the beeps. Of course, the brain of all these is the neural network model we use to extract information from the picture. Now let's zoom in more and look at the model itself. In like the more technical terms, the model is an efficient V0 vision network, which is 8-bit quantized to run on the DSP instead of the GPU, such that the DM model doesn't compete for resource with the driving model, such that they can both have room for growth. Say we want to train big model in the future for both of them, we can do that. And the two main outputs will be the driver's head pose and eye stage, which are the two cornerstones of openpilot DM. It may not seem much, but as we shall show here, we shall be showing, these two aspects are actually proven to be quite versatile when it comes to determining driver attention. Here are a few examples of DM model in action when I was driving. We can see that by just looking at only the head and the eye, you can actually catch things from simply looking away or playing with your phone when driving, or the even more subtle, like falling asleep somehow. And of course, the model works both day and night. Well, you might now wonder how the measly 8-bit model can do all these tricks. As George always says, the most important aspect of machine learning is, of course, the data. So the next talking point will be our data. The latest DM model is trained with more than 23,000 hours of driver videos uploaded from over 1,600 unique users from our fleet, which makes up roughly 25% of the total user space. Thanks to them, openpilot DM can be as good as today. We would love to see this number grow, and in the coming slides, I'm going to show what we are doing with the data and why more people should upload. Well, some people might be worried that their faces will be looked at when we label the data, and thus have concerns about privacy and stuff like that. And yes, we do have our diligent data labelers, but they are machines. So these beautiful computing clusters that Greg built are also our DM labelers. Here I have 3 pictures for them because we have 3 racks. So how are the ground truth generated? So we have been building this DM data annotation pipeline for almost 2 years now, which can do the following task in a fully automated manner, so that no human would need to look at the data, any of the data. Here are some of the examples of our auto ground truthing stack in action, where you can see faces being detected and the pose being accurately estimated, and also as well as the eyes and whether they're closed. So what's actually doing all these things are what we call the teacher models that we train separately to work specifically on our data set using a technique called transfer learning, which means the knowledge of these models are obtained from somewhere else. In this case, it's the open source data sets. So you have these open source data sets. Of course, you can naively just train some models on them, but it won't work because they look like nothing from our data, which brings us to the idea of domain adaptation. It means that we need to augment these open source data sets to make them look somewhat similar to what's in our data set. Then we can start training models on them. Speaking of domain adaptation, the idea can be also be applied to, say, when we want to retrain the model that used to work on eons to work on comma 2s. We can just start by making the eon pictures kind of pinkish to mimic the IR lighting in the comma 2. And it's also the same trick when we want to transfer the, say, the comma 2 model's knowledge into the comma free, into the comma free capable model. That's how we ship the really good comma 2. That's how we ship the. That's how we make the comma free DM model good at launch without actually using a lot of comma free data. So after all that labeling and training, now we move on to testing, which is the most integral part for us to move forward and avoid regressions. So to test, you need a metric. What is a good metric for good DM experience? Is it model accuracy? Does a high model accuracy equal to a good experience? Well, not necessarily. Well, that's not true for DM at all, actually. Usually, like 99% would be fine, but now you're assuming the 1% bad experience is evenly distributed among all users. Then, in this case, all users are enjoying 99% of the experience. But in DM, usually, 99% means 1% of the users are constantly suffering and having constant false positive or something like that, where DM doesn't work for them at all. So how do we catch them? So to catch any of such bad experiences, we crunch numbers on every device in the training set and validation set. For example, here we try to see how often each device will get alerts with some candidate model we want to ship. Each dot here represents a bit device. We can see some device get a lot of DM alerts consistently, and it's important that we understand all these positives. For example, if this happens on me, where the model constantly thinks I'm distracted while I'm not, we need to find out why. It could be because the model doesn't work well enough when wearing glasses, or is it because the policy is too strict because I squint too much into the sun or something like that? These are the questions that inspire us to write more detailed tests and fix the problems they exposed. On the right is another example of testing by worst cases. According to this distribution curve, some devices are constantly failing to detect faces. Why? Is it due to the model not working in certain lighting conditions? Or maybe it's just the lens is covered? We need to figure them out. So by visualizing all these worst cases, we can easily identify what some of the problems are and what can be fixed, either by software or hardware. Say, for example, in the red ones, they're clearly covered and they're hopeless. And then in the black images, it's probably because the IREDs are broken, and that's a hardware issue. So the takeaway is we can learn and improve things a lot by just looking at the worst cases. All right, on top of everything I've talked about so far, I would like to also add some comments about thinking DM as a machine learning problem in general. So we currently have data uploads from about 1,600 users. And below is the amount of people from who we don't get DM data from, which is 75% of all users, which means for us as a company, we are stuck with this small subset of data to build a system which is expected to work on a much larger user base than the training set size. Well, now all this looks like a disaster for overfitting, especially when we have shown that even 99% isn't good enough. In other words, the model is only guaranteed to perform well on the people who's in the training set. What's the solution then? Well, how about more people consider uploading their driver camera maybe? Well, it's just an informed recommendation. Absolutely nothing more than that. All right, seriously though, turn it on to help yourself and help others. Now, let's move on to what's next. apparently, the next big thing would be end-to-end DM, where we remove the boundary between perception and reasoning, like we did in the driving model. The DM model will have only one output called eyes on roll, unlike like in the classical model where we output like many parameters of the driver and did a lot of complex math on that and figure out whether it's distracted or something. And actually, we are now actively working on getting automatic rank through working on this end-to-end pipeline. Pretty exciting stuff. Also, to give the model more context, we are also considering making it temporal or training big models on the comma freeze 180 model to make it see more. So yeah, there are so many potential big improvements we can make to stay ahead of the DM game. Very exciting stuff. That's it from me today. Thanks for listening.
All right. How many of you are going to turn your driver monitoring toggle on? Right. All right, here we go. Jason?
Thanks, this is a lot of good info. Can you talk a little bit more? You said there were times when the DM model would kind of relax versus tighten up its requirements for paying attention. Is that more than just stopped versus not stopped right now?
So in the driving model, it outputs the probability of you like being engaged, and also the probability of you like disengage in so many seconds in the future. So we use all that information to like adaptively set the threshold based on the scene complexity that the model thinks like when it will fail, so that such that the DM model can be more relaxed when, say, it's driving on a straight highway compared to it's like stuck in traffic.
Okay, so every once in a while I see someone question, I tried closing my eyes and the DM model didn't do anything, or I tried doing this or that, or I looked away and it didn't detect anything. And a good explanation for that might be that it's relaxed a little bit because this is a simple scene with a low probability, according to the model, of the driver having to grab control.
Yeah.
Would that be fair? Okay.
Thank you.
It doesn't mean you can ever not pay attention, though.
That's right.
My question is more about future possibilities with the comma 3 and the 180-degree field of view. Obviously, there was some questions about a sentry mode and comma security and all these things. Do you think implementing some of those features into the official release of openpilot may encourage, with like a prerequisite of needing to upload your driver monitoring to record these events, could help encourage more people to use that feature and upload because they're getting more benefit from it, when right now they may just feel that it's only a benefit for comma at a cost of their privacy, where you could give them security at a cost of their privacy and they may consider it.
Yeah, so we are considering that. So actually, we are actually also considering using the comma freeze 180 like driver camera to extract some of the like information for driving, which is like the offering like we can do, like you mentioned. So what we can do is like if we can somehow make the users upload with that, and if they don't like it, they can like choose to blur out their faces, then that would be great.
Quick question for you. Are you always limited to using the DSP? Will the openpilot team ever give you more compute if you ask for it? And is there any difference between the C2's Qualcomm, I think it's an 820 or 825's DSP versus the C3's 845?
The C3 is way better. But we are only using, say, 10%, maybe 12% potential on the C2, so there's a lot of room for growth.
Got anything in the crowd? All right, we got someone upstairs.
Not really a question, but a comment. Thank you for looking at the scratching your head. Just distraction warning, because I get that all the time.
No worries. Gotcha.
All right.
You mentioned transfer learning from training on some general object detection data set with some kind of augmentation. Are you doing like self-supervised pre-training, or could you explain that a bit more?
Well, you can do augmentations like color, like mimicking, or you can do like something like Fourier domain adaptation to mimic like the sharpness on like a finer level of the image to make them look more like the ones on our data set. Does that answer your question?
And you aren't directly training the efficient net. You're training a teacher policy.
Yeah, we first generate the ground truth using the teacher networks on our data, and then we use our data and those labels to train the efficient net to make the model perform.
Have you ever considered using a monochrome IR camera? It looks like there is some color data of maybe limited use on what we saw in the demos.
We are not having problems with using like RGB IR cameras, so I don't think that's a limiting factor for us so far.
So given that this is an opt-in, are you currently tracking the users who show a high, what's it called? The distraction level on a consistent basis? And would you ever seek action to ban those users? Is that a consequence?
No.
You want to put up with the beeping. I mean, you know, if you choose to not pay attention, you're an idiot. But don't mess with your DM. If you mess with your DM, I'll ban you.
From the man himself.
You heard it.
That's right.
Hey, so kind of a broad question. So it's totally understandable why you need to like work on DM and have some way to like be able to alert the driver and even help them and perhaps even hold them accountable. Maybe that's taking it too far, but at the same time you also say stuff like, and I realize it's maybe half joking, but like we're L2, we take no accountability. So I guess what do you see as the purpose of DM to the extent that what I'm saying of the company not taking any, maybe I meant to say liability instead of accountability. Not taking liability, like, what's the purpose in light of that?
It's not like a liability level. It's more like you want you want to remind the driver that the limitation of the system and what their expectation of the system should be. And by using DM, we are ensuring that concept is always present. Does that answer the question?
I think so.
Thank you.
Since in the future you guys are going to be using the front-facing camera for the driving portion of the comma of openpilot, are you going to be doing 2 passes, basically process a frame of video for driver monitoring and then reprocess the frame again for the driving? Or is it going to be all mended into just one process?
We'll see. So now we have the super combo. Maybe there's a super combo in the future using all 3 cameras.
Hello. Have you considered incentivizing users to upload their video as an investment in improving the overall effectiveness for everybody?
Yes. I mean, if you upload, it works better on you. So, I mean, that's the direct incentive.
Comma points obviously are very valuable. The more you have, the more important you are. So. All right, that looks like it. Any other questions?
Not so much a question. I find it a little bit sometimes not working very well when the visor is down. Maybe it's a mounting of my comma. Have you tested it with different position of the visor?
You can check the visibility using the preview function in the settings if you're worried about like visibility when you're using a visor.
Great. All right, live stream. You guys are going on pause. We're going to set the stage up for a few minutes, you know, a really fun part about working at Comma is the lunchtime and dinner conversation. I think, you know, really get to spend time with the team, and I wanted to recreate that vibe on the stage. So we're just going to have a conversation with the whole team. Anyone, wherever everyone is, you guys come on down. See her over here. If you want to grab a chair. And thank you so much, Weixing.
Thank you.
All right. We got the live stream going again? Great.
Yeah, who's the strictest code reviewer out of all of you?
Adeeb.
Ah, nice.
Actually, you know what? That's a great question. Why don't we go around and anyone who didn't speak maybe wants to introduce themselves? This is Weixing, we know. We got Nick.
Yeah, Nick. I've been at the company 3 years.
Okay, what do you do, Nick?
That's a
There's no
good
rush. Take your time.
I am the head of hardware, but probably the last 6 months I've been purchasing components for Comma 3. So sourcing hard-to-find components at good prices.
Part hunter. How did you find out about Comma originally?
One of my friends from college initially shared the Bloomberg article with George from the original ILX, and kind of just started following Comma from there. After graduating college, moved back home, bought a Civic, put a Neo in it, and then just kind of just got involved from there, and now I'm here. So.
And I think you originally came on as you're doing customer.
I think at that point I was like hardware operations, so taking responsibilities from Eddie, doing like Eon production, and then moving like production and fulfillment and day-to-day operation stuff. So.
And some people might know you as Vanilla Gorilla
yes,
online.
Vanilla Gorilla online.
In the flesh.
Yes.
Hi, my name is Shane, and I've been an intern here for the past 3 months or so. Yesterday was my last day, so.
Thank you,
very,
Shane.
Very exciting.
All right. You know, Vivek came in last night. He told me he came into your office and he said, "Today's your last day, Shane." And you said, "I'm so excited."
I didn't know what to say. I'm excited for Comic-Con, that's what I meant.
Oh, okay. All right, all right.
Yeah, I worked in the openpilot team under the strictest code reviewer, Adeeb. But I learned a lot, so it was really
And
nice.
also, you run one of our most popular forks.
Yes, I used to, and then I stopped updating it because I was so busy. But it's coming soon.
Amazing. You want to pass the mic on?
Hi, my name is Yassine. I've been an intern at the research team for about 2 months now. And yeah, been working on research, training models.
You said I never asked you how you heard about Comma.
I kind of not always knew about Comma, but it was in the back of my head. Then I was browsing GitHub, and then I found Comma 10K dataset, and I thought it was cool. I looked at it, and the quality is amazing quality. So I just started training a model on it, and I realized it was cool. And yeah, that's how I got in touch.
The model was more accurate than the one we used internally. So this is how you get an internship at Comma.
Yeah, it's been an amazing time. Learned a lot of things. Yeah, it's
We're
exciting.
really glad you found us.
Yeah.
Hey, I'm Vivek. I joined as a full-time employee 2 months ago. I work in research. I interned at Comma last summer, for around 3 months. And then I finished my master's, and then I joined full-time. Yeah.
Yeah. Yay, Vivek.
I found out about Comma through the hackathon. I think I was just browsing Twitter one day, and then I saw a tweet that somebody I was following had retweeted saying, hey, comma has a hackathon. And I do a lot of hackathons, so I applied and then I came down. And then I was super excited to meet everyone. It was a fun experience. And then I came as an intern.
So happy to have you.
Thanks.
Yay. Okay, Harold, you could talk about yourself.
I guess I'm next.
Okay.
Yeah, we should probably do everyone, huh?
Just, in case someone just watches this segment. They haven't been with us all day.
All right, so I'm Harold, and I've been working at comma a little over 4 years now. I heard about it through a friend that was just telling me about self-driving stuff, and I started watching videos of George and comma, and just thought it was a very straight up, no bullshit approach to the problem, which I really liked. And then I sent an email after I graduated and started as an intern, and I'm still there.
Amazing.
Hi, my name's Robbe. I'm on the hardware team. So we developed the comma 3 over the last 2 years now, I think, something about that. I joined in the summer of 2019, straight out of university. I was really looking for a job in Belgium, but there was nothing cool around Belgium, so decided to move to San Diego instead. So yeah, that's my background.
Great. Thank you.
I'm Greg Hogan. I work on infrastructure at comma. I heard about comma because I bought a 2017 Honda CR-V. And I really wanted adaptive cruise control, and this car had it. And then when I realized it was crap, I was like, is this it? I wanted this for so long. And now I have it, and this thing's horrible, like the lane keep assist especially. So I think I was just searching the internet, and I came across somebody opened a pull request to add support to openpilot. I was like, holy crap, this is amazing. So then I started kind of following the company. I thought it was pretty cool. And then I noticed there's these bounties. So my previous job was software development, and I was like, oh, maybe I should try to make some money doing this kind of stuff that I thought was fun. So I fixed up the J2534 driver so that you could use like the diagnostic tools that come from OEM manufacturers with openpilot, or with the Panda, with the white Panda. I did one other bounty too, and I thought to myself, well, maybe I want to work here, but if I do a good job, they'll probably reach out. Sure enough, that happened, but then something weird happened. George called me for an interview, and his first sentence was something like, so, I'm interviewing you for a firmware position? And I said, oh, hang on here, buddy. I don't think you want me working on firmware. But I did see you had a cloud infrastructure engineer position on the website. And it just kind of went from there. So, yeah.
What's up, guys? Virtually Chris here. Yeah, you all probably remember me from most openpilot videos until Hubble Sphere really started taking off. I've loved comma for a long time. I started back in the Neo. I think a lot of you will remember my Building a Self-Driving Car series, where I went to my school, 3D printed some parts, and just made this really janky Neo, soldered for the first time ever on that connector, and it was not good. But yeah, I just had a Civic, decided to look up if I could get autopilot for it, found openpilot, and here I am. Now I do communications, and I'm head of production. So yeah, I've been making a lot of comma 2s over the last few months. We have, we made over 1,000 at one point in stock, and yeah, now me and my team are working on making all the comma 3s. So we have a great hardware team, or sorry, not hardware.
Production.
We have a great production team. I just want to call out, Alan, Ada, and Juan. They're our full-time production staff. They're amazing. Yeah, we're making a lot of devices right now, and we really hope you like them when you get the comma 3s. So, yeah, it's been a crazy journey, but here I am.
My name's Mitchell. I've been at comma for about 9 months now on the research team. I think I've known about comma for at least 2-3 years back, since like 2018, and it always seemed like a really cool company. But I thought like, oh, it's too cool for me. Like, I don't know how I'd even apply. And then in early 2020, I left my job up in SF. And around that time, I saw one of George's live streams, and he was saying like, hey, if you want to apply to comma to work on research, you should do the speed challenge. And that was our challenge back then. It's much easier than what we have now. And so I worked on it for a while, and I thought like, yeah, comma would be a really cool place to work. So I applied, I got in, and I've been working on training machine learning models for the last 9 months. It's been great. I really love it here.
So I'm Adeeb. I work on openpilot. I might have reviewed one of your PRs if you open a PR against openpilot.
Definitely.
And I was an intern twice, and then my total tenure at comma is about a year and a half.
I also want to add that Adeeb is a machine. He's also a full-time student and full-time employee. Thank you, Adeeb's parents, for letting him work here.
There's 2 employees not on the stage right now. You saw Willem earlier and Joost. They work in our Rotterdam office. So comma is a multinational corporation. Oh, wait. Where's Igor? Oh, Igor's back there.
Igor, come on up. And actually, Igor is our... Oh, he started after you, technically. Igor's the latest hire.
Someone's got to guard those comma 3s. Nice.
He's a soldier. Thank you, Igor. No, just talk into it.
Okay. So I knew about comma.ai, I would say from 2017 to 2018, but at that time I just arrived to United States and I had my first car that is not supported. So I was waiting and waiting, then forgot about it, and I would say in November 2020, I decided that I need to buy a device with openpilot. At that time I had a Mustang, so I decided to sell my Mustang and bought Corolla. Right now I'm full-time employee for a month. But before that I was as intern for 2.5 months, and I was working, I was working on a Red Panda. So that's my project.
Great.
Igor was also a member of EPOT, which you guys heard about earlier. So yeah, like I said, Willem and Joost, we would have loved to have them here, but unfortunately, the people at the border felt differently. And you can't hide by holding a microphone out.
I like to hide. Nice. Let's see. I think I met George in 2017. I was hosting an event at NIPS, which I don't know if you know is now called NeurIPS. That's because of me. And shout out to Rivatez.
The event was called TITS.
It's true. And yeah, because you can't have, it did. You can't have nips without tits, I think we said. Anyway, George was speaking at the event. At the time, he was giving a talk about crypto kitties.
Got to chill your bags.
That's right. And we were running some errands for the event. And I was like, what is this thing in your car? And he's like, oh, this is a self-driving car. And if you remember Willem's talk, he had that graphic of the green boxes and the red boxes. And I think the first question I asked is it going to stop at this stoplight? And you're like, well, maybe one day. And I was, enamored with the project since then. And in 2019, I came down. George and I went to China to try to find more phones. And on the trip, I was talking about some ideas and different thoughts for the comma 2 launch. And George, like, why don't you come down and help get the company prepared for the launch? So I worked on that for about 6 months. We launched at CES 2020. Hopefully we'll be back again in 2022. If things are allowed in person again.
The Comma 3 was supposed to launch at CES this year, but we never would have had it finished.
Well, it came on in June 1st. George called me. He's like, "We come down. I think it's ready. We're ready to launch the Comma 3." One year and 1 month later. I thought, he's like, I was like, I don't really know a lot about it. He's like, it should be ready like by December. I was like, all right.
We had one. Worked sometimes.
Okay. He's like, and some parts have 6 months lead times. Just like make sure you order those. He's like, I'm be gone for a month. Like, you'll figure it out. And here we are today on the stage. What's that? Oh, never mind. And that's how I got here. Yeah. Weixing got skipped.
All right. So I went to school in Michigan. It was cold. I just wanted a job in California, and then I find comma on this startup website. It's pretty cool, and that's it.
That's what you wanted to say. Well, first off, we do all have hot mics, so everybody tapping the mics. I hear a lot of tapping. My name is George. I was working for this company, this AI startup in the East Bay. My friend approached me, and he's like, yo, Elon needs someone to build vision for autopilot. I was interested. I met with Elon. We almost had a deal. There was a miscommunication. I don't know. I don't like to lose, So I'm thinking, all right, how do you beat Elon at self-driving cars? But it turns out it's not beating Elon. It turns out you're all on the same team. It turns out it's beating, Honda. So yeah, 5 years later, I'm still here. It kind of works. The software's nice,
So nice.
Never thought it's not, it's like I said, I'm a cheerleader. Yeah, the software's nice. Let's see. Back when I started Comma, that was during a smoking weed every day phase. It's like, yo, I'm gonna start a company. Yeah, Silicon Valley shit. Yeah. And then you stop smoking weed and you're like, what did I do? It's like having a kid, man. Yeah, here we are, and it's it's been a journey, and I think the journey's going to continue, and I think when lay back and let the winnings start rolling, no, just continue to work hard forever, but it's the same thing.
I thought maybe you guys could talk about what your favorite things about Comma are. Harald?
It's kind of putting me on the spot here.
Ice cream. Free ice cream.
Yeah, I do like the food a lot. The food's really great. But on a professional level, there's just not much red tape or nonsense to deal with. If you want to try any approaches or you think there's a better way of doing things, I think there's not really many obstacles in the way. And I think that really promotes doing good work and keeping people excited.
I care a lot about being right, but not at the expense of being wrong.
Yeah.
So I guess I can go if everyone else is going to be silent. One of the things I really like is, so I've worked for small companies that got so small that they closed the office, and I worked from home for a few years. Then I worked for a big corporation. I grew up on a dairy farm in Iowa, so I work really hard. People tell me, and
it's true.
Anyway, I really want something from everything I put in. I have all this energy I put into things, and I really want it to be something. And being a user of of the actual company, I just saw the company. I thought to myself, like, this is my chance. I should try. And like I still feel that way today. Like that's why I work here, because I think, is there a chance we don't solve self-driving cars? I think it's possible. I'm kind of a pessimist. I think anything's possible. But if anyone is going to win, like if I have any chance, I think this is the company, and that's why I work here. I love it. And even if we don't, it's great. So.
I'm going to be less serious about that. So in comma, you can use company cars, So I own several cars that I would say impractical. They work 20% of the time, so having access to company cars is a great perk. Thanks.
You meet the requirement of having reliable transportation now because of the company, right?
Yes.
A few months ago, Chris did a recruiting video that went on the website and had interviewed me on what I liked about working at Comma, and I'll just reiterate those points because they're still true. One, building something that's not been built before. How do you build a Comma 3? Like, there's no instruction book. Okay, add some cameras to a SOM and that sort of thing. But the design is, fluid, and we can make our own decisions based on this thing. The other thing, too, being just being able to go directly to the openpilot team to give feedback on specific issues. I myself have a Honda Civic. I use our system quite frequently, and if I see any little small item, I can easily just report it, and it's within reason looked at pretty quickly. I used to work at a larger company, and this was not the case. Issues with the app. The company was so large. Okay, you got to put it in Jira, and like, who's gonna look at that? And like, when are they gonna look at that? And do I ever know if they're really looking at it because they're in a different building? No, I just walk down, and I think that's probably the biggest thing why I like working at Comma, and the food is also nice as well. So.
The Comma 3 sells well. We're getting a dinner chef.
I can speak about a few reasons why I chose to work at Comma. So I had to make a decision sometime earlier this year. I think one reason, it's a big reason, is that we build something real, like something tangible, and that means a lot to me, that I can really hold it, and it's real, and it's not like nobody's trying to scam you, right? Like, it's a real thing that you put on your car and then you it drives. And that really feels like magic to me even now when it's like you're thinking about something and then you drive it a lot of times, and then one day I'm like, paying attention to it, I'm like, oh my God, this is actually driving, and that feels really cool. And that's super important to me. That's a big reason. I also think Comma is like super aligned with the final users, right? We want to win, and like you will win when we will win, and we will win when you will win. It's like the same thing. Like there's no side angle. Like we're not trying to steal your data or pull one over your head. It's like it's a real thing. Right? It's like, yeah, it's real, and our incentives are extremely aligned. Which, you might think that's common, but it's not as common as it should be, right? So that's very nice. Another reason why I like working is the people. I really like, so I was here last summer, and I really enjoyed just hanging out with people, and especially while having lunch. We were recently discussing which are real sports and which are fake sports, and this was like a real thing that we discussed and debated for like half an hour. So that's fake. Oh no, basketball is real. Our current criteria is sports where the world, the supreme athletes are fat, is not a real sport. So that's like our current criteria. It's just subject to changes. And finally, we have a lot of fun in office, apart from like having fun doing what we do, but also generally having fun. We play GeoGuessr in the evenings, and the winner gets one office furniture. So that's also a good perk. These are the reasons why I like working on comma.
I just realized today I'm getting my Izzy's back. It's been months. We bet them in GeoGuessr. We all bet our worst, like the thing we don't want to lose. And I lost along with like half of us, and we all couldn't drink the things we liked. It's back. Drinks are back. Yeah.
So I don't know if you noticed, but you can see the windows up there are open, and the temperature in here is perfect. So I come from Texas, and so it's 100 degrees there right now. So the perfect weather is the reason that I came here. But more seriously, this is my first experience like in open source software and like a professional setting. So I knew a little bit of Git and GitHub before, and I think not having to relearn like a proprietary set of like software management systems and everything's just out there, and you can request help from the community if you need to, or yeah, the community support's been pretty cool about this whole thing. And yeah, I just like how everybody here knows each other, and it just feels like a big family. And somebody at lunch, I think, one day said that's how your company succeeds. Everybody knows each other, and it feels like a family. So those are the reasons.
So I'm doing a PhD in computer science, and they always teach us that we have to try things, and then we have to try to break things and discover stuff, be bold, and do experiments and try stuff. But then when you go in a company, you can't do that because they just tell you, hey, you have to write this piece of code, and you have these specs, you can't go outside, and it's kind of annoying. And I loved that at comma, we are given the opportunity to try stuff, and it's really easy. The barrier to experiments and the time from experiment to shipping the product is really short. So that's what I love about comma. And yeah, I just want to keep experimenting and keep doing research.
One of the cool things spending a lot of time in tech is I think everyone here wants to make the thing work better. And it's kind of clear what better means, and it's nice. Right? Because when you come to a company, a lot of the times, the ground's kind of already paved. Right? There's no space. There's no space to expand. There's no, how do you make Facebook better? You don't know. I used to work at Facebook. I show up there. It's like, what can I do that would possibly, I don't even know what better means in the context of Facebook. So a nice thing about comma is it's very clear. And everybody who works here can see it get better and can work on the things like, at least I think we all share a definition of what better means. And that includes you guys. So something that's pretty cool. Let's just, if you guys want to throw out topics, we'll just kind of talk about them. Auto-tune, like T-Pain? Let's talk. I don't know about that. Who wants to talk about auto-tuning? Vivek?
About what?
I mean, I can briefly say some things about it. It's something that seems like it might be necessary at some point. We really, until recently, had no idea how cars were tuned, whether cars were performing well or not. The only way we'd know is like people would be like, oh, my Subaru doesn't drive well. And then somebody else was like, oh, I have a Subaru too and it sucks as well. And recently Vivek's been working on writing a lot of metrics that can really tell us exactly which cars are performing poorly and in which ways. We recently started doing some metrics on longitudinal, and turns out that most Hondas are horribly tuned for longitudinal. And so this is the first step. We're going to try to understand which cars are bad and in which ways. Then we can think about the quickest way to solve them, and perhaps that somehow leads to auto-tuning of some shape or form.
I was tempted to post it. Vivek posted a PDF on our internal Slack that said which cars worked well and which cars didn't.
No, we actually wanted to post those, I think, on GitHub discussions. I think it'd be nice.
All right.
Yeah, that's what we wrote them
That
for,
sounds
so.
good.
How-
I apologize in advance to Chevy Volt owners. It's not you, it's your car.
I want a megawatt of power for our servers.
Guys.
And I'm not even joking. Like, I would be so happy if we found an office, like, even if we get the office that we're at now, somehow. In a dam.
In my office, there's a cork board, and it has a list of everything we can do after we launch the comma 3. And the number one thing is find the team a new office. We want to find a long-term home that has all of our power needs solved. We want a fancy kitchen and a gym and
Big parking lot. I want to buy a lot more
we're
cars.
gonna get
I
20
love buying
cars. George asked that it look like a spaceship, so it's gonna look like a spaceship.
All right, that's negligible. Power and cars.
And actually, our commercial realtor, Bill, is here tonight. Thank you for coming. That's how serious we are about this office. We're very excited. San Diego is great. There's not a lot of traffic here. It's easy. Originally, our goal was to be near a highway. San Diego is a large highway, so that's worked out very well for us. I don't know if people know the original story of how we got down here, but comma used to be located in SF, and we were looking for a new office. And I think it was you and Ricardo, you guys couldn't find anything you really loved that met all of our requirements. A spaceship, that's a hard thing to find.
We went and looked at some spaces in SF, and you like went outside, and I was like, this is this much money? I don't know. We had our cars broken into twice. We had our office broken into. It's insane up there.
So the team at the time, rank choice voted, and I think San Diego was first. I think LA was a close second. I wasn't there, but this is what I've heard.
And staying in SF was a...
That's because it was funny, but we never really hired anyone. No one here came from SF. So we were like, all right, it's time to move. And that's how we got down here. Really, really enjoy it. Yeah. Jason?
Going back to tuning for a second, and this might be kind of a dumb question. First off, I've been playing with openpilot for like 3 years, and thank you to everyone up there that has answered all of my dumb questions. Most of my questions are getting less dumb over time. So my question is this. For the driving task of openpilot, you've made a big deal, and I understand it, about doing what a human would do. But everything about controls is hand-coded, is classical. Humans don't drive by doing a bunch of math and predicting exactly what the car does. They can get in any car and just drive it no matter what the steering ratio is, no matter if it's slipping a tiny bit. Is the way controls works now, is it going to work that way forever? And why does it need to work the way it does now? Why do you have to have that precision prediction of what the car will do in order to drive it?
So the alternative would be to use a machine learning approach for controls.
Okay.
Controls is superhuman with these mathematical optimizers, right? Unlike planning, which it's unclear what the good definition is, right? Because from Harold's presentation, where what should your weights be on the planner, for controls, you can actually come up with a very good set of weights, and you can execute these in a superhuman manner. Maybe you saw, I think it was Marty, the self-driving DeLorean, that was doing the perfect drifting figure eights. Controls is already superhuman using classical techniques. So in order to achieve superhuman driving performance, we don't need machine learning. And also, I don't think it's as good. I haven't seen good machine learning control approaches. Maybe if you use RL, but then there's a question of what you're going to do RL in. Do you want to do RL in a simulator? How good's your simulator? Do you want to do RL on the road? Well, you can't really do that. So That's why we keep
So
it the way it
it's
is. And
done-
yes, I imagine it in the final system.
So it's done in classical code because you can define the problem really well, so you can solve the problem really well in code.
Exactly.
Okay.
Hey, thanks. Can you guys speak a little bit about the interface between the Discord community and all the team members? Like, I'm sure a lot of you aren't on the Discord, but you know, it's just very cool to interact with the company as like a user, and then talking to someone you don't know who they are, and they're giving you like super answers, or they're ignoring you. So it's an adventure.
We're on the Discord. We have a special color. You can talk to us just like normal. We're pink, yes. Fuchsia? Pink? I don't know. There we go.
Yeah, the Discord's probably one of the coolest things about comma in our community is that you can report feedback in the Discord, and someone on the research team is going to look at it same day if it's like a concern, right? So I mean, you don't get that anywhere else. So thank you all for being a part of the Discord community, and yeah, it's a great place to report problems and stuff.
Wish everyone in Discord knew that we could tell them, like how to make a good report.
Yeah. When you join the Discord, look for questions before you ask questions, or look for answers before you ask questions. A lot of the times, we have the answers on our website, on the wiki, or as like Eric likes to say, where's Eric? I don't know. Check the pins is what Eric says. But yeah, if you have a reasonable question, someone's going to be there to answer it, and if you have any issues, someone's going to be there to help you. So that's really good, because it's kind of all a community effort. Your community porting your cars. How do you install this in your car? I mean, like maybe you're the only one with the volts, so you got to tell people how to install it. So yeah.
I don't know if this came out in the comma 3 reveal, but is there a RAM memory difference between the C2 and the C3? Or is it the same amount of RAM?
Usually it's the same amount of RAM. It's the same amount of RAM.
Okay, should we tell them?
OpenPilot uses very little RAM. We'll say that.
Hi, I have a question. What does the team feel are barriers of entry for new users?
If you have a supported car, it should be pretty easy.
Something we've spent a lot of time thinking about, also on the cork board, is UX. We know that our ecosystem can be the bar to get into it is pretty high, and we want to keep it pretty high, but also we don't like when there's bugs or problems or errors. We want to continue to improve our communication and our documentation. You'll see when we shipped the comma 2, it came with a tiny pamphlet, and it just said, get your phone, go to this website. We're trying to increase documentation and the quality of our documentation. I think we'll continue to get better with the products over time.
The comma 3 still is a dev kit. OpenPilot is not 1.0 software yet. We like people in our community and people using these products to have some, it's not even technical knowledge, it's the willingness to search for technical solutions. It makes for a better community, and it makes for a better experience while we're developing the product.
I think in some sense it's also like a lot of people, like friends from me, like they don't really know about comma yet. They are technical and they do want to solve this stuff, but they actually don't really know about comma yet. And like you tell them about it and they figure it out and like, oh, this is great. And then they buy one and then they drive with it and they tell their friends. Like I think at some point there will be some kind of like critical mass thing going where like this will spread a little faster, but yeah, it's pretty amazing.
Do you think that as you continue to grow, that Discord will no longer be a scalable enough platform? You might have to move to a more like Zendesk kind of approach with knowledge base articles, or do you want to keep that, fostering that community like you mentioned?
I think we always want there to be a Discord. Maybe there'll just be a test before you can enter it.
What about the discounted prime without SIM card? I'm like from Europe, so. No, discounted prime without SIM card, because like I'm from Europe, so the prime is cool. I like most of the prices probably the same.
The problem with that is we have a saying at comma that every line of code is worth $50. So it would take a good number of lines to implement that, and I don't think they'd pay for themselves. This may change at some point, but at least for now, Europe Prime is what it is. Maybe we could do it. What would you pay?
Sorry? What did you say?
What do you think's fair?
20, 15.
Instead of 24, 20?
Don't you have 30?
Common Prime is 24.
I mean,
all right, what do we think? 16? No, 16 for if you don't use the SIM?
15 would be cool.
Oh, well, but the people get the SIM card with 24. Yeah. If it's easy to code, 20 to, well, no, I can make it 16, I think.
Make 15.
T-Mobile's expensive. Whoa, 15, whoa. Well, that's way too cheap. I have an idea. We'll keep it 24, but we'll raise everyone else's prime to 40. Prices go up tomorrow. Do you want to say?
I got a question for George. I think you mentioned earlier that if you had known what the company would turn into 5 years from, today, from 5 years ago, you said that you wouldn't have created the company. I was wondering if you could expand on that, maybe talk about some of your regrets.
I wouldn't go that far. What else would have I done? I'm aging out of my competitive prime. It's ups and downs. It's a lot nicer now. It's nice to be profitable. It was very stressful when you realize you're not profitable and that you're losing money every month. And what do? Do you shut it down? When things make money, well, they have kind of a intrinsic, so do I regret it now? Of course not. It's nice now, but no, I think, again, it was a lot of just kind of personal letdowns with the business world and a lot of the people I encountered. I was in the hacking world before that and liked almost everyone I met. You could just like right away, or some guys were here, we were talking about some game console exploits, and like right away it's a shared language and it's cool and you respect skill and talent. Whereas in the business world, it's not this. But we try to insulate from that as much as possible. And I'm very proud of everybody up here for building the comma 3. I always wanted to be part of a team that shipped awesome consumer electronics like that. I love consumer electronics. I wish there were more things like the comma 3 for me to buy. I love these things. I buy them all.
I think most of the team has a robot vacuum now.
Yeah? You guys all buy the Roborock?
Mine has a LiDAR.
You have the Nito, right?
I got the Nito, yeah. It's old now. I think.
The Roborock actually just sent me a message that it's stuck. My vacuum got stuck about 30 minutes ago and needs help. So I guess I'll have to go home at some point and help it out.
Hi, I saw that on eBay an Apple II signed by Steve Jobs and Steve Wozniak sold for 40 grand last November. So, George, will you sign my comma 2?
For 40 grand.
I'll buy a comma 3 if you do.
You know what? Sold.
Does this need to go into like escrow now?
We'll use the honor system, but this is we only have one of these in stock.
Just out of curiosity,
before you got hired?
Yeah.
I guess yeah. If you want the best self-driving car system, your best chance is to like work for a company that builds it.
You get the good hardware here before everybody.
Is there anything you guys are looking forward to with the Comma 3 that you can say as far as like features you're looking forward to working on? It can be general, but just things that you are excited about this new device helping you guys like come into work every day and push forward.
I can say some things. We were just talking a lot about the desire problem at work with if there's a fork or an exit, you take the exit, you not take the exit. It's kind of all acceptable if you don't know where to go. And if we can implement nav correctly, then the model can just do what it needs to do to get you where you want to go. So I'm pretty excited about that.
Yeah, I had the same one. I think we think nav's going to be fun and easy.
We always think that before we start working on it.
I'm really excited in the last few weeks. Adeeb and I have been working on new UI on Shane. So you'll see some new interface stuff on openpilot, and just seeing it on the stress test has got me really excited about continuing to update the design of openpilot.
I hear Shane and Igor stayed up all night last night getting those replays working on those devices. But is that actually replaying? Like, that's awesome.
Thanks, guys.
So one of the hardware features that I'm really excited about, that's one of the hardware guys obviously, is that like all of the sensors are now coupled to like the same synchronization line. Like this is something that wasn't possible in Comma 2. Like you'd have these sensor events from like accelerometer and even the image sensors coming in, and you'd kind of have to like guess when they were actually recorded. Well now like they're all synced, they're all on the same lines. You can even sync them up to GPS time if you wanted to. So I think that's really cool.
There's a lot of cool stuff we can do with Agnos too. I think boot time, somebody asked about this earlier. This is something I'm really excited to drive down. Maybe not 5 seconds at first, but I think there's tons of low-hanging fruit in Agnos. It's already better than EOS. You have apt, you have pip. It's great. But there's tons of low-hanging fruit like reducing boot time, and there's a lot of stuff to kind of chip away at and use a real Linux operating system and not be stuck with Android. We're still cleaning up some of this Android stuff.
Great. Do we have any outstanding questions? If not, I'm going to wrap up.
One more. Now that you're releasing the newest version of the hardware, are there plans for the next version, or is that a too early question to ask? Or kind of tying in with that, are there other how do you approach that? Are there just new ideas like, oh, we could do this, we could do that? You know.
Comma 3 forever.
What should we do if there's this car that meets all the requirements for being officially supported, but it's on the community supported list, asking for a friend? My friend's name is Erich, actually.
The Toyotas are already officially supported.
Yeah, Toyotas, you're all good. They're all officially supported, even Lexus. No, you're asking about VW, I assume.
I'm sure Erich was concerned on my behalf.
No, they're not officially yet. We have to do A/B tests. Yeah, we got to take the car out. Well, I think Willem showed a picture of our original A/B tests. So we got to find some time. We have a lot of safety testing to do to bring some cars out of dash cam mode too. So we do own an Audi, but
Hey, that's the first step, you know? VW, Chrysler.
Yeah, we are thinking about buying a new car.
yeah, should we do a poll?
We can't decide. There's been a lot of indecision on the team on our next car.
Shout out a car.
Sprinter.
Sprinter.
That's a flex ray.
Hey, can we just like
It's flex ray.
go all in with the flex ray? I want an S-Class again, but with openpilot.
Purple Panda.
The purple Panda? That's not a car.
It's not going to be a Panda, it's going to be a harness.
Flex ray harness.
purchasing conversation goes.
No, but to answer Jason's question, VW hopefully will be official soon, at least the Audi A3 that we own. It's just kind of been in the queue while we're making comma 3s incredible. Now we came back to...
And for the record, Adeeb already told me that, but Eric said I wasn't making enough trouble over here.
Because in one of the talks, it sounded like Comma said they were actually looking into Toyota security key, but from what I thought, it wasn't going to actually start till 2022. I personally think Toyota is the best in the world. I know a lot of people have sold their Hondas just to get a Toyota. But anyway, I think that the security issue is pretty big, so I want to kind of know from Comma if they really do have some solid plans to look into it.
So we looked into it a bit. I think Willem just looked into it a bit and just kind of understand what the scope of the issue was. And then we just decided this isn't affecting too many cars yet. It's not where we're choosing. We've aggressively chosen in the last year or so to not spend time on specific cars. We've spent almost all of our time doing things that improve everybody's experience with openpilot. Now that the comma 3's out, maybe we can get back to doing stuff that helps some subset of the users, but we've really been pushing on the experience that every user sees.
I'm counting on the community for that one. One of you out there, we put $5,000 of Comma's hard-earned money up. What's the total bounty now?
I think it's like 8,000 something, but honestly, you know, a lot of the community is wondering if you still have that hacker blood in you.
Whoa!
That's some fighting words. Fighting words, Eric.
Now it's happening.
Wow. I think that's a great note to end our group talk on.
All right. We'll contribute a comma 3 to the bounty. There's a cross-country edition.
Woo!
One more thing to remind you guys about. You guys know Comma Jeopardy is tonight. The prize has a $15,000 value. $15,000.
It's true.
Retail value. You can fly with it on a plane.
Maybe. I don't know. It's kind of heavy.
Yeah, well, you might have to pay extra for your suitcase weight limit.
I couldn't carry it myself.
Hey, you get a rolling suitcase.
You can split it. We are playing in teams, so yeah, it's much more manageable in 3. Yeah. It's great. I'm glad you brought up logistics, Comma Jeopardy. It's around 5:30. I think we're going to say goodbye to the world. Thank you, everyone, for tuning in today.
Bye, live stream.
Woo!
Bye, Mom.